Okay, it's loading, but typically when it's loading, it's also starting. Okay, now YouTube Live. Good. And Carlos, you can start. We can start. So the first speaker of the session is Carlos Nunez from Swansea University, and you can start.
Thank you very much. All right. So thanks obviously to the organizer for putting together this conference and for the invitation. That's the title of the talk. What I will be discussing is work in the area of ADS-CFT. Okay. So there are many technical details. I'll try to avoid many of them. I will try to focus mostly on the ideas and the outcomes of this program. The main idea of the talk will be to discuss the mapping between certain superconformal field theories and certain string theory backgrounds, okay, in diverse situations, in diverse dimensions. Then as a prediction of this mapping, I will discuss some aspects of integrability of string backgrounds and integrability in the associated quantum field theories. Today I will leave, because of the shortness of the talk, any comment on renormalization group flows away from conformal points, but the final goal of all this line of research would be to calculate correlation functions in the conformal theories, in their deformations, and along the RG flows. So today we'll focus on two examples. The first one that I will discuss in the most detail will be an example in n=2 conformal theories in 4 dimensions, just because we share a common language there probably. And then with much less detail, a thing in 5 dimensions with n=1 conformal theories. There are other examples I've been working in the last year and a half involving 2-dimensional theories, quantum mechanics conformal, and 6-dimensional theories. The lessons I will discuss today are quite generic, okay? And this is a list of the co-authors with which some of this work was done. And I will describe a mix of the papers of the last year and a half and some contributions that they did by themselves, okay? So because of the character of this conference, I thought it was convenient, because not everybody needs to be completely familiar with what ADS-CFT is, what the Maldacena conjecture is. I thought it would be nice to start with one transparency, trying to say clearly what's the goal here, right? Or what ADS-CFT is. Let me start with that. So the Maldacena conjecture is a duality, okay? Like many other dualities, it proposes the complete equivalence between 2 physical systems. One of the physical systems is a theory of quantum gravity formulated on a space that is asymptotically anti-de Sitter in different dimensions, okay? Being this space asymptotically anti-de Sitter has a boundary, okay? And in order to define the theory of quantum gravity on that space, you have to give the boundary values of the fields of the theory when defining the path integral, right? So there are these boundary values, these phi b, that are part of the definition of the theory of gravity. The proposal of Maldacena is that this is completely equivalent to the partition function of a conformal field theory in 1 dimension less, where these boundary values of the theory of gravity act as external sources for gauge invariant operators of the conformal theory. This is the Maldacena conjecture, together with the refinements made by Gabser, Klebanov, and Polyakov, and Witten in a different paper. The reason why this is useful, the reason why we are going to use this in this talk, is because calculating semi-classically in a theory of gravity, you get this when you study the conjecture in some detail, calculating semi-classically in the theory of gravity, namely approximating this path integral by saddle point and basically working with the action of gravity at the classical level, you learn about non-perturbative aspects of the conformal theory, okay? So this is the usefulness of the thing. Of course, there is another arrow where you do a simple semi-classical calculation in conformal theory, and in principle, you could learn about gravity. And one aspect of this conjecture that I will use again and again in this talk is that the theory of gravity and the asymptotically conformal theory, they both have the same global symmetries in the theory in the field theory, the global symmetries are the same as the isometries in the theory of gravity. Okay, so this is the main idea I will be working with. Let me now try to tell you where I'm going to apply this. So I'm going to focus for today's talk on what are called superconformal field theories in different dimensions. Okay, so here you have a list of different dimensions on which there are theories that are supersymmetric and conformal at the same time. And you see there names of colleagues who have worked either on the field theory aspects or on the string theory, namely holographic aspects of these systems. I would like to start discussing the example of theories that were introduced by Gaiotto, and that then these colleagues, Gaiotto, Maldacena, Jaroni, etc., Stefanski, and Reid Edwards, worked on the holographic description. I want to start with that. Then I will move very briefly to the 5-dimensional case, and all other cases have been worked out. In all these systems, it happens that the symmetries that are imposed on the systems are supersymmetry, in this particular case, 8 Poincare supersymmetries, and this implies, this is part of the superconformal algebra, that there is at least an SU2R symmetry, okay? Kind of a global symmetry of the field theory. This implies, because these global symmetries have to be captured by isometries in the string configuration, that there has to be, because these are d-dimensional conformal theories, an ADS d+1, and at least a two-sphere to take care of the SU2R symmetry. Okay, there is some internal part of the space. We are going to see this in examples. And there are Neves-Schwarz and Ramond fields that complete the configuration to give a solution to the string equations of motion. All the functions that we see here, this F1, F2, etc., and all the functions that appear in the Neves-Schwarz and Ramond fields, they can only depend, in order to preserve these isometries, on the coordinates here and those two. Okay? And we are going to see examples of this in a second. Generically, and this is what I'm going to show now in examples, generically what happens is that when you impose supersymmetry on this system, you write a set of BPS equations. These BPS equations are nonlinear, partial differential equations, and coupled. So the problem is quite hopeless at first sight, but then you start doing algebraic manipulations with these partial differential equations, and you are able to write all of these functions that appear in the background and in the Ramond and the Neves-Schwarz fields in terms of just one single function. I will refer to it as potential function, and it will happen in all these different examples in different dimensions that the potential function satisfies a linear second-order equation. This Laplace-like equation is a Laplace equation, needs of some boundary conditions, and here is where the kinematic information, the matter content of the quantum field theory enters. I'm going to describe this procedure in one example and briefly in another. So let's see this in examples. I will start with the 4-dimensional n=2 conformal theories, continue with 5-dimensional case, and leave out of the presentation these other examples work not long ago. So let me tell you the field theories in 4 dimensions that I want to have in mind. The field theories could be thought as sort of generalizations of the standard model. These are quiver field theories, groups SUN1, SUN2, up to SUNP, with flavor groups, right? The color groups are joined by what are called bifundamentals. In the language of supersymmetric theories, they are what are called hypermultiplets. Similarly, they are joined with bifundamentals with the flavor groups. And these theories, because they are conformal for a particular choice of the numbers N1 and 2 up to NP, these theories, because they are conformal, they enjoy the group SO24, okay? And because they are supersymmetric and conformal, they have a global symmetry that is SU2 times U1, okay? So the associated background will have to capture this as isometries. We'll have to have an ADS5 to take care of the conformal group in 4 dimensions, to take care of this a two-sphere, to take care of this a circle, okay? Let me say something before we go into the background about the field theoretical description. These theories, they are conformal when their beta function is 0. Their beta function for this particular type of theories is exact, is one loop exact. And it can be calculated to be, and let me say it this way, and I'm writing it better in the next slide, twice the number of colors minus the number of flavors. So for example, for this group to be conformal, 2N1 has to be the same as F1 plus N2. This acts as a flavor group for this. 2N2 has to be the same as N1 plus N3 plus F2, etc. So the imposing conformality here implies a set of equalities, right? And all this can be packed very nicely in a function. It's a convex polygonal function that starts at 0, ends at p plus 1, is 0 at 0, 0 at p plus 1, and then at x equals 1 is n1, at x equals 2 is n2. So you see it's a convex polygonal function of that form. The integer values are the ranks of these color groups, okay? And if you take the derivative of this function, okay, you have a discontinuous function like that. If you take the second derivative, you observe that you have delta functions whose coefficients, like this one here, are precisely, if you look here on top, the number of flavors associated with the first color group, similar for the second, and etc. So this rank function is a quite smart fashion of capturing this same information just in a function, right? So it knows about all the matter content of the theory. Let me now move into the holographic description of this system. This was first attacked by Lin, Lunin, and Maldacena, completed then by Gaiotto and Maldacena. They proposed string background that should capture all the isometries and all the dynamics, obviously, of these conformal theories. They propose that it needs to have an ADS5, a two-sphere, and a circle. That's to take care of the isometries. And then there are two remaining directions. There are some Ramon and Neves-Schwarz fields compatible with these isometries, and all these functions from F1 to F8 can only depend on these two coordinates. Okay, so you impose supersymmetry on this system, and what you find is that these functions from F1 to F8 solve nonlinear uncoupled partial differential equations. Okay, you operate with these equations, you replace one in the other, make different manipulations, and you are able to write all these functions from F1 to F8 in terms of just one single function and its derivatives, like for example here or there, and there are expressions for the rest. The equations that this single function, this potential function satisfies is a Laplace-like equation, as written there, is partial differential linear equation that needs of some boundary conditions, and this is the most interesting part. The rank function we were describing before acts as a boundary condition to this problem. Okay? So if we sit down with this problem and we had half hour, 40 minutes, we would reach, after separation of variables and imposing of boundary conditions, to a solution that is in terms of a Fourier Bessel series, where the coefficients are basically the Fourier transform of the rank function. So if you want to think about this algorithmically, the way to think about this is the following. Pick up your favorite conformal theory in 4 dimensions, n equals 2 conformal theory in 4 dimensions. Choose the numbers n1, n2, np, and f's to be such that they satisfy this, because that will imply they are conformal. Write the rank function, okay, is written there. Then come to this solution to the Laplace-like equation, write explicitly the potential function with those coefficients particularized to the case you decided, and then come back here, use the expressions of the functions in terms of the potential, replace the functions there, and you have there the holographic description of the quantum field theory. This holographic description is supposed to know about perturbative, both perturbative and non-perturbative aspects of the quantum field theory. Okay? So there are different tests for this proposal. One of the tests comes from calculating the number of brains in the holographic picture and making a correspondence with the color and flavor charges of the quantum field theory. There are many other things that can be calculated exactly both in the quantum field theory and in the gravity theory, and those act as tests. There are other things that are predictions. One particularly nice test is what is called the one provided by the counting of number of degrees of freedom of the theory. In 4-dimensional n equals 2 theories, there are two central charges, A and C. They have these expressions in terms of the number of vectors and number of hypers. And just to take one example, for a particular field theory like this one here, one can write a rank function, one can calculate number of vectors and number of hypers, calculate A and C, and calculate this quantity that counts the same on the gravity side, and find that to lead in order, when this equivalence is trustable, they are exactly the same. This is just one test. There are many other tests. Below, in 2 or 3 transparencies, I will describe for you one prediction of this holographic correspondence. In far less detail, allow me to comment on what happens for 5-dimensional n equals 1 conformal theories. These 5-dimensional gauge theories are non-renormalizable. They are argued to flow to a strong coupling fixed point in the UV. And what one is going to describe with this is this strong coupling fixed point. So you may think about field theories like this, right? Again, you can associate them with a rank function. For this type of systems, because they are supposed to flow to a conformal point at high energies, you write a background that contains an ADS6 taking care of the conformality, a two-sphere taking care of the SU2R symmetry of this system, and these are the remaining coordinates. This is the full configuration. And once again, here it happens that all these functions solve couple nonlinear partial differential equations that you process them and you write them, all of them, in terms of a potential function. This potential function solves a very nice Laplace problem. This Laplace problem can be put in complete equivalence with a very simple electromagnetism problem of two conducting plates at zero potential with a density of charge. So basically, by solving this for the density of charge equal to whichever is the rank function you decided to use, you are solving the potential problem for this case. You come back here and you form your holographic background. Okay, so it's exactly as it happened in the 4-dimensional case. There are many checks for this. Some are protected quantities that can be calculated both in conformal theory and in semi-classical gravity. And the description I presented here, I just presented because it's 1 day old, appear on Monday, is completely analog and complementary with a very nice description that since 3 years ago, these colleagues have pushed and has many tests. The good thing about this is it's very easy to work with. That's why I mention it here. So, brief summary up to this point. There is always a quiver field theory, a linear quiver field theory. There is a rank function associated with it. There is a potential function on the gravity side that's solving a partial second-order differential equation. The gravity background is fully expressed in terms of this potential function. And you solve this Laplace problem and you have a holographic description of the quantum field theory. There are many tests for this, and typically all these dual backgrounds are generically of this form. So I would like, in the next 5 minutes, just to go closing, describe for you one prediction, one thing that would be quite hard to come by using field theoretical tools, but using holography is quite simple to find or to come by. That is some aspects of integrability of these linear quiver field theories. Okay? What I will mean by integrability in this case, I will think it in the following way. Let me drink some water. So I will be thinking about integrability in the following way. There are these field theories, there are these string backgrounds, and I'm going to throw string on the supergravity background, and I'm going to study the sigma model of that string. And I'm going to wonder, is the sigma model, at least for the classical string, an integrable two-dimensional field theory? If it is, if that sigma model is integrable, I will suggest via this conjecture that the dual field theory also has some integrability properties. Okay? The way to find if a sigma model is integrable or not is if the equations of motion of the sigma model can be written in terms of what's called a lax pair. In general, it's quite hard and is certainly not algorithmic to find such a lax pair. Much easier is to follow an idea by Pandosayas and Basu. The idea is the following. They consider a generic string soliton, a generic string solution, right? Moving on these supergravity backgrounds. For a generic one, the equations of motion, or the sigma model equations of motion will be partial differential equations. They will be quite hard to disentangle if they are integrable or not. But their suggestion is the following. Concentrate on a subsector, so particular string solitons, okay, moving on these supergravity backgrounds, and study this subsector. This subsector will be such that it will lead to ordinary differential equations. Analyze this subsector. If you find that this subsector is integrable, all you can tell is that this subsector is integrable, right? It's a bit tautological. But if you find that the subsector is not integrable, then you can tell that the full sigma model is not integrable. So the logic here will be the following. Given a field theory and the associated supergravity background, throw string there, study the sigma model in this sense, and decide if the sigma model is integrable, then you will be able to say that that subsector is integrable. If the sigma model is non-integral, then you will be able to say that the full string theory and the full dual field theory are non-integral. The summary of what I'm going to tell is that generically, for any field theory generic one, you will find non-integrability. But for each dimension, from 1 to 6, there seems to be a unique exception in each one of these dimensions, a particular string background and a particular quantum field theory, and I'm going to discuss some aspects of them. So do I have, for the chairman, do I have 5 minutes? 5 more minutes. Chairman, do I have 5 more minutes?
Luca?
You have 8 minutes.
Okay, perfect. We will finish on time. So the idea will be the following then. I will consider string, first consider in the case of 4-dimensional n equals 2 conformal theories, I'm going to consider a classical string moving on the holographic dual background to this particular field theories. Remember this function from F1 to F5. These are the fields that are relevant for this particular study. These functions, they are written all in terms of a potential. So you propose for this type of backgrounds a particular string soliton, right? The string soliton will move on ADS, will move on these 2 directions, will move on this direction, but importantly, it will wrap this direction and this direction, okay? And you carefully study the equations of motion of the string sigma model, the Polyakov action, and the Virasoro constraint. And you find a set of nonlinear uncoupled ordinary differential equations for these variables as function of the time tau, okay? So this is a problem that was studied by mathematicians in the 1980s. The main name that comes up there is the name of Kovačić, a mathematician who studies this type of problems. His Kovačić's algorithm, Kovačić criteria to determine the integrability of this particular system is the following. First, find a simple solution to these equations, okay? So that's a simple solution. I'm not showing the equation, so this is a bit meaningless. But then what's interesting is that Kovačić say, okay, based on that solution, make a small fluctuation. This is a small fluctuation. And study the equations of motion for this small fluctuation. These equations of motion turn out to be ordinary second-order linear equations with coefficients that depend on the background functions, okay? And the background functions at the same time depend on the potential. So Kovačić gives you a set of criteria to decide if this equation is integrable or not, which then translates into the integrability of the original system. So you follow this criteria of Kovačić, and what you find is that for any generic potential, like those I was writing in Fourier-Bessel series, there is no integrability. So generically, these linear quivers are not integrable field theories. But there is one and only one exception here, that is for one potential that's written there. Okay, so you look at this potential, you say, oh, it's a bit odd, doesn't respond to the previous description, but does solve the Laplace equation. You study the associated supergravity background. Here is the metric, and you see, okay, it has the structure that it should have, but interestingly, it has some singularities, right? When you study the Ricci scalar, the dilaton, you find that it's singular. You study the associated quantum field theory, and it's very odd. It's a field theory SUN, SU2n, 3n, 4n, and going forever and never ending. Okay? It happens that this potential is not new, was not found by the imposition of integrability, actually was found long ago by Kostas Festos and Dan Thompson when applying an operation called non-abelian T-duality on AdS5 cross S5. Okay, there is this particular example where the non-integrability is absent. For that example, one can show there is a lax pair. So the string theory on that particular background is integrable, and then this suggests this field theory is also going to be integrable. Running a similar analysis in 2 dimensions and in 6 dimensions, this was run by Kostas Filipas, student in Swansea, and in 6 dimensions we did it with Kostas and Jerome van Gorsel, another student in Swansea. We found, again, only one exception of one particular field theory for which there is no non-integrability, and for which you find there is integrability, both in 2 and in 6 dimensions. So let me just gather some intuition here of characteristics that these backgrounds have. So the first thing is that on these special backgrounds, one can write a lax pair. The bosonic string is classically integrable. In all these cases, you find, and this let's observe it here, that the word factor in front of the AdS bit is a number, is a 1. Okay, so is there a 1, is there a 1, and is there a 1? Somewhat, the dynamics of the string decouples the AdS from the internal space. It just happens in these 3 cases that the internal space is an integrable deformation of a known integrable space. And from the field theory perspective, it happens that the flavor structure of the associated conformal field theory is quite simple. Basically, there are no flavors, or there are a bunch of U1 flavor groups. This you can see in this case. There are no flavors here, no true flavor groups. Same here. And in this case, what you see is a bunch, a continuous of U1s. Okay, so these are all very strange field theories. They go a bit away from what we are familiar with. And in 2017, with Yolanda Lozano, we embarked in a program to cure these field theories from their problems. You can do so. I'm not discussing this here. But what happens is that when you cure the field theory, basically you do so by involving some non-abelian flavor group and spoiling integrability. So there is a very fine, very refined equilibrium between integrability and suitability of the field theory. Let me finish with some conclusions. There are features I discussed here for 4D and 5D theories. They do repeat in 2-dimensional conformal theories, 1-dimensional conformal mechanics, and 6-dimensional conformal theories. And things similar to this regarding integrability should occur in 3 and 5. This is not work yet. In those cases, there should be some special solutions with very special features regarding the flavor structure, and these solutions should be integral. These systems I've been discussed can be thought in terms of DP branes intersecting DP plus 2 branes and Neves-Schwarz branes, and the relations with integrability are new aspects of these special conformal theories. I didn't discuss it today, but we recently started the study of RG flows away from these conformal theories, and there is an interesting universality. Basically, some observables decouple their flow from their flavor structure. And just to finish, someone in the audience might be proficient on this. It might be quite useful to unify all these backgrounds under the same language and make a taxonomy of all of them. It would be quite interesting to study how integrability reacts to RG flows and in particular, starting from a conformal theory that is integrable, performing an energy flow, falling into another conformal field theory in the infrared, and telling about the fate of integrability at the end. With this, I finish. Thanks very much for your attention.
So we are perfectly in time, and we have 5 minutes for questions.
Let me see if I can see you.
Is there any question? Okay. Nikolaos Papagoropoulos.
Nikolaos.
Ask to... Please.
Nikolaos,
yes. Thank you very much, sir, for this nice discussion. I hope you can hear me, right?
I can hear you perfectly. Yeah.
Yes.
I have to apologize for my ignorance about all these things. So can I ask the following question? This is not a criticism. This is just a question.
Please.
When I start reading papers on similar matters to this, I see the metric similar to the metrics that you have written down. And as you know, one of the criticisms that has been over the years been thrown against string theory, and I'm not against it, is the fact that there is an abundance of possibilities. So coming from a slightly more formal background, the question is, are these metrics unique? Not how you build them, but how many of them do you have?
Very good, very good, very good.
Right, in the sense of, allow me to say, I don't expect you to give me something like the Schwarzschild, right, which says that if you have a spherically symmetric, static, and asymptotically flat, then uniquely modulo some mathematical things, you have this solution and nothing else.
Very good.
Right? I don't expect that. But at least you have an idea how many of these things you have, or the abundance, because if you have an infinity of those, then the predictability somewhat of the theory is, if not in question, at least.
Very good, very good. Let me address this point. Thank you very much, Nick, for this question, because something that I want to emphasize here is that the program, the ideology here, is not to find the compactification of string theory that gives a standard model. Not at all, right? This criticism that you mentioned, this abundance of possibilities, is related to what people call the landscape of string theory, etc. The program here is quite humble. The program is the following. Give me a conformal field theory or a field theory that has a UV conformal point in any of these possible dimensions, right? So say any of these ones. Let me go here. So I say these ones here, okay? So these are the possible dimensions where there are conformal and supersymmetric theories, okay? Yeah. So give me, you think, if you wish, one of these field theories, okay? Can I write a description in terms of a string background that will know all perturbative and non-perturbative aspects of the field theory? And hence, can I calculate semi-classically, namely basically doing a very simple calculation, right? Semi-classically on the string background to learn non-perturbative aspects of the field theory?
Excellent. Thank you very much. I'm completely covered.
Good. So you answered. You see, Nikolaos, that the program here is different, right, and there are as many metrics as there are field theories.
Right.
Okay. Right. Yeah. All right.
Yep. Thank you very much. Thank you.
No problem. No problem. Alfredo. You, Alfredo has one.
Can I go?
Go.
Yes. Go.
Okay. Okay. Let me. So, Carlos, thank you so much. You have this gift of make me think I have understood something in this complicated world.
I have the same gift with myself. So
no, you're always very clear what you say. So, but given the spirit of this meeting, I want to ask you a question that I always wanted to ask, and I keep asking to people, but never get a good answer. And perhaps you're the person that you can help me with this. So, the basic idea about ADS-CFT is to find a duality between gravity degrees of freedom and field degrees of freedom. Has anyone serious in that community thought about thinking that both are referring to some common structure, that there is an underlying common structure to both, that these are just two, because that's usually what happens. when you have two descriptions. You have two descriptions, there are different variables. You can, you have many examples out there, okay, of dualities of any kind. And these are just different variables for describing the same object. As anyone out there start thinking about this object, this common thing, which, you may think that these are the fundamental degrees of freedom, or you may say quantum gravity or whatever.
Very good, very good. Let me see if I can answer this by sharing the screen of the tablet. Let me see if this works. Is this working? Yeah. So what Alfredo is saying, okay, tell me, Alfredo, if I'm interpreting your question. What you're saying is that there are many dualities that can be thought in the following way. You have one partition function in terms of some fields. You have other partition. Okay, let me write it explicitly, actually. One partition function in terms of some fields. Another partition function in terms of some other fields. And some trick that one can play in many cases is to write an interpolating partition function containing both fields. Such that if you integrate one of them, you fall into set 1. If you integrate the other, you fall into set 2. And then you propose a duality here and there, right? So this is a typical trick that people play in dualities. Some dualities can be proven this way, but notice this implies that you can perform this path integration. So it's typically valid for quadratic actions, right? So if the thing is not quadratic, you cannot. In this sense, what you are describing as the underlying system would be this one, a system with both sort of degrees of freedom. Okay, in methods similar to this, one can prove some dualities, for example, what is called T-duality or non-abelian T-duality, or particle vortex duality can be proven this way in condensed matter, and they have applications. In this case, the difficulty here, with many other dualities in the market, is that the systems are interacting. So these path integrals cannot be performed, right? So what you have here is one system and another system. And for the moment, the thing is at the level of trying to make the mapping of what calculation do I do here to learn about something there, and vice versa. Okay. Now, if there is something like this structure, is completely unclear at the moment, right? But maybe you can, in order to appreciate what's going on.
Sorry, Carlos, it is unclear, but someone is working on it, or is not an issue?
No, look, a main, very important progress would be to prove this duality, right? This is a conjecture. So to prove it would imply either something along these lines or a complete mapping for all the infinite observables in this theory into quantities in there, right? So
which is not there, which is not given yet.
Not even, right? Not even. So I think people at the moment are developing, and this is 20 years old, right? So it's not super new, but people are developing this dictionary in one direction or the other, right? There are, I have to say, in particularly simple situations that involve not a string theory, not a typical field theory, but a topological quantum field theory and a topological string, there you can prove this, right? But these are particularly non-dynamical situations, okay? It's okay, but the ideology is there. So, yeah, at the level of proving the conjecture, I think we are as far away as
the beginning.
I don't know. There is a lot of the dictionary, right? And there is this element of integrability that enter into the game that is quite valuable because allows you an interpolation, continuous interpolation between one regime and the other.
Sorry, we are 5 minutes.
Thank you very much, Carlos.
So we have to interrupt.
Sorry.
Postpone everything.
Apologies. Thanks very much. Let me unshare this. Sorry.
Don't worry.
So see you later if at all.
Yeah, for the discussion session,
session.
everyone can continue.
Right.
So Vaclav, can you share your screen?
I'm working on it. So is it working as it should?
Yes, sure. So the next talk is from Vaclav Zatloukal from Czech Technical University in Prague. So go, please.
Okay, thank you, Luca. So, so my talk will be somewhat more on the quantum side of the conference title, and I will be concerned with the spinors and the Dirac equation, and why my arrows are not working now?
Is it okay? But well, because we
Okay,
see
now.
just the first slide. Okay, now it's going.
Okay,
Perfect.
Yeah. So yeah, so the motivation for this talk is, I mean, it's very simple. It's the presence of complex numbers basically in quantum theory, and of course we are taught the formalism of quantum theory, and it's full of complex scalars, and somehow it's taken for granted more or less that there are complex scalars, and well, of course this is supported by the agreement with experiments argument, but still this doesn't mean that perhaps we shouldn't try to think about the geometric meaning of these complex numbers, namely the imaginary unit, and trying to give some more intuitive geometric interpretation. So I will be presenting basically the program following the work of Estenesh and Doran and Lazenby to make use of a rich geometric structure of real Clifford algebras. So we will work with real scalars, but we'll use the structure of Clifford algebras to somehow replace the complex scalars in the quantum theory, and namely in the Dirac equation in this talk. So more broadly, I would say that regarding this workshop, since we are trying to unite or marry the quantum theory and classical general relativity, in order to marry them, perhaps it's a good idea to make sure that they speak a common language, then the chances, I guess, are higher for them to marry, and I will propose the language of real Clifford algebra or geometric algebra, as some people use. So there will be essentially two parts of the talk. In the first part, I will just recapitulate and reintroduce real Clifford algebras with a special emphasis on their geometric significance. So I will show how these can be used also in classical physics or in geometry to algebraically describe geometric objects and to manipulate them, rotate them. And I will propose a definition of what I will call real spinors. These will be elements of, I will say it already, this will be even elements of the real Clifford algebras, and we will see examples in 2D, 3D, and in the space-time. And in the second part, I will focus on the Dirac spinors and Dirac equation, and I will show how traditional matrix form of the Dirac equation can be translated to this Clifford algebra language, and how this can provoke perhaps new ideas regarding Dirac equation on a generic space-time background and introduction of gauge fields via essentially minimal coupling procedure in this setup. So, okay, so let me go to just reintroduce the Clifford algebra. So we have a, say, n-dimensional vector space, a real vector space with some quadratic form, and the real Clifford algebra is, so to say, freest associative algebra that is generated by this vector space, and that obeys the condition that the square of any vector is a scalar. It's a number given by the quadratic form. And in this way, we get a vector space again, but then algebra at the same time. It is 2n-dimensional, contains scalars, vectors, and products of, and higher products of vectors, so bivectors, and so on up to the pseudoscalar E1 times up to En. So the operation, the product in this Clifford algebra is so-called Clifford or geometric product. When we consider just two vectors, the product can be split into the symmetric part, which corresponds to the scalar product on the vector space, and to the anti-symmetric part. And this anti-symmetric part is a so-called bivector denoted with the wedge. It's the outer product, and it has a nice geometric interpretation. It's basically the plane that is spanned by two vectors, and it has an orientation from vector A to vector B, and it has a certain magnitude or size, which is the area of the parallelogram that is spanned by the two vectors A and B. And it's common in physics to represent the Clifford algebra basis vectors by matrices, namely the gamma matrices in space-time. But this is not always illuminating. In fact, I think more illuminating is the geometric representation. As I said, like you can form also higher dimensional so-called multivectors via this wedge product or geometric product, and if you wedge R vectors, you get basically an algebraic object that corresponds to an R-dimensional subspace or parallelogram with a certain volume. And I mean, this this view on geometric algebra, on Clifford algebra, was really advocated by David Hestenesh. One can read his books, and his aim is really to make real Clifford algebras the geometric, the language of theoretical physics. Yeah, like universal language that would encapsulate all, namely, especially classical and quantum physics. And so one can talk time about geometric algebra and also Clifford or geometric analysis. But there is just one point that we will need to acknowledge about the Clifford algebra is that if we take the even subspace, then it is closed under the multiplication, so it's a subalgebra, and so these are then this is a space of even multivectors. Multivectors are elements of the Clifford algebra in general, and it has half the dimension of the full geometric algebra. So let me go to concrete examples. We take a two-dimensional plane and two orthonormal basis vectors. The Clifford algebra is four-dimensional. It contains, apart from the two vectors, also scalars and the pseudoscalar E1, E2, which is essentially represents the plane. And even subalgebra has two linearly independent elements, the scalars and the pseudoscalar, and these are or represent the complex numbers, in fact, because E1, E2 when squared it gives -1, which is easy to see from the basic Clifford algebra equations. So, and the complex numbers, of course, are useful because we can implement rotations in plane efficiently with them, and this is of course also the case of these even multivectors, which represent the complex number. So if we take any vector v and multiply on the right by a complex number, we rotate the vector. Of course, one can just calculate it explicitly. What is interesting when one goes to higher dimension is that this action on the right, that since vectors commute with the pseudoscalar E1, E2, they anti-commute with the pseudoscalar E1, E2, then we can take half of this action on the right and put it on the left, and this will be a formula that generalizes also to higher dimensions. In fact, so, and a small comment, I mean, one usually describes complex numbers as points or maybe vectors in the Gauss plane, whereas here we are dealing with complex numbers as scalars plus bivectors. Of course, one can translate between these two points of view. One just needs to pre-multiply any vector by some reference vector E1. This E1 then basically gives the direction of the real axis. So this involves a certain choice of the real axis when we want to represent the complex numbers here by vectors. So now let's go to 3D. The Clifford algebra is 8-dimensional now, and it contains 3 vectors and 3 bivectors. Bivectors here have very nice, clear geometric meaning. They are the planes orthogonal to the corresponding vectors, and of course they're also orthogonal to one another. They have the algebraic properties of quaternions, of quaternion units ijk. By the way, so this Clifford algebra, it contains quaternions. So this is just one instance where one can really think of like once you learn the real Clifford algebras, you have the quaternions checked, and you can like kind of forget about the term perhaps. Now to rotate in the 3-dimensional space, one specifies a plane in which one rotates, and then so this corresponds to a certain bivector, and the bivector gives also the orientation to the plane, and it has a certain magnitude, which is the angle of the rotation. So the bivector characterizes completely the rotation, but now the action is two-sided. So one takes a vector and takes this adjoint action by the so-called rotor u, which is an exponential of the bivector. And these rotors form a spin group, which is double cover of SO3, and due to this double-sidedness of the action, we can naturally extend the rotation to any multivectors. So essentially, any multivector is rotated in geometrically intuitive way, because like each vector that constitutes this multivector is rotated in the same way due to this observation. So now comes the point of introducing the spinors, and the spinors here for us, what I will call real spinors, will be the even elements of the Clifford algebra. So we are in three-dimensional space at the moment, but this will generalize to also other dimensions. So it's so this even subalgebra is a linear space, and in fact it's the smallest linear space that contains all rotors. So rotors themselves are even multivectors, scalar plus bivector, but they don't form a linear space. But if we take a span of all rotors, we get the real spinors. And since it's a subalgebra, the even subspace, we can think about the action of rotors on the spinors, and this will stay within the space of spinors. So yeah, this would be a spinor representation when we act just one-sidedly on some spinor psi. But notice that it also makes sense to act double-sidedly on the spinor psi, because this double-sided prescription works for any multivector, including the spinors. So now what is the relation between these real spinors and the Pauli spinors that one is used to in three-dimensional space? Well, so again, the real spinors, they are scalars plus three independent bivectors, essentially. So they have four components. As a side remark, they can also be written as a scalar multiple of a certain rotor. So these real spinors have a nice geometric interpretation as basically an instruction to rotate and stretch vectors or multivectors. Yeah, so one can think of them as really the elements that can also act on other elements. And with these four real components, we can define two complex numbers, and these will constitute the Pauli spinors. So we'll denote this by ket psi, and so this will be the traditional spinors with the ket. Okay, and we define the two components by this prescription, where the angle brackets, they denote the scalar part. So the scalar part is essentially in the Clifford algebra. If we are to represent the Clifford algebra with matrices, this would be the trace of the matrix. So it's so the multivectors commute under the scalar part, for instance. And now we have a way to translate between those real spinors and the complex spinors. And also we have a way to translate between operations on these spaces, on these spinors. So we have, on one hand, we have algebraic operations on the real spinors. So these are operations in the Clifford algebra, like we multiply by a certain bivector, for instance. And on the other hand, we have matrix operations on this C2 space. And so how it works now, if we multiply by those basis bivectors, B1, B2, B3, on the left of psi, we recover Pauli matrices times the imaginary I. I mean, the reason that we recover this is just because we deliberately chose in equation 3 the assignments for Z0 and Z1, of course. And so now, most notably, we can also act by bivectors on the right of the spinors, on the real spinors. And when we act with the B3, again, due to the definition number 3, we basically get just multiplication by an imaginary unit on the side of complex Pauli spinors. So at this point, basically, this imaginary unit is reinterpreted or interpreted geometrically as a bivector B3, which acts on the right of a real spinor. And since we are acting with B3, why not act with other bivectors on the right? And we get these expressions in the matrix formalism, which involve the component-wise complex conjugation. So this star is a complex conjugation. So these operations on the level of matrices, they look a bit awkward because they involve complex conjugation. Yet with real spinors, they are completely natural. Okay. So now let's go to the space-time. And okay, so we have 4 space-time directions, an orthogonal or orthonormal basis of space-time. We call this gamma 0, 1, 2, 3.
You have 10 minutes.
Okay, perfect. So the Clifford algebra is 16-dimensional. Lorentz transformations, they can again be written as a double-sided action of certain rotors U, where rotors are now even multivectors satisfying some condition, and but one can again think of them as to assign as exponentials of bivectors. There are 6 bivectors, 3 of them for rotation and 3 of them for boosts. And okay, the tilde is the reversion operation, which in any Clifford product, it reverses the order of vectors in the product. And again, for real spinors, we will take the even subalgebra. So even multivectors will be the real spinors. And there is exactly 8 parameters which characterize, or 8 components of these real spinors, because it's half of the dimension of the full geometric algebra. And yeah, in fact, one could do this in any spaces, like to define spinors in this way, so that always they would be the smallest linear subspace that contains all rotors, and this would give representations which are reducible, but they are somehow geometrically appealing, at least to me. So now, okay, so now what is the correspondence with what we know traditionally? We have 8 real components for the real spinors, and they can be distributed into 4 complex numbers. And so let's do it, and this will define, and this will be the Dirac spinors, the elements of C4, and the complex numbers we will define by equation 6. Again, algebraic operations in Clifford algebra translate to matrix operations on the space C4. So in particular, for instance, it's gamma mu and gamma 0. When they act left and right, they give the gamma mu hat. So the gamma mu with the hat here is these are the Dirac matrices in the standard representation. So these are really tables of numbers. Those gammas with hat and the gammas without the hat, these are like vectors of the orthonormal basis. And we get these relations because we deliberately chose the assignments of Z1, 0, Z0 up to Z3 in equation 6. And okay, we can go further. And to get the I, we just multiply by gamma 2, gamma 1 by the bivector gamma 2, gamma 1 on the right of the real spinor. So again, this is gamma 2, gamma 1 is essentially, again, the representing the plane yeah, in space. Now, okay, so this is the usual matrix form of the Dirac equation, and one can consider localization of Lorentz transformations for this equation. This would lead to spin connection. Okay, so I'm just recalling this, and also one can consider localization of phase rotations of this wave function psi, and this would lead to the introduction of electromagnetic potential. Now, if we use our dictionary to rewrite this Dirac equation with real spinors, we get the equation 9, which was put forward by Hestenes a couple of decades ago. And again, we can think of spin connection being derived from action on the left by the rotors U. Now, to get the electromagnetic potential, we act by the phase, but now the phase is so e to I phi. I is represented by the bivector gamma 2 gamma 1, and so okay, if we use this particular rotor and gauge its action, we get the electromagnetic potential. But immediately one can think of like more general rotors acting on the right, or bivectors being placed in the exponential. And okay, this was considered by Hestenes and Doran Lazenby, and they try to make some connections with the electroweak theory. But let me just present in the last 5 minutes perhaps my take on, or my proposal, how one can think of what one can do now with the real Dirac equation. And let me jump straight to a curved space-time where we have some manifold with the metric, and this metric can be decomposed to a tetrad field, and we have a tangent space at each point of the manifold, and let's define a reference flat Minkowski space, and above this space we construct the Clifford algebra, and then we have, let's have isometries from the tangent space at each point to this flat reference space. So this goes like this. So the gamma A is an orthonormal basis in the flat reference space. Of course, since we are on the manifold, we can make this mapping from the tangent to the reference space in many ways, and in particular at different points of the space-time. I mean, we have different choices, and so there is some freedom in choosing basically where the tangent vectors are mapped exactly. And so this freedom, I would say, for me would be local Lorentz gauge transformation. So this local Lorentz transformation would rotate the gamma A's. And let me just try to and it will rotate the vectors in the Clifford algebra, and let me postulate that it will also rotate any other multivectors the same way, including the spinors, the real spinors. And on top of that, let's consider that under Coherent transformations, all the multivectors in that multivector valued fields that they transform as scalars, because they don't have any space-time indices. So when reduced to a flat space-time, this construction, it's a bit unusual, because one gets one gets for global Lorentz transformations in the flat space-time, that essentially that the spinor transforms, that even the complex Dirac spinor, that it transforms as a scalar, but this possibility was coined also, for instance, in one of the lectures by Feynman on quantum electrodynamics. The point essentially is that if you postulate this, I mean that for spinors you have the usual spinorial transformation with the matrix U and under Lorentz transformations, but if you accompany this transformation by a change of representation, which is complementary to that, or inverse, which basically then in total give you like untransformed or scalary transformed spinor, you are effectively changing the gamma matrices, the representation. This is what also happens here, because the gamma mu prime contain the tetrad, which changes under Lorentz transformations in the Minkowski space. Now let's try to write a covariant equation, real Dirac equation here. So we introduce a covariant derivative, and since we are acting on both sides,
5 minutes including questions.
Okay, yeah. Since we are acting on both sides of psi, we needed to we introduce two fields, so omega mu will be on the left and a mu on the right of psi, and these are bi-vector valued one forms, so they have 6 components essentially, a vector, form, one form components, and yeah, indeed they could be also identified, just writing omega mu equals a mu, but then we wouldn't get the nice, yeah, it could be done in principle, but let's keep them separate because we would like to see what they reproduce the spin connection when acting on the left, but on the right we have 6 fields, and one of them will be just the usual electromagnetic field, which corresponds to the rotations in the gamma 1, gamma 2 plane. But then we have 5 other bivectors, and we need to see here. We have the action of the bivectors as rewritten in terms of the complex Dirac spinors. So again, it contains some complex conjugations and some operations. So in summary, I would, maybe I don't have to talk too much about summary since I'm running out of time anyway. So I would just stress the point too, that we kind of interpreted the imaginary as a spatial bivector, but a spatial bivector on a generic manifold. Who chooses? We have to somehow choose the spatial bivector at each point. So in principle, this imaginary might depend on the space-time point x, and this idea somehow led to the introduction of this non-abelian connection, which extends the electromagnetic potential. Of course, whether this has any significance in physics is a separate question, but I would like to just message I would like to say is that perhaps even by just reconsidering the formalism or rethinking the formalism, one can get new ideas, perhaps which are very straightforward in the new formalism, whereas in the old formalism, these operations would look kind of awkward, I think. So this is all. Thank you for your attention.
Okay, thank you, Vaclav. So one very fast question from Tom.
So you hear me, I assume. Good afternoon to everyone. The question is very simple. I mean, on the slide 9, you mentioned something like 4 i's, right? 4 complex numbers. How is it with quaternions? I mean, is there any relation with a quaternion group or not? I mean, between this formalism which you were showing now and quaternions.
So the quaternions geometrically, like they would be in the 3-dimensional space, these bivectors, the quaternionic units, and the space of spinors is basically a space of quaternions. So the quaternions can represent the Pauli spinors as well.
Right. So is there any, I mean, closer relation? But I will stop now. I will wait for discussion session. I mean, there was a, you talk longer. So I will stop now and I will wait for discussion session.
Okay.
Perfect. So in fact, we can postpone everything to discussion session. And thank you once more, Vaclav. Leslaw, are you here? Can you?
Yes, hello, I'm here.
Okay, you can share your screen.
Yeah, I will start it. Can you see it?
Yes, perfectly. So next speaker is Leslaw Rachwal from University of Luis de Fora. And Leslaw, please start.
Okay, thank you very much. So, yeah, I think, okay, you have seen me on my video, but when full connection, I will not turn it on. So first, I want to thank the organizers, especially Luca, for inviting me to this nice conference. I think we have already learned a lot, and I'm keeping my hope for the other days and what we'll also learn till the end of this week. So it's a very nice workshop, and once again, I'm very grateful for your invitation. So today I will talk about quantum Weyl gravity at the level of first loop. So first, let me show you my co-authors, and this is Petr Jizba from Czech Technical University in Prague, and also Stefano Giaccari from Holon Institute in Israel. And we performed some of this research in this project under the grant, which had to do with quantum symmetry, and this was both in gravity and also in particle physics. And here you can also see the references that there is some work already put in the papers, but there are also more to come, so please stay tuned. So let me first show you some slides as a motivation. It's a very rough motivation, and you can see it from cosmology. It's actually from Planck data that, of course, for those who are experts in this is very specialized plot, but just think like a physicist that we want to describe our words using some more and more detailed versions. So zero leading order assumption is to say that the word is very simple. And what does it mean? Looking particularly at this plot, that of course you see this orange little blob, which is in the center of the confidence level for the measurement. You could say it's not very far from the point which is 1. And actually, if you look really what is on the horizontal line, this is the spectral index of the scalar perturbation in the CMB. So that's what we see in the sky. So let's take the assumption, and it is very, as I told you, in a physics perspective, it's a good assumption that is not so far from 1. So the zero order approximation, you can say 1, and then there's also some deviation, which I here quantify by epsilon. And epsilon, you want to say it's a small number, and that's how we want to describe the physics. At first, this is zero order, and then there are higher order one. So now you are completely legitimate to ask the question, what happens in the point when this thing is equal to 1? So where we are in this corner of the square, what happens there? And this is a very particular feature, because then it is scale invariant spec of the scalar perturbation. So this is a first sign that maybe there is something to do with scale invariance, and of course you can promote it. And the good promotion in the, let's say, geometry language is the language of conformal symmetry and conformal transformations. So they preserve only angles. The distances are not anymore absolute notions. They are relative, or you can say also they depend on the conformal gauge. So the differential structure of the space is not anymore invariant, is not anymore absolute. This has to is changing when you perform a conformal transformation, but there are some things which are less, I mean, which are more restricted, some conformal invariants, and for example, the causal structure or the light cone structure, or you could also say conformal structure of the space-time, this remains. So this is something that you can see even on this cartoon at the bottom of the slide, that from the rectangular grid you get in 2 dimensions. From rectangular grid you can get into some other, which you have some curvilinear system of coordinates, but still the conformal structure for such transformation is preserved. So this is, you know, from the differential geometry. Now you can ask, where do we meet this in physics? So first, the very intuitive assumption and a kind of intuition is that if you take the system of particles, like in particle physics, and you go to very high energy, then you see that all the particles are effectively massless, and when they are massless, the symmetry most of the time, I don't say all, but most of the time is enhanced, and then we end up with some conformal symmetry, which governs the dynamics systems at very high energy. So this is what you can intuitively see in a framework of particle physics, but also this symmetry can be used as additional symmetry in a gravitational theory. So not only invariance, the coordinate reparametrization, we also want to have invariance under this possible conformal transformation, only keeps the causal structure unchanged. And like for any other symmetries, this symmetry can be presented in a local way, so in a gauged way, when we allow for the parameters of transformation to be space-time dependent. So we perform this gauging transformation. So these are the properties that you have on a classical level. I mean, even I have not yet specified for you, it was just, let's say, kinematical. Now I can, in connection with what Carlos was saying 1 hour ago, I can also tell you what is the corresponding picture on a quantum level when we have quantum conformality. And the first prerequisite is that you have to have scale invariance, and later you can promote, but just from scale invariance you see that this is a very particular situation, because quantum fluctuations look the same no matter what is the energy scale. So both in the infrared, both in the U, so at intermediate energy they behave the same way. So this is a very special situation, almost, you could say, almost never happens, but it does happen. And this means there is a very enhanced and very peculiar dynamics on the quantum level. So it is very constrained. You could say that the system is not arbitrary. It has very limited freedom. And this you could see also that there is no problem with UV divergences, because when you require symmetry on a quantum, you shouldn't have divergences, you shouldn't have beta functions, your field should stay at the fixed point of renormalization group. And as Carlos said 1 hour ago, these are conformal field theories, very special quantum field theories. So another point of view is that also the effective action in this theories is very highly constrained. You can say even mathematically that is idempotent. So this simplifies the story a lot, but of course this is of the symmetries present in the model. So now again you can ask what are the examples, and of course a long list was given but not complete by Carlos, but also let me say that quite well studied was n=4 super Young. So again we have to have a lot of supersymmetry, or in a first gravitational framework it was n=4. So nomen the same number of supercharges, conformal supergravity due to Fradkin and Zeitlin. You can ask, why do I want this symmetry on a quantum level? and this may be instrumental in solving the space-time singularities. There will also be talks today later about this point, and this is a good starting point for some non-conformal nations. So I showed you the first slide where there was this Planck data. We know that we have that the world is not conformal, so we have to perform a non-conformal deformation of the good starting point. So what is the good starting point? First, on the level of class action. So this is unique and very constraining already there, because if you are in four-dimensional and you require action to be diffeomorphism invariant and conformal invariant, this is the unique functional you can come up with. And this is, of course, this is constructed with the Weil tensor, and there is one unique dimensionless coupling constant. So it's a very, very minimal and very, very economic theory with just one constant that for the boundedness of the action you require to be positive. So this is the setup for the theory, and even on a classical level there are a lot of feature, because you can study the exact solutions, and for example they explains for you the kind of in a different way the dark matter problem, and this was in the work by Mannheim and O'Brien. But also there are other solutions which you can you know that they are Mannheim-Casanas solutions, and besides that all the solutions that we have in vacuum in conformal gravity, they coin with Einsteinian solutions. So you may wonder, you may be worried whether this theory passes the tests that Einsteinian gravity passes, and it does. Why? Because in vacuum the Weil gravity is basically broader, but it encompasses all the solutions that we know from classical GR. So there is no any problem, for example, with the redshift, with the precession of Mercury, and so on and so on. These things are exactly reproduced, the same like in Einstein gravity. So the amazing feature of this course. And moreover, because we have this freedom of playing the conformal factor, we can reabsorb the singularities of standard general relativity. So for example, Big Bang singularity can be encoded in this conformal scale factor omega, and then now the metric will not be singular. I mean, if you consider the invariants, they will not show you any singularity. So basically, you make singularity gauge dependent object. So this was so far so good for the classical level. Now, if you want to quantize the theory, you may think first we have the models of quantum matter, and already has a very speciality in 4 dimensions, because if you take the classical actions of electromagnetism or Yang-Mills theory, or even the one that Vaclav used, although half an hour ago, although he didn't really show the action, these systems, if they are massless particles, so without symmetry breaking, they are conformally invariant in 4 dimensions. This is already a feature that you see, and if you are careful enough, you should not spoil this fact that there is something special happening on a classical level. And now you want to couple it to gravity. So imagine that you don't want to break the symmetry, the same like the matter systems. You don't want to break the homomorphism because it was already there. The same you should do with conformal symmetry. It happens to be equal for this symmetries there, and the only way how to preserve the conformity on a quantum level is to couple it via the c-squared action, because when all the divergences are generated in the matter sector, there will be completely absorbed in just this one counter term, which is the c-squared action that I showed you. So this is also another route to conformal gravity, followed by, for example, by 't Hooft, that you can think that we have the standard particle physics when we have massless and also electromagnetic field and Yang-Mills field, and on the level of pathing you can, on a curved background, so on a non-trivial manifold, you can integrate out all these fields, and what you end up necessarily is the c-squared action. That's what you get as the kind of WKB approximations. When you integrate all the matter fields, the gravity must behave according to this action. So this is the story at quantum level. Now let me say we want to buy this framework, we want to analyze the theory of gravitational and conformal interaction. So we have both diffeomorphism and also the conformal symmetry. We want to treat that, so there is a very special procedure how to quantize it. So we have to add, of course, the Faddeev-Popov ghosts. So these are good, useful ghosts, and we have to add them both for the conformal group and also for diffeomorphism. So I will not go into these details. I'll just want to show you what the features are, because now it is a renormalizable quantum theory of gravitation. It's asymptotically free in the UV regime, so it is very similar to the QCD. And there exist even the very special versions of supersymmetries when the theory is completely without divergences. So you have quantum conformality fully present on a full level of the theory. And this framework, when we don't have problem with divergences, they are under control or they are completely not, is a very nice to perform the computations. And let me say that even in the Euclidean framework, when you consider the C-square action, is very nice because it's bounded from below and there is no inequality related to the conformal factor. So it means that the partition function, if you want to compute, of course, it's not with problems typically related to negative definiteness. Here is completely well bounded, so it doesn't have this problem, and the theory be viewed as a statistical in Euclidean framework as a statistical mechanics of four-dimensional manifold, so something which goes under the name of quantum shape dynamics. So in Weil gravity we have this diffeomorphism symmetry which is fully realized. We also have the conformal symmetry, but this is a very peculiar system, and for example you cannot obtain it by some limiting procedure, because even if you want to take the coefficient in front of r squared, send it to 0, then there is a kind of discontinuity which is similar to the Zakharov discontinuities known for the massive theory. But here, even in the dimensionless couplings, you see that this is very special case. You cannot obtain it in other way. And this also means that the spectrum is very special because they are only transverse and traceless gravitons. The other things, they decouple. I will show you in a minute. So in this framework, when we have gravitational interactions, I will want to show you some results of basically 4 computations that we have done. And I will use the methods of the background fields, and as far as it will be possible, I will use the only physical degrees of freedom, so only this traceless and transverse gravitons. So let's go. So first, I will want to show you the partition function. So for this, a technical development is the Young position of the metric functions. Of course, here the metric is the main and the single degrees of freedom are using in quantum field theory, and you extract the trace, and all the other things they are transverse, so the distance is 0, and they are without trace. So actually, on the level of second variation, this is the only thing which survives, because all the other they are killed by the diffeomorphism. The transverse part is killed by the diffeomorphism, and traceless part is killed by the formal symmetry. So let me just show you what are formal invariant. So we have in 4 dimensions there is the C-squared, which is completely conformal invariant. Then there is another which is invariant because it's a topological, so it's up to boundary term is 0. And then the other one is R squared, which is invariant under this transformation, which are dubbed as a restricted conformal transformation, so they have to satisfy the D'Alembert equation. This invariance will be important as what follows, because I will choose very specific background manifold, and this will be a merger of the both maximally symmetric and Ricci-flat spacetimes. So this is basically the class of Einstein, and these are the curvature relations which are satisfied there. So basically, the Ricci tensor is proportional to the metric, but besides that, with some proportionality lambda, capital lambda, but besides that, we also have the non-vanishing Weil tensor, and this is that in terms of other invariant. And it's important to notice that they are all Bach flat, so they are the classical ones of the Weyl gravity. So now let me go into this derivation of the partition function. So first, the level of the second variation of the action, as I told you, is only in terms of transverse and traceless field, and inside there are two brackets with the operator, and then there is also the matrix of the Weyl tensor. But this expression is not yet complete, because you have to take into a Jacobian of the change of the variable, and then this produces the things that you see in the numerator, and it's still not a complete expression. That's why there is Z tilde, so it's not yet the full answer for the partition function. Complete, you have to correct by the contribution of zero modes, and they are active only on maximally symmetric spacetimes, and they change basically the subspaces in which you have to take the determinants, and this is the result now. It is fully okay, and you can also perform the extension of some operators such that completely unconstrained. So for example, 2t for me means spin 2 but traceless, but if it is just determinant in subspace 2, then it's a spin 2 completely unconstrained. So this is the partition function, and now I want to show you in the remaining 10 minutes what we can do with that. So we can study the flow equations, but now we will see going into both directions of ultraviolet and also of the infrared. So first, this is a non-perturbative flow equation due to Wetterick, and then if we a priori, before getting to the partition function, it will be very nice to fit this equation with the factors that we had in a partition function. So in the one loop
now you
partition
have 10
function.
minutes.
So first, okay, thank you, Luca. So first, for the left-hand side of this flow equation, we choose the following ansatz, and this is based on a curvature invariance that we discussed before, and there is one feature that it's, you can say, miraculous, but square term is not generated at one loop. So this means that there is a hierarchy of beta functions. So that's why to first approximation, I can write the ansatz for the left-hand side completely without it. And now what happens to the right-hand side, we would say this just comes from the partition function of the C-squared theory. So there is only, everything is sourced just by the C-squared term. So if you use this equation now in one, because we are on Einstein space, general Einstein space, we can extract the information about the C curvature and also about the lambda squared terms. So let's do this. This is the form of the equation, and for this I use the partition function in, with 4 elements. There was also this extended form, but they are equivalent, and it's important to evaluate the beta functional on this general Einstein spaces. So basically on the left-hand side you have this C squared and GB, so Gauss-Bonnet terms, but if you explicitly write what are the curvature invariants, then you see that basically you will be able two combinations. One, there will be beta C plus beta GB. This will multiply the C squared term, and the other there will be 8/3 the beta functions of the Gauss-Bonnet term. So this will be the two things that we will be able to read, and then we'll be able to disentangle the system. So we have the following formula relating the two traces. So that's why this this form of the flow equation is to the other one that I showed you with the longer form of the partition function. Let's use this equation and all the ingredients I showed you, and then you can, for example, find the expression for the bits of the Gauss-Bonnet, and it takes this form when we include the threshold phenomena. These are these brackets with 1 plus lambda over k squared to some power to the inverse. But then we also can include the anomalous dimension, and this is that eta, which is the prefactor of the expression. So when you take the limit now k going to infinity and you set eta to 0, what you get is exactly you reproduce the values which were already reproduced at one loop and the Fradkin and Saitin many years ago. So in the case of Gauss-Bonnet, we get minus 87/20. Numbers fit, of course, perfectly. In the case that you look at the terms which are proportional to C squared, you get this combination, namely the sum of beta C plus beta Gauss-Bonnet. And if you this entangle is a very simple algebraic system. You get the beta of the Weil term, which is again the number which completely agrees with previous work. So these were the beta functions obtained Atkin and Zeitlin in one loop approximations, for example, in dimensional regularization. But we improved them in a sense of RG because we included the threshold phenomena. Also, we include the anomalous dimension. So if you want, but this is kind of for free, it doesn't change so much about the flow. So in the UV, when we look for the fixed point, so the points that beta function is 0, then we found the Gaussian fixed points. But interesting is the situation, what happens in the when you go towards the lower energies. And this is what that basically the blue and red lines, these are these Fradkin-Zeitlin beta functions, which are a bit boring because they are constant. But the ones that we computed, these are this orange and green. And when you see that they are opposite sign, but there is a moment when they cross the 0 line. So a moment when they are 0, the functions are 0, it means that there is a fixed point. And this happens almost at the same location of energy. If you go back, if I go back one slide, when you see that the numbers that we get for the location of the fixed point, they are with % accuracy. So you can say that higher loops, maybe they will increase the accuracy, but we are already quite impressed that at one loop level we have this 2% agreement between the values that you find for the location of the fixed. So now you can ask what is the station of that, and we found one using the holographic figure, because since this point it happens at finite energy, is not a true fixed point, it's rather a turning point of the RG flow, and this corresponds to multi-branch holographic RG flow, and there is the discontinuity, or you can say non-analyticity in the coupling, and this of course is related to the fact that this is at a finite energy scale, so it doesn't happen at k equals 0, it happens at some values that I showed you before. But if you want, we can go with the true IR, and then these are the characteristic of the true infrared fixed point, which will be IR stable in this space of the two parameters, two operators, Gauss-Bonnet and C-squared coupling. So there is this interpretations like very similar to what Carlos was saying about the holography, that here we can, to describe this point, we can put some brain construction in the 5-dimensional, when because basically on this brain you have the joining, the bifurcation point of the two branch solution for the profile of the scalar field. So but this requires typically some exotic matter to put on this brain. So it has of course some implications for some relations to the cosmological situations, but this is in 5D, because we have to keep this in mind. So let me maybe in the remaining 3 or 4 minutes tell you about one final point, which is the counting of the running degrees of freedom, because this is also something which is interesting. So you have this formula for the number of degrees of freedom, and on flat spacetime you cannot do much with that because you have no scale of curvature. You have just, for dimensional reasons, you have a renormalization scale mu that you have to plug that. But in the case that you are on a density or on a spherical bag, you have one additional element, which is the scale of the curvature, and you can play with dimensions, and you can construct small lambda, which is now a dimensionless parameter, and we will use it to study basically the running of the effective number of degrees of freedom. So what we know already from this flat spacetime expression, that in quantum Weyl gravity on a classical level, there are 6 degrees of freedom, and this is the list, that they are 2 spin massless and 1 spin massless. So altogether this to 6. This expression that I showed you, that the ratio partition functions you could see, it's expression which is very nicely constructed because it's finite at any edge. So this is not any problem with divergences. It is completely finite. And when you see that, for example, this one, which is valid on a sphere, when you take the limit of large energies, so when the mu squared is much bigger than the curvature scales, then this expression is designed in a way that it exactly reproduces the fixed. So exactly you get 6 degrees of freedom. That's what you did from the classical from the flat space-time consideration. So now we want to compute this on a, and for this we need a non-perturbative evaluation of the determinants which are in the partition functions. So this you can do using the method of the heat kernel, and this is basically this expression with the integral and S parameter. And you write everything correctly when they are this B coefficients of the operator, but we need some of them. So that's why I put in the last line of the slide, I put the dots pointing that that you have to resum all this, which is numerically possible to be done. So these are the determinants of the operators, the logarithm of determinants operators, which also take into account finite contributions. So that's why I said that we want to take it non-perturbative summations. And then I do the results again, another plot. So line is the boring line when we have fixed number of degrees of freedom, but then depending on this parameter that you use for polarizations, you see two curves, green and blue, and they correspond to decreasing number of degrees of freedom. And then in the UV it starts from 6, but you see that smoothly and monotonically it goes toward 0 when you lower the energies, because this lambda still is basically proportional to the energy you use to probe your system. So you see that we have some analog of the A function, and here in quantum Weyl gravity, and here it's monotone. It is smooth. So it could be a good candidate. So yeah, I think maybe it's almost time to finish. So let me just show you the conclusions that, yeah, we have found one new partition. We have also found something interesting thing about the infrared fixed points, which now both we have the turning point at some finite scale k, but at some deep IRs we have also true IR fixed point, which are with this special values of the couplings omega Gauss-Bonnet and omega Weyl. And I also showed you in the last few minutes this proposal for the A function, the analog of the A function in Weyl gravity, which is a good, because it satisfies the assumption that it is decreasing monotonically, and it reproduces exactly what we know in the UV limit. And this can be used to about the character of the phase transition, how to go from conformal to non-conformal world, because of course I know that the world is non-conformal, so we have to come down from the UV, and then we have to go to some place where we see the gravity, even to in the non-conformal regime. Basically, I started with cosmology, so let me also finish with that. You see the UV fixed point that we have found here, it could be like the moment of the Big Bang, so the time when first conformal symmetry breaking. But the infrared fixed points that we found is another moment very important in the evolution of the universe, because it's like you could say onset of inflation, the moment when this very important era for the evolution of the universe starts. And scale lambda could be the scale related to the radius of the de Sitter, which is important for of course, for the cosmological inflations. So these are the references. So they are some old and also some recent paper that I wrote in collaborations with Petr and with his students, also Stefano. So this is, I think, the good moment to thank you for your attention, and I'm grateful for your comments and for your questions. Thank you.
Okay, thank you, Leslaw. I think we have time for one question.
I have a question. So you said that depending on the energy with which you're observing, you're obtaining a different number of degrees of freedom, starting in the beginning with the 6 degrees of freedom of conformal gravity, and later they change. So my question is, you observed at the end that you reach Einstein gravity?
or from the number of degrees of freedom.
Yes.
No, I don't see this, because of course in Einstein gravity we are two propagating degrees of freedom, because they are the two polarizations of the massless graviton. So if I go to this, okay, I think I can to this plot, then you see that for me these curves go to zero. So it is completely new dynamics. If I, for example, they flatten out of 2, which is the number of degrees of freedom in Einstein gravity, yes, then I could claim this, that look, this is a mechanism how conformal gravity comes down to Einstein gravity. But I don't see that button and they reach the IR limit 2. They, at least for me, they go to 0. So it means that when I go toward phase transition, I find that this theory will be completely different. It may not be even a gravitational theory at the end. So unfortunately,
what would it be at the end? Do you have any predictions?
Oh, it's typically, I don't have a prediction, but it's typically difficult if you are reaching the fixed, say what's on the other side of the fixed point. Because, for example, in statistical mechanics, we have some intuition when we go, for example, from critical phenomena to another side. We can say that we would start to see atoms or molecules. I don't know if I can be so bold to predict for the structure of this here, that I start with continuous conformal gravity, I reach some fixed point, and what's on the other side of this fixed point, maybe there is some atomic structure of space-time, I don't know. But something that typically RG cannot tell you, RG flow, because you try to go beyond infinity, because the fixed point happens at infinite kind of fictitious logarithmic time. But if you want to know what's on the other side, you have to go beyond. And okay, in statistical mechanics and the critical have some ideas, but here it's difficult, and I don't know.
Okay.
Okay, so Leslaw, you can share your screen, and I think we can directly start the discussion session. And I will give priority to Nick Mavromatos, who had a question to Carlos Nunez before. And so, let's Nick.
Hi. First of all, I would like to thank all the speakers for this very nice presentation. I have a question to Carlos. What happened? Two questions actually, which are related. What happens if you have a breaking of the number of supersymmetries? I mean, what happens to the ADS-CFT if you have a breaking of the number of the supersymmetries? And also, which is related, what happens with finite temperature effects? So is the duality valid under these conditions? Do you need a sufficiently large number of supersymmetries, as in the original Maldacena conjecture, which was softened a bit by Witten later on, who also talked about breaking of duality on finite temperature? So that's my question. What's happening in your systems at finite temperature, or if you have broken supersymmetries? Carlos, I think you are muted, or you have not been given permission to speak.
No, I think yes, but okay.
He's muted.
There we are.
Now you are allowed to speak.
Exactly. It was written, the host doesn't allow you.
It did.
Okay. Very good.
Okay, maybe you log out
okay.
for
all right. So Nick, both are perfectly reasonable questions. If you allow me to share my screen, I'll explain with a little drawing.
You can do. I give you now more permission.
All right. Okay. So can we all see this? Yeah.
Yes.
Good. So what Nick Mavromatos is asking is, okay, very good. In some anti-de Sitter and some conformal theory, right? So say that this is in D+1 dimensions, this is in D dimensions. What happens if I want to break some of the symmetries this system has? Characteristically,
I cannot listen, Carlos. He has problem.
Disconnected for a moment. I'm back. So disappear. I'm back. Yep. I'm back for all.
Yes.
Sorry. Sorry. This, I don't know what happened. So indeed, you can do this by deforming. So this metric that was an ADS, okay, is no longer going to be an ADS because you are going to switch on some other fields in the string configuration that will break this, right? So say ADS is like this. Let me write a particular metric for ADS5. That's 4-dimensional Minkowski. So if I have something like this, that's ADS. But suppose that I do something like this. Yep. And I found now a new solution where this function is only R, or this function is only R asymptotically for large values of R. And then in the interior of the space deforms into something else, okay? So in this case, this would correspond on this conformal field theory side to the addition of some operator, say, for example, in the action, or the presence of a web for some operator that will break the conformality, okay? In breaking the conformality, you may also break, very likely, part of the supersymmetry, okay? So you will be flowing from some superconformal field theory into some usual quantum field theory, okay? And just to go for the second of Nick's question, what if I would like, for example, to break conformality by the addition of temperature here? Yeah, so you fall into some quantum field theory at finite temperature, okay? So the way to do this on the ADS side is by introducing, for example, a black hole in the ADS solution, right? So usually say that ADS looks like this. Sorry. Yep. And so now you introduce some non-extremality factor here and there. And if it happens that the non-extremality factor allows for a horizon, then you are putting a black hole. The temperature of the black hole will be associated with the temperature at which you are putting your particular field theory, right? So this game was playing many different examples, among examples like, for example, flowing from n=4 super Young-Mills into some more phenomenologically interesting theory, something like Young-Mills, right? Or Young-Mills plus some matter, etc. Okay, so this is a well-developed line of research, and many people have contributed to it. So this is possible, and what's very nicely refined is the mapping between what am I doing to this field theory to deform it into that, and what I have to do on the gravity side. Okay, this is part of this dictionary I was discussing before regarding Alfredo's question. Am I answering your question?
Yes, fully. Thank you very much. So in principle, it's fine. It's a valid conjecture. Of course, it's a conjecture view.
Yeah.
It cannot be proven rigorously, but in the examples you discuss with symmetry breaking, it's valid perfectly. Thanks. Thanks very much.
You know what you lose in here? You lose the quality of the tests that you can, right? Because having less symmetries, the theory is less protected. So observables that you can calculate, say, perturbatively, and say, okay, this observable is protected, okay, ceases to be. Okay?
Yeah, of course. So it's expected that you lose something.
Right. You lose some calculational...
Yeah, tools. You cannot do a fully non-perturbative, which is expected because you lose symmetries. So,
exactly.
Thank you very much.
Thank you.
Appreciate it. Thank you.
Are there considerations, questions? That's perfect. Okay, Luca, go.
Yeah, thanks, Luca. I have a question for Leslaw. Hi, Leslaw. So, in your talk, you spoke, of course, about conformal grounded one loop, but in some of your papers, I read some consideration the two-loop computation, which were concerned with the R square term. Okay, and I know that, for instance, from Toftem and Heim claim that there will be no R square appearing, not even at to loop because of conformal symmetry. But in your paper, you say that you have good reason to expect that R square can be generated at two loop. But I'm not sure I've really understood the reason why you would expect them to appear. Can you maybe comment on that?
Yes, sure, Luca. Actually, it was not me. The story is, of course, older, probably even older than me. The first paper was by Fratkin Zeitlin from 80, as I remember, 2 or 83. So they show that, of course, on the one loop level, you don't generate this R squared term. So your theory is the counter terms you write, they are exactly of the C type. So everything is, from the point of view of divergent action, is conformal invariant. But they showed not, of course, fully fledged, because even now no one can do two loop computation. But they show some, say, relevant parts of the two loop computation. And from this part, you can deduce that the R squared term will be generated there. So basically, you only take the scalar mode, and then you see that there is some divergence that you cannot absorb. So R squared will be generated in conformality. So this is the old wisdom. And now I want to say that, okay, since the two loop computation till the end was not done, because you cannot do using covariant techniques, you have to really probably either some very tricky technique of resummation like Bern Kosover or I don't know, Feynman diagrams, but this is probably hopeless. So there are some people, like you mentioned, 't Hooft and Mannheim, since no one has computed two loop, they say that maybe there is still a hope this R squared term will not be generated and the theory still will be conform at two loop. So let me just substantiate why you can have this hope. Because in gravity, a lot of happen. For example, if you forget about conformal gravities, you just go to highly supersymmetric Einstein gravity, so to normal supergravities, you met already many times that the worst predictions about divergences do not fulfill. So there is a whole series when they saw that, for example, at at 4 loops or 5 expected divergence in supergravity, like high supersymmetric, like n equal 4 or n equal 6, but they are not. And the reason why it is not there is not very clear. I mean, it's some hidden symmetry which is not visible in the original formulations that we have now. So you may think that the same will happen in conformal gravity, that you may have some hidden symmetry there, which is not present in the current formalism that we use. And this symmetry might be so powerful that even at two loop, it will prevent R squared from being generated. So I think this is the hope that and Mannheim still keep. Why they keep? Because no one has done two loop computation. If someone would be so bold to do this, then probably this question would be settled down. But yeah, I just in my papers I just repeat what was the argumentation. Is not that I'm the first who did it. So of course, as I said, people did it 30 or 40 before me.
So I would say, I mean, there is no really very, very strong reason to say that there must be an R square contribution, right? So I would say still.
No, I mean,
totally
if you look in Fratkin Zeitlin, I don't think anyone has any objections to their computation, although it's not full, but just a sector which is relevant, and I don't think that
I mean,
that this is any problem there.
It may still happen that the contribution which is still missing may cancel that, or
yeah, because okay, the standard, sure, in Fratkin Zeitlin is based on genericity. So if you take a generic situation, you would expect that the coefficient is, and this will say that the R squared term is generated. But maybe there are some miracles, we don't know. And these miracles can be such that maybe the coefficient will turn out to be 0. That's quite unlikely, but still possible. And as I said, miracles are possible, in gravity especially.
Thanks.
You are welcome.
Other questions or comments? Tom, now I unmute you. Please.
Okay, now I should be able to say something. So I'm still coming back to my question concerning quaternions and this geometrical algebra. So I would like just to get a feeling, nothing else. So is there, Václav, is there something what you are at least a little bit more familiar with this topic? What is linking this quaternions algebra? I mean, to give it more more geometrical view or motivation, how to link it to this geometrical algebra. I mean, for example, the number of such complex numbers, etc. If I'm not clear enough, please say.
Oh, I see. I mean, the quaternions are quite geometric already if you view them as spinors in the three-dimensional space. As real spinors, that is the even multivectors. So they consist of the scalar part and the three independent bivector parts. And these three bivectors are the three orthogonal planes, and they are just literally the quaternions. If you multiply them and use the geometric product as the product, you have the algebra of quaternions. So I think there is not any better geometry to assign to quaternions. And with these bivectors in three-dimensional space, you can do all those rotations, and this is the quaternionic implementation of rotations. And as regards, and then with this identification of quaternions being the real spinors, of course, you can write them as two complex numbers, as these Pauli spinors, if you like, and then you split them into two complex numbers. I guess that's maybe also common in quaternionic literature, but I don't know. For me, quaternions are like just real elements in the three-dimensional Clifford algebra. So.
Okay, I mean, I wanted to comment during when you're talking, but I was not able to come. So look, the question is rather, I mean, you said there is a number four, right? This is what you predicted in some sense, what you are able to do. And it seems that you cannot do more. So the question is whether, I mean, you have in this geometric algebra view, you cannot get a bigger algebra. I mean, something more reached the quaternion algebra, because it's given, you cannot get more. You understand me?
Yeah, I mean, if you take three-dimensional space, this is what you get, and you can if you consider higher dimensional spaces, then you have bigger spaces of even multivectors.
So basically, when you go now to this generalization, I mean, when you mentioned at the end of your talk, right? So you will still consider, I mean, 3 + 1. You will not go to the more dimensional space just to see what you will, I mean, eventually how much you will enrich it. I mean, you think it will be trivial. That's what you mean.
No, I don't think it would be trivial, but I mean, I'm just happy with the 3 + 1 dimensional physical space. I mean,
just to get some, I mean, the question is if you will get some more limitations, for example, because it somehow naturally contains this quaternion group there. I mean, in this geometrical algebra, you are getting 4. This is the number, right? So that man would expect that you will provide eventually another limitations for the higher dimensional space for such considerations. But okay, I will do it differently. I stop here. I mean, you are based in ČVUT, right, in Prague?
Yeah.
So you can tell us a little bit more. I will write you. Okay, thank you very much.
Okay. Yeah, perfect.
Okay. So, are there any other questions or comments from the audience? Please raise hand. Don't be shy. So otherwise, I can ask just a curiosity to Leslaw. So if you, it's just you mentioned many motivations behind conformal gravity, why it should be studied, and so on. Okay, and it's very interesting. Just curiosity. Yeah, among the various things you mentioned, the Mannheim argument, Mannheim solution of the dark matter problem, let's say. But in the last 3-4 years, they were published. This is about classical wild gravity, and there were published various papers on gravitational waves in conformal gravity. And clearly you have modifications. Instead of having just spin 2 modes, you have other kind of solutions. And but the interesting fact, it appeared, as far I understood, is that if you try to fit the rotation curves of the galaxies, you cannot fit the gravitational waves. And if you try to fit gravitational waves, you cannot fit the curves of rotation of galaxies. And so there were proposed conformal gravity models with dark matter, which is actually beyond the original argument of Mannheim. It seems strange to me because Mannheim actually studied a lot conformal gravity exactly because it couldn't do everything without introducing dark matter. I want to just comment from you about this, if you.
Yeah, so thanks, Luca, for this question. Yeah, so let me just repeat what Mannheim writes in one of his articles, that basically because this is one of the features of conformal gravity that actually I didn't have time, but maybe on one slide I flashed that it's a fully Machian theory. So basically you don't explain the things locally. The global structure of space-time matters. So actually for this Mannheim-Casanas solution, what matters is, for example, behavior of the universe in late time. So there is one term in the solution which is actually driven by the cosmological constant, or by the expansion, accelerated expansion of the universe. So this is one thing that, of course, personally have nothing against matter. If it will be discovered experimentally in particle physics detector, it is there. Just that, okay, I agree with you that maybe Mannheim was very strict, saying, I don't want dark matter, completely other solution. But let me just point that he says that it is not dark matter, is a local solution, because you say, okay, here they are particles, and they are the objects that you can detect. Instead, he says that they are maybe different, and then you have to look at the global scales, and then the solutions are different. And now to this to this middle point, you mentioned that it is impossible to fit two things at the same time. Look, this is a story with very conditions, because if you have the differential equations that you want to solve in a classical regime, and here you have differential equation with 4 derivatives, yeah, because conformal gravity is a theory not with 2 but with 4 derivatives. It means you have more integral constants, and how you typically choose them, you choose the boundary conditions. And of course, for different physical problems, you can put different boundary conditions. And as I said, for example, for the galactic rotation curves, Mannheim used, and also with O'Brien, they use this identification, what happens not only on the galactic scales, but of course, there are basically 3 regimes. One regime is when you have 1 over r, and this is, let's say, solar system of gravity. And there is this intermediate regime when you have constant term, and this is flattening of galactic rotation curves. But then there is also another term, the final one, the ultimate one, which goes like r. R is, of course, the distance from the origin. And this r squared term is related to the embedding in the de Sitter. So it's basically the cosmological term. So you can like in conformal gravity, you could say there are three regimes for the gravity: the solar system, the galactic, and the logical. And the solution that Kazan has found was basically using all these three ingredients. So this depends on the boundary conditions. And I think in the situation when you want to put at the same time gravitation and dark matter, then okay, I don't know whether this was really studied, that you have situations when both you study some galactic rotation curves and gravitational waves in the same physical system. But if not, then these are different configurations, so we have different boundary conditions. So I would say the theory has now 4 derivatives, so it has 4 integration constants. So yeah, these different boundary conditions, they solve the way, because for different physical configurations use different boundary conditions, and everything is, I mean, on one side is consistent in gravitational wave is consistent, on the other side for dark matter is also consistent.
But the fact
I hope
is,
that this
the fact is for further, it means that linearized equation in fact is so for further, and it's exactly the reason for which you have more than one mode. You have not just spin 2 mode, standard spin 2 modes in when you try to solve
if you want
linearized equation. But the point, if I understood, was exactly about fixing the coupling constant, and that at least at classical level you don't have running coupling or something else. Then you
sure
have different
this
regimes.
is not possible.
So you should manage to fix both kind of experiments without. Probably, okay, now possibility is that in quantum theory you can find a solution of this dichotomy, but
yeah, but I also think that, yeah, you see, since they were, okay, you have a general theory, but now depending on which configurations you prepare the specific boundary conditions, and I would say they are different for dark matter, different for gravitational waves. And I agree with you that, of course, if you study the linearized equation of formal gravity, you have more degrees of freedom. Basically, this is that number 6, not 2. Sure. The 2 was in the question that I received. That 2 is the 2 polarizations that you have in Einstein gravity. That's what we see as the 2 helicity states of the spin 2 graviton. But in the spectrum of the conformal gravity, linearized around flat space, you don't have 2, you have 6 freedom, because there is also the massless spin 1, which is a vector, so it has a helicity. Exactly. And then there is another part which is a spin 2 massless, but this is with bad fame, the ghost, so you have to be careful about it. But generally, they are additional degrees of freedom, so you would, if you are, this is of course a question about the boundary conditions, but if you are, let's say, choosing boundary conditions as in Einsteinian gravity, you should also see the same thing in the gravitational waves, because as I showed, the exact, not linearized, but the exact solutions of gravity, they coincide with those of Einstein gravity. So if you study the propagation of gravitational waves in empty space-time, then there is no matter from the gravity side point of view, and the equation the solutions in Weyl gravity are bigger, but there is a sub which coincides exactly what you know in Einstein gravity. So it's exactly the same gravitational wave propagating in empty space-time in conformal gravity as in Einstein gravity.
I see.
To have more degrees of freedom, you have to probably prepare different boundary conditions, which is, we know how to do this when you solve equations, but I don't know if we have technically mastered the procedure how to change boundary conditions for the gravitational field. This may be a bit technological challenge right now, but we have to see and we have to observe given to us by nature, and if we observe the gravitational wave, they are there. We observe this.
Sure. In fact, I think it's the reason for which they're proposing this now Weyl gravity models with dark matter is that it's easier to modify that side. That's the side of gravitational waves.
Sure. But
very direct prediction, I would say.
But as I would say, I have nothing against dark matter. If it will be needed to be added, it's the same like, you know, in particle physics. They discover new particle. It was not expected. It is there. So yes, you have to accept. You have to live with it. It is there.
Of course, what you cannot avoid is dark energy. That's a different issue. Am I right?
Sure.
Yes, yes.
Dark energy you cannot avoid because it's the
I
vacuum
think in
of your of the
conformal
conformal
gravity, Leslaw can correct me. The contribution to dark energy is given by coupling with scalar field when
That's
you
right.
have
That's
conformal
right.
symmetry breaking, right?
That's right. It's like quintessence.
It's addressed actually.
Yeah, so actually, yeah, I agree with you. There is also a point of view of Mannheim, and yeah, it's actually quite simple that if you just take dark energy, which has equation W equal -1, equation of state, then the solution, at least classical, is maximalist space. So this is de Sitter, and de Sitter as a manifold is conformally flat. So by conformal transformation, you go back to flatness. So there is one paper and when he says that there is no cosmological constant problem, exactly because of that, because the solution is equivalent in conformal gravity to flat solution. So you don't need the, I mean, cosmological constant in this sense, it's a you could say a constant of integration, but it's not really anything that it is tangible to measurement, because by conformal transformation you can say it's a flat spacetime. So the spacetime,
it's a scale. You cannot have a scale in a conformal situation. But dark energy is a field. It's a different thing. And you might have deviation from W equals -1 actually. I think that's what was.
Yeah, of course. If you have
that's what I call dark
yeah,
energy.
the story is not so simple. Yes.
I avoided the use of cosmological constant because cosmological constant is an energy, is a scale with dimensions of mass. So, but mass to the fourth. So you cannot have scales in conformal gravity in any conformal theory. In that sense.
Sure.
Thanks.
Thanks.
Good. Are there any other questions, comments? Okay, if not, I think we can really take some time, 20 minutes before the next session, and we can recollect at I think 2:45, right? For the next talk.
Yes.
Sure. Okay. I thank once more all the speakers of this first session, and see you later. Stoppo anche la live YouTube o la lasciamo andare?
No, penso che puoi continuare, perché alla fine abbiamo fatto così pure ieri e l'altro ieri, quindi non fa niente.
Infatti.
Piuttosto dopo, chi vuole registrare dopo la prossima sessione? Chi può, in realtà. Io avevo fatto...
Io ho sempre paura che possa andare in contrasto. No, non c'è. Luca, tu hai provato a fare tutte e due in contemporaneo, live YouTube?
Sì, si può fare, non c'è problema.
Okay,
però posso parlare anche di questa qui. Però non devo essere tutti, quando sono 4.
Ma il problema no, tu non riesci, perché poi dovresti tornare in hotel, no?
No, ma ti salvo, riesco, puoi fare, li puoi scaricare, li puoi salvare dopo, non è un problema.
Eppure se non stai nella room, no?
No, dico se faccio le 3 sessioni, però effettivamente vorrei andare a casa prima. Il primo talk posso farlo.
Non ha senso spezzettare, il secondo faccio pure io il secondo e va bene così. Adesso ho interrotto quella della prima sessione, poi faccio pure il secondo.
Vede, io posso interrompere anche la live e poi la faccio ripartire, tanto non è molto utile in questo momento.
Vabbè, ma non niente. Avremmo 2 video inutilmente, cioè, capito?
Vabbè, allora lasciamo. Vabbè, allora ci vediamo fra 20
minuti. Se puoi intrattenere con un intermezzo musicale, prego. famiglia chitarra.
Non l'ho portata la chitarra. Quindi. Va bene, ci vediamo fra una ventina di minuti.
Ok. Può intervenire ogni tanto, non è che subito si è mutato.
La vergogna.
Vabbè. Voi avete cenato? Io mi sa che mi concedo una rapida pausa pranzo. Victor, tu hai mangiato, sì? Hai la faccia di chi è soddisfatto. Sì, no, penso che dovrei avere giusto il tempo per...
Mi siamo fatti una bella pizza.
Vabbè, fin quando ci sta il pizzaiolo napoletano, però, scusa. O Kyoto, o New York, o Napoli, insomma.
Parla, bisogna. No, perché sei votato, sei...
Bene. Comunque dovete fare un tentativo, una prova per il bene dell'umanità. Dovete assaggiare quelle pizze che si prendono nei distributori automatici, perché voglio capire qual è la differenza.
Ma io non ho mai trovato un distributore...
Perciò ti dico, so che ci stanno, se non ero avevo letto notizie che volevano metterli anche in Italia, anche se qua penso che avranno meno successo rispetto al Giappone. Però
ho visto qualche video con questi distributori, però non ho mai trovati, me ne stavo per strada. Però se lo trovo, sì, per curiosità assaggio.
Fammi sapere. Ok, sai che io mi defilo giusto 5 minuti per mangiare al volo.
Dai, ci vediamo tra poco, ciao Luciano.
Ciao.
Lots.
Bravo.
Funziona?
Sì, funziona, funziona.
Ok.
Fabio ancora non è costo.
Ma noi non possiamo renderlo post, giusto?
No, Luca deve farlo.
Fabio, ci sei?
Eccomi qua. Ciao.
Ehi, tutto
Ciao.
bene?
Sì, sì, tutto ok.
Buongiorno organizers, come va?
Ciao Roberto, tutto bene? Te?
Non c'è male, dai.
Ciao Roberto, come stai? Buongiorno.
Era
Anzi,
più bello
buon
era più bello
pomeriggio.
trovarsi giù, non so, dalle parti di Salerno. Non so.
A Vietri sul mare, sì. Tipo...
Ma anche altri posti, però...
sì, speriamo presto.
Speriamo, sì.
Che faccio? Provo lo share screen?
Sì, abbiamo un paio di minuti, Fabio, poi provo.
No, mi sa che non è cost, Fabio, non può fare.
Non è
Ah no,
cost?
mo sei cost, perfetto, puoi farlo. Ora si diventa cost.
Allora, che faccio? Lo metto?
Vai, prova.
Provo, eh? Aspetta. Clicco sul verde, giusto?
Right.
Allora, share screen, tac. Così?
Ok, sì, però lo metti a full screen.
Ah, aspetta che lo metto a full screen, dunque. Dov'è che?
No, forse è view a destra.
Eccolo lì, sì, view. Full screen mode. Ok, vediamo cosa succede. Sì.
Ok, perfetto.
Però non riesco a leggere le mie slide, perché c'è la strisciolina delle telecamere sulla destra.
No, in realtà penso tu possa spostarla pure in alto. Se la trascini, penso che quella si sposta pure in
Ah, sta a
alto.
fare qui, la posso spostare dove mi pare? Ah, sì.
La puoi anche ridurre di dimensioni, Fabio.
Come faccio a ridurla?
Afferri il bordo e la stringi, di solito funziona.
Vediamo cosa succede.
Col mouse, come se tu la trascinassi.
Butto di qua, io la butto. No. Tanti saluti, così non mi impallate. Okay. Sì, dai, così va bene. Vi vedo parzialmente. Quindi.
Ok, non so se vogliamo aspettare. If we want to wait some other minutes, I don't know.
Ma come volete voi, per me è indifferente. Magari la gente torna da pranzo.
Let's switch to English.
Maybe a couple of minutes, 2 minutes.
Okay. So we shall start within 2 minutes.
Ok, fine.
Comunque salve a tutti gli speaker della seconda sessione.
Did you have your lunch, Fabio, Roberto? Pasquale is breakfast.
Yeah, I had it.
Yeah, I just finished my breakfast.
Ah, the beauty of virtual meetings.
Ok. Ciao a tutti gli speaker. Tranne Fabio.
Cosa?
Saluto a tutti gli speaker, tranne a Fabio. Dico.
Ah, saluti a tutti gli speaker.
Sì.
No, ha detto salute.
No, salute no. No.
Okay, Alfredo is here. Okay, I think maybe it's time to start. So welcome to this middle session of the third day of TQTG 2021. And it's a great pleasure for me to be the chair of this session. Here we have 3 speakers who are actually 3 colleagues and friends as well for me. And so the first speaker is Fabio Scardigli from Politecnico di Milano. Second one, Roberto Casadio from University of Bologna. And last one is Pasquale Bosso from Lethbridge University. So let's start by the first talk, Fabio Scardigli, who will talk about the Bekenstein bound and uncertainty relation. Fabio, you have 30 minutes plus 5. You can start as soon as you are ready.
Okay. Okay, so let's start. First of all, of course, I thank very much the organizers for the invitation and for the very beautiful meeting conference they were able to put together. It's really interesting, at least so far. I will tell you something about the Bekenstein bound and uncertainty relations.
And this is a collaboration with Luca Bonifante, Gaetano Luciano, and Luciano Petruzziello. Let me first tell you something about the Bekenstein bound itself. So the so-called universal entropy bound proposed by Bekenstein in 1981. Essentially, Bekenstein said that the entropy of a localized quantum system can be bounded from above by a very simple relation containing, apart from the fundamental physical constant, essentially the sides of the system itself are and the total energy content, energy mass, energy content of the system. According to Bekenstein, the universal entropy bound defines how much information can be stored by a mass energy contained in a region of size d. It is derived by imaging, at least the original derivation was made by imaging that a capsule of matter energy is engulfed by a black hole of about the same size. And then the increase in the black hole size places a limit on the entropy that the capsule may contain. Although the Bekenstein bound was derived via Gedanken experiment involving black holes, which means essentially in a strong gravity environment, G Newton does not appear in the equation. As you can see immediately here, there is no G Newton. So essentially, the bound is considered to be valid for gravitational for system with a gravitational self when the gravitational self interaction of the system is neglected. The inequality proposed by bound is by Bekenstein is saturated by the Schwarzschild black hole entropy. Essentially, which is given by this expression here, the famous expression proposed by Bekenstein in '72, the proportionality between the entropy of the black hole and the area of the event horizon. The Bekenstein bound is tighter than the holographic bound, except when the capsule is almost as dense as a black hole, and then the two bounds are equivalent, goes to coincide. The history of the proposal of Bekenstein is a little bit twisted. In any case, the bound has been very directly verified, of course, in terms of theoretical calculations, in many papers. For example, I just reminded the paper of Gibbons and others. Some counterexample or believed counterexample have been discussed during the years. And finally, in 2008, Orazio Casini proved the bound rigorously using the standard quantum field theory in flat space-times. What we have done with my collaborators and friends is to connect the first step was to connect the Bekenstein bound directly with the Heisenberg uncertainty principle, essentially a direct derivation of the bound from HUP via a simple thermodynamic argument, which is I'm going to illustrate to you. Given an isolated quantum system localized in a region of size R, then we know very well that the relation between the energy, the entropy, the volume, and the temperature is given by the thermodynamics. So is this relation here. Then we have done just very simple, very general assumptions. Essentially, we considered valid the equipartition theorem. Therefore, the energy of each constituent of this bunch of matter energy should be proportional to the temperature of the system. The system is supposed to be weakly interacting, essentially, this means that the energy of each constituent is just given by the standard dispersion relation, the standard relativistic expression of the energy. And of course, then there is the quantum ingredient, so to say. We suppose it to be valid, the de Broglie relation between momentum and wavelength, which, by the way, is substantially equivalent to supposing valid the Heisenberg uncertainty relations. Immediately from here, you can derive this very simple inequality. And since our system is localized, so is more the de Broglie lambda is smaller than the average size of the region where the system is localized, then again immediately you arrive to this differential inequality. And in the hypothesis of R independent from E, so the size independent from the energy of the system, then you can integrate this differential inequality, and you arrive to the expression of the Bekenstein bound. Of course, modulo a constant which cannot be fixed by this very simple thermodynamic argument, and essentially should be fixed a posteriori, requiring that the bound goes to coincide with the formula proposed by Bekenstein. So this fixes alpha equal pi. It is also very interesting the fact that this inequality is valid, holds also in the case in which R is a general function of V, provided this function is a monotonic non-decreasing function. It's a monotonic non-decreasing function. You can still derive this inequality from this very general thermodynamic relation. Not only it is possible to derive Bekenstein bound from the HUP, it is also possible to do the opposite. Essentially, supposing valid the Bekenstein bound, you can derive the Heisenberg uncertainty relations. And actually, this has been done in a little bit convoluted form by Bosso in a paper of 2004. Suppose to consider a particle of rest mass m described by a wave packet of size r, and suppose that the particle is marginally relativistic, so essentially the relation between P and E is this, then the Bekenstein inequality can be swiftly recast as in this way. Essentially, E over C is just P, R is the size of geometrical size of our system, and so you arrive immediately to this first inequality here. And the second part of the inequality is also true for any system in which the entropy is at least of order of KB, of the Boltzmann constant. For example, a very simple system like a particle, suppose an electron with spin up and down, you have an entropy of the order of KB. You have an inequality like this, and then since the direction of the motion of our particle is unknown a priori, we can safely suppose that the uncertainty in the momentum in the x component of the momentum of our particle is of the order of the momentum itself, and obviously our particle, to be precise, the wave packet describing the particle is confined in a region of size r. Therefore, delta x is of order, the uncertainty on the position is of order of r. And immediately you see that this inequality is the Heisenberg uncertainty principle written for our specific particle. So we have established a correspondence and one-to-one correspondence between the Bekenstein bound and the uncertainty relations. And this, by the way, can explain also why the Bekenstein bound has such a general validity. Once you have done this, of course, we have considered that the fact that the Heisenberg uncertainty relation can be generalized and actually has been generalized during the years. Here I have my usual slide telling in a very compact way a long history in a few lines. Essentially, this kind of generalization of uncertainty relations have several decades nowadays of history, starting from Bronstein before the war, and then Young, Snyder, and Mead and Carol Yaz in the 60s. And then, last but not least, string theory suggested that in Gedanken experiment on high energy string scatterings involving gravity, the effective uncertainty relation should read in this way, where you have the usual Heisenberg term, deformed, so to say, by a term proportional to the momentum transferred into the scattering. Obviously, you can rewrite the relation in this way. Or if you are interested in a plot of delta x against delta E or delta P, you have a plot like this one. Essentially, if gravity were not there, then you would have just the standard Heisenberg hyperbole here. But since there is gravity, you have this deforming term where the G Newton appears explicitly in the Planck. This is written here in the form of Planck length, but of course here there is G Newton, or if you like, here there is the Planck mass. String theory is not the only way to arrive to this kind of deformation. Different ways bring to the same result. For example, Gedanken experiment involving formation of micro black holes in a measurement process, or also completely different approach proposed by Maggiore arrives to a similar relation, considering the Hawking radiation emitted by a large black hole. And uncertainty relations like these have been studied and derived from deformed commutators in a very important seminal paper of Kempf, Mangano, and Mann in 1995. So now that we have considered this generalization of the uncertainty relation, of course, you have a correspondent generalization of the de Broglie equation, which actually was proposed these two quite long ago, 20 years ago, by Ahluwalia. Here you have the generalized wave-particle duality in case, as I said, of the in case of a deformation of the uncertainty relation. If you start from this relation instead from the classical de Broglie relation, then you can derive the P as a function of lambda. This is the expression, which obviously go back to the standard de Broglie relation when beta goes to 0, if you choose the minus sign here. And again, if you repeat similar steps as those we have seen before, so considering a system of size r confined, whose de Broglie length is confined in a region of diameter 2r, more or less, immediately you get again a differential inequality like this. At this point, I would like to discuss separately the two cases in which beta can be positive or negative. In case of beta positive, we know that the GUP predicts a minimum observable length of the order of the Planck length, more or less, time the deformation parameter. And then, assuming the usual independence between R and E, with the usual initial condition for the entropy, by integrating the previous inequality, we get this expression, which is actually the what we proposed as a generalized Bekenstein bound. Still, this argument does not give an exact value to this alpha, which, however, can be recovered again by demanding that when beta goes to 0, you go back to the usual formula of Bekenstein, and this fix alpha equal to pi. Moreover, the inequality can still be derived in the very general case of a monotonic non-decreasing function relation between R and E, the size of the region and the energy contained in that region. This expression can be expanded in beta, the first order, which maybe gives a better understanding of the expression itself, since here we have the usual bound proposed by Bekenstein, and here we have the correction due to the GUP, to the generalized uncertainty principle. Some notes can be the fact that the generalized Bekenstein bound lowers the standard, the usual Bekenstein bound when beta is positive, as you see. However, a Schwarzschild black hole will not violate this generalized bound, since if you go to compute the entropy of this Schwarzschild black hole using GUP, you will find an entropy. You will find an entropy which is lowered also in respect to the standard entropy computed with the standard Heisenberg principle. Physically speaking, it is expected that the existence of a minimum length reduces the number of microstates in a given volume, thus decreasing the total information that can be contained in a system of a given size. This is quite intuitive from the physical point of view. I want also to discuss the case of beta negative, which maybe can sound a bit strange, but is not so strange if you think that, for example, already 10 years ago, we proved together with Petr Jizba and Hagen Kleinert that if you formulate the fundamental commutator between x and p over a lattice, you end up with a formula where the beta is negative. The first correction is in beta is negative in respect to the standard Heisenberg commutator. And this, by the way, can represent also a link to what my friend Alfredo was telling yesterday about the lattice, the graphene lattice, where actually the commutator has this negative term. About the consideration, well, the calculations are similar, obviously, to the case. The mathematics, I mean, is the same, just beta is negative, so you can integrate again the differential inequality, thermodynamic inequality. Again, you can fix alpha to equal pi, demanding that the standard Bekenstein bound is recovered for beta goes to 0, when beta goes to 0. And again, the inequality holds for any monotonic increasing function of R as a function of E. If we expand this formula to the first order in beta, we get an expression like this. And we see that for beta negative, this generalization of the Bekenstein bound allows the entropy to exceed the standard bound. You have a plus here. And by the way, this is also not so crazy as maybe can appear at the first sight if you think that for beta negative also the standard Heisenberg principle can be violated. I mean, with a generalized uncertainty principle containing a beta negative can violate the Heisenberg inequality. The situation can be the situation of the three bounds can be summarized by a diagram like this, where you have the blue line representing the usual formula proposed by Bekenstein in 1981. And here you have the two corrections that we have studied. The yellow line is the case of beta greater than 0, which, as you see, it stops because there is for beta greater than 0, there is a minimum length. And for beta negative instead, there is, in principle, there is no minimum length, and you have this red line here above. Let me tell still a couple of things about the fact of the case of beta negative. As I say, that the GOP in this case implies for an uncertainty in momentum of the order of the Planck momentum implies an inequality like this, which is typical of a classical regime. Essentially, the uncertainty goes to 0. I mean, the term on the right hand side of the standard Heisenberg inequality goes to 0. This possibility, this gives possibility of a classical physics at the Planck scale, and actually this possibility may sound crazy, but it's a scenario already explored, at least in several papers. For example, I remember the paper of Magasian and Smalling, the one where they proposed essentially their version of double special relativity. There is an explicit formula in which H bar is considered a kind of dynamical field vanishing at the Planckian energy, and so giving a classical behavior at the Planck energy instead of a quantum behavior. And another very intriguing possibility that we have a universe in which at the Planck scale appears to be deterministic. Well, this possibility is contemplated. I mean, the universe appears to be deterministic instead of being dominated, as the standard knowledge would demand, by quantum fluctuations. This idea is at the core of the vision of the Toft proposal of a deterministic quantum mechanics, a deterministic foundation of quantum mechanics, in which this determinism somehow should become evident or clear close by to the Planckian energies. So I go swiftly to my conclusions. We have proved essentially a one-to-one correspondence between Heisenberg uncertainty relations and Bekenstein bound on the entropy of a localized quantum system of a given size and energy. We have generalized this Bekenstein inequality using the generalized uncertainty principle approach, when both the quantum and gravitational effect at the Planck scale are taken into account. And of course, still many avenues remains to be explored. First of all, the possible consequences for the holographic bound, which obviously should be modified also. These can have consequences for quantum information theory. And
Fabio, Yep. 5 minutes left. So if you want to say something else, you can add.
To be honest, I was going to just to conclude here. Maybe I can give more time for questions if there are questions.
Okay.
Just I was saying that the last thing that can be affected by this modification of the Bekenstein inequality is the information paradox for black holes. And so yes, I would finish here. Maybe it's still well 3, 4, 5 minutes perhaps earlier. Okay.
Okay.
That's all. Thanks.
Okay. Thank you, Fabio, for your nice presentation. We have time for several questions, actually, or comments or criticism. I see. Okay, Luca Smaldone, please.
Okay, just a curiosity. Very nice talk. And the standard Bekenstein bound is usually saturated by a black hole. And so you mentioned that this this modified Bekenstein bound is not violated by black hole, but you didn't mention if this is saturated by a black hole, taking into account that also the black hole entropy, as you said, should be modified.
Yes, it's going to be saturated if you recompute. Wait a second. If you recompute, where is the expression? Here, yes. If you recompute the entropy of a Schwarzschild black hole starting from a GUP, from a generalized uncertainty principle, you will see that the entropy get corrections, and essentially to the first order, you see that the Bekenstein bound saturate the GUP deformed Schwarzschild, the corresponding deformed Schwarzschild black hole entropy.
I see. So very nice.
Everything is reproduced also in the case of deformation, so to say.
I see. Thank you.
Okay, thank you, Luca. Next question by Alfredo.
Hi. Okay, can you hear me? Yes. Thank you, Fabio, for this very nice talk. It is just a curiosity about, well, it's very interesting. It's two questions, very quick. So one is, do you actually have a one-to-one correspondence between the bound and the uncertainty principles? I mean, this is rigorously proved, because it is, of course, intuitively reasonable, but to have it fully under control would be very nice. And second question, have you considered like quantum correction to the Bekenstein formula when, as Luca was saying, is saturated? Because when it's the black hole, you have quantum correction, you have an extra term there, which is a log, because like the log of the area, and you do have two terms there. So I was wondering whether you've been including that in your story.
Yes. I think I can answer yes to both of your question. The first, okay, sorry. The first was about let me go back to the derivation. You say, right?
The one-to-one correspondence. So it is truly one-to-one.
Well, of course, this is a thermodynamic argument. So, for example, doesn't give to you the alpha. You have to fix the alpha posteriori, so to say. But the argument is very clean. So, I think quite robust. I don't think you can destroy the argument easily, so to say. So, by the way, the fact that HUP can be derived from the Bekenstein bound was already something written in the middle of the lines of a paper of Bosso in 2004, not explicitly clearly written, so to say, but the derivation is essentially similar to the one that we proposed here in this. I mean, this kind of derivation. So until, of course, I'm aware of the fact that this is not a rigorous proof. Obviously, it's not a rigorous proof in quantum field theory. It has nothing to do with the very rigorous proof of elaborated by Casini, proposed by Casini in 2008. But I think that given the generality of the arguments, is also quite robust. Is also quite robust. I mean, I don't think it can be easily disproved. Something like this. And for your second question, the fact that the entropy correction, yes, if you compute the correction to the black hole entropy in 4 dimensions to a Schwarzschild black hole, you get this log term, and this is I mean, it's okay. It is still the deformed, the GOP deformed Bekenstein bound is saturated by this deformed GOP entropy of the Schwarzschild black hole, as I was saying also to Luca Smaldone earlier.
Okay, thank you.
Okay, thank you, Alfredo. Maybe we have another question by Lorenzo Marcone. If it is a short question, otherwise we can discuss in more detail in the discussion session. Lorenzo?
Okay, maybe now I managed to unmute myself. So I'm curious about this proof you showed that is on your slide. You're saying that Bekenstein bound implies the Heisenberg uncertainty, but then you're using a relativistic particle, whereas the Heisenberg uncertainty is not necessarily for relativistic particles. So this is strange, no?
Well, partially strange.
The first hypothesis you have in this slide.
Yeah, I see. I don't think it's so strange in the sense that you can essentially consider particles marginally relativistic, or even photons you can consider if you like. And
but it does not apply to photons, that uncertainty relation. I mean, you cannot localize a photon.
Yeah, okay, but in this case, I'm thinking about this relation, P and E, sorry. So I don't think it's particularly strange. Of course, I agree with you if you tell me that it is not rigorous, because a rigorous proof would be obtained considering the full dispersion relation between P and E. So for massive particles, I fully agree with this. Is something that, so to say, still should be cleaned in the proof. But I'm quite confident that this kind of argument can be successfully cleaned, if you like. It's something that still we wanted to investigate, so to say.
Great, thank you.
Okay, thank you, Fabio, for your talk. So there was another question by Luca, but maybe it's better if we postpone to the discussion session. So thank you again, Fabio.
So I just I stopped sharing. Okay.
Stop sharing. Okay, thank you.
Stop sharing. Okay.
Okay, so let's move on to the next speaker, who is Roberto Casadio, and he will talk about quantum black holes and the resolution of the singularity. Roberto, again, you have 30 minutes plus 5.
Okay, can you tell me if you can see my slides?
Yeah, we can hear you, we can see you. I don't know if it is on full screen, right?
Yeah, just give me a second. Can you see it better now?
Okay, okay, perfect.
Now, I didn't switch on my camera, but that's probably not a big problem. My connection is not always very good at home, so
okay, don't worry.
Oh, nice. It doesn't go backward. Okay, yeah. Well, thank you very much for your invitation. And as you can probably tell from the title of the presentation, let me try to see if I can turn on the camera. So I think it would be nice for everybody to see each other. I don't know where it puts. Oh, yeah, there we go. Every time they update Zoom and other stuff, they change position. So I don't know if you can see me now. Not that you missed much. From the title of the presentation, you probably figure out this is about singularities predicted by general relativity and their possible fate in quantum theory of gravity. I think there's probably a general consensus nowadays that such singularities should not be there in the quantum theory, if for lack of a better argument, because of the Heisenberg uncertainty principle. So the question is really, can we learn something from a quantum description of black holes that remove the singularity about the general theory of quantum gravity on the one hand, and on the other hand, can we make possibly phenomenological predictions of quantum gravity that can be tested somewhere in the space? Okay, going. And so here I'll present just a few simple arguments, really, that point toward, let's say, both directions, if you wish. And I know if you can see my pointer, you will find all the details in these two preprints that
we can see your pointer anyway, Robert.
Thank you. Which I posted recently in the archives. Now, as a preamble, I mentioned quantum gravity. The first thing that everybody says about quantum gravity is probably that we have no data about it, which is correct, in a sense. The right interpretation of such a sentence is that really we have only access to the classical sector of whatever quantum theory of gravity is. If we believe that, and we have all the reasons to believe so, that quantum physics is the correct description or the better description at our disposal of the world, it's not that we don't know anything about quantum gravity, but we can only test experimentally a subset of states of the full quantum theory, which are roughly orthogonal. There's no superposition of macroscopic states, and such that the expectation value of all the accessible observables of the quantum theory follow very closely the classical behavior. And I would like to stress, this must hold just for the observable that we can actually test, not for all the operators we can conceive in such a theory. Now, this doesn't mean, however, in particular, that the quantum space of this theory that we call quantum gravity should contain a state for each and every classical behavior we can conceive, because this is not how quantum physics works. And the prototypical example is given by the hydrogen atom that we learned from the very early days of quantum mechanics. According to classical electrodynamics, the hydrogen atom should live fractions of a second. The electron emits radiation, spirals down into the nucleus. However, as far as we know, the hydrogen atom is pretty much been around since the early days of the universe or so. So classical electrodynamics is off by many orders of magnitude, but we are not surprised by that anymore. We know why, because the quantum mechanics of the hydrogen atom tells us that there's no quantum states in the theory that reproduces that behavior. It's not that there are perturbations around that classical behavior. That classical behavior is completely absent in the quantum theory. And I think it would be natural to assume that the singularities that are predicted by GR might be removed in the same way, not because there are large perturbations around those singularities, but because the quantum state representing anything close to them is just removed from the spectrum. Now, this might sound nice or not, depending on your taste. The problem is that classical gravity, I mean, the classical sector of the quantum theory that we have access to, is nonlinear, unlike classical electrodynamics, and nonlinearity is a big problem. Gravity is long range, that's common to classical electrodynamics. It's, however, also universal. Everything that exists and has energy gravitates. And every time we forget about this, we are in danger of making some mistake. Now, I don't want to spend more time on this slide. Let's go to a very simple, extremely simple description of, this sort of ideas, starting from the oldest model of gravitational collapse that we know of. Late 30s, the Oppenheimer-Schneider model of the gravitational collapse of a ball of dust. Dust means there's only gravity acting on our source. The surface of a ball of dust, spherically symmetric, we know very well would follow a geodesic in the outer Schwarzschild spacetime. This is the equation for the radial motion of the surface of our sphere. And solutions are known, everything is known very well. Now let's play this game. Like in quantum mechanics, we quantize the position of the electron, although nowadays we know that's wrong because the correct description would be given by quantum field theory. We should deal with fields. It's a lot more complicated, but quantum mechanics works pretty well in that regime. We naively quantize the position of the electron, which is an observable. That's very hard to define in quantum field theory. Let's play the same game here. Let's just take the radius of the ball as our observable and treat this equation in terms of a Hamiltonian constraint. After all, it's just a mass shell condition. You quantize it naively, and what you get is just, well, the Schrödinger equation, time independent. I don't care about the time evolution anymore. I only look at the time independent case. This is just, again, the Schrödinger equation for the hydrogen atom. Solutions are very well known because the potential is just Newtonian or Coulomb, if you wish. Now, the spectrum is known. We know it from our textbooks on quantum mechanics. In principle, it starts from principal quantum number n equal to 1. So if you see the bottom of the spectrum is extremely large and negative. This ratio is the mass of the object to the 4th power units of the Planck mass. It's huge. Correspondingly, the width of the ground state, n equal 1, would be a tiny fraction of the Planck length. This is practically the singularity. And this is what the Newtonian physics would predict if we look at this condition as the energy conservation in Newtonian physics. However, this calligraphic E, in this case, should be related to what you see written in red there. That's what general relativity tells us. That's the difference between general relativity and Newtonian physics, in a nutshell. That normal E quantity should be well defined, should be positive. It's a square, okay, it cannot be negative. This places a bound, a lower bound of the principal quantum number. The principal quantum number, to make sense of that Hamiltonian for the relativistic, general relativistic case, cannot be smaller than this expression you see here. The square of the mass of the ball in units of the Planck mass. which you might be familiar from other approaches. Comes again and again in many different cases. We'll see it in the next slide, another approach that sort of assumes or reproduces that behavior. This is the acceptable ground state now. You fix the mass, that's the ground state. Principal quantum numbers smaller than that are not acceptable. They don't belong to the spectrum. So the minimum value of the calligraphic E is minus m/2. The minimum width of the state is basically of the order of the gravitational radius. Now, don't take numerical coefficient too seriously. The model is so simple. I don't think it makes much sense to debate about those. But clearly, the difference between this expression and the naive Newtonian case, I don't think it can be fixed by any numerical coefficient that you plug in there to make things better. You can also notice the separation between energies. Let me call them energy. It's debatable whether it is energy or whatever it represents. Let's say the calligraphic E spectrum, the separation between states is given by this expression, which is extremely small compared to the Planck mass, whereas the regular E is separated or quantized in unit of the Planck mass, as you would naively expect in a quantum theory. Now, if you accept the fact that these are the quantum states you need to use to build any quantum state for your ball, including those representing a collapsing one, you come up, of course, with a bound on the possible values of the compactness. It cannot exceed 1 or something of order 1. The singularity is obviously not obtained in the quantum sense. Now, that said, there's not much else you can ask from this very simple description. We only have a wave function for the radius of the ball. Other question we might ask is that, for example, what's the probability that the radius of your ball is inside the horizon or outside? If it is inside, it's a black hole. If it is outside, it's not a black hole. So if you take this expression, the minimum width of your ground state to be half the size of the horizon, 95% your object is a black hole. A factor of 10 would make this probability exponentially larger, for example. Okay, this again doesn't allow us to ask many questions. The question we would like to ask, however, is, okay, what can we see outside this object? Because everything we see about black holes in space is related to motion of planets, other astrophysical objects orbiting the black hole. So in principle, what we need is the outer geometry, which is the tool. Metric is the tool we use to study motion of objects around that are gravitationally bound. By the way, a quick notation, the fact that the ground state satisfies this condition and its energy is very far from the minimum one we saw before, is a sort of classicalization in action, but I don't have time to discuss that. The other question I want to talk a little bit about is how can we recover the outer geometry? How can we reconstruct an effective outer geometry corresponding to this quantum description of the collapsing ball itself? Particularly, we are interested in the case when the ball is a black hole. So it is the ground state. Now, you may have noticed that this expression of the principal quantum number for the ground state is the same you need for the Bekenstein's area law. It's the same thing. It is also the scaling of the number of graviton you have in the corpuscular picture that was put forward by Valle and Gomez almost 10 years ago now. I will not have much to say about that particular model, but I will show you how to recover the same number interpreted as a number of gravitons in a sense, using this argument. We want to reproduce somehow the outer geometry, or reconstruct the outer geometry of our black hole starting from the fact that the potential that appears in the geodesic equation we have seen before is just the Newtonian potential. How can we reconstruct a Newtonian potential, is a classical thing, in a quantum theory? We can do so using coherent states. For example, let's start from a massless scalar field in, I would say, sort of fake Minkowski vacuum, Minkowski spacetime. Here, you don't have to think of the metric that defines this D'Alembertian operator as being the observed metric. It's you could actually take a Euclidean metric there. It doesn't matter much, although there is a good reason, I believe, to choose the Minkowski one. It's not the one we observe outside any configuration of interest to us. Let's put it that way. Sort of formal metric in this space-time arena in which things happen, and we use that arena to describe what happens. We are interested in a spherical symmetric system, so it makes sense to use spherical Bessel functions to, as normal modes, quantize the operator in the usual way, pose the usual commutation relation, A dagger, the usual creation and annihilation operators. A coherent state is then defined as an eigenstate of the annihilation operators, all of them. K is the radial quantum number, and these are the components, in a sense, the coefficient in this, the eigenvalues of this relation, and there are also arbitrary, there are phases there you can fix after. The expectation value of your scalar field on this coherent state is given in general by this expression, and we require that it reproduces a given potential of choice. And what you do is just notice that there must be no time dependence. This is static, so you choose the phases accordingly. And you find out that basically the eigenvalues in this expansion are related to the Fourier transform using the Bessel functions of your potential. Now you can rewrite the coherent state, this is well known, in this form, as the exponential of creation operator, the action of creation operators. The normalization factor contains a number called ng, which is the total occupation. You can interpret it as the total occupation number in your coherent state. Having defined the vacuum in the usual way, the vacuum corresponds to the fake or sort of fake Minkowski metric that appears in the D'Alembertian. This occupation number, I'm not sure you can interpret it as the number of quanta. For sure, it's a measure of how far the coherent state is from the vacuum. The larger ng, the farther you are away from the vacuum. Another quantity you can compute the expectation value of the radial momentum. We'll see what you can do with it. Now, for the particular case of the gravitational potential we have to deal with, it looks like Newtonian, it is Newtonian in a sense. This is what you obtain. Total occupation number is a divergent integral. You have to cure this integral because it diverges both in the infrared, but that's not important. You just assuming your system is infinitely extended. It doesn't make any sense. Any source is a finite lifetime. Newtonian potential can only reach up to a finite distance. So this is irrelevant. You can actually show that modes with very small radial momentum do not contribute to the shape of the potential very much. So that's let's say, a nuisance. What's important is the ultraviolet divergence, because this is related to the fact that the radial coordinate, you're letting it go to 0, but we can't, because our object that sits in the middle and generates this potential has a certain size. And therefore, we can just simply introduce this fact by placing a cutoff there. If you add a different source like a Gaussian, the integral would not be divergent. It's all standard stuff. So apart from this logarithm related to these cutoffs, what you get here is the scaling that we saw before, the square of the mass of the object in units of the Planck mass. This is universal. It always appears whatever your source is, even if the source is not a black hole, far from it. The expectation value of the radial momentum, unlike the number, total occupation number, only diverges in the ultraviolet, you place the same cutoff for consistency, the same infrared cutoff, and this is what you get. Again, this is generic. Now, if you want to describe a black hole, you can use the previous information and takes this cutoff here equal to what we obtained before, the typical width of the ground state, order of the gravitational radius of the object times factor of 2. If you place that cutoff there, what you get is that your coherent state will not reproduce exactly the Newtonian potential, but it approximated very well in the region outside the source. Let me give you an example here. This is when I take exactly the cutoff equal to half the gravitational radius, and you see the dotted line is the Newtonian potential, or the potential advantage in the geodesic equation, to be more precise. Solid line is the quantum corrected, let me call it like that, quantum corrected effective potential. This is where the horizon sits. This is where the source radius, a typical width of the source, it's a quantum source, sits. There's no singularity, the potential is perfectly regular. And you recover modulo numerical coefficient, the corpuscular scaling relations. The total occupation number, you can interpret in a sense as the number of gravitons with respect to the vacuum, the distance of your potential from the vacuum, proportional to the square of the mass of the ball. Typical wavelength that appears inside this potential as a coherent state, same quantity, scales like the mass of the object, which is a black hole in this case. A simple way to recover those corpuscular relations. The actual shape of the quantum corrected potential is highly affected by the specific value of this cutoff. If you decrease it by a factor of 10, the oscillations outside the horizon decrease in size quite significantly. So, if the quantum width of your black hole inside the horizon is small enough, eventually you'll not see anything outside. The effective metric, you can reconstruct it from that potential. It's a Schwarzschild with the quantum corrected potential replacing the usual Newtonian expression. So if the quantum width of the ball that formed the black hole becomes small enough, you won't see much outside. Is it that a good thing or a bad thing? Well, that's open to debate and potentially phenomenological observation. So I think this is pretty much everything I wanted to say. I'll leave you with the last slide. I hope I gave you a very simple, maybe because of that simplicity, convincing argument that we should treat black holes as quantum macroscopic objects and not as, the usual fully geometric classical picture. We don't do that for the hydrogen atom, so why should we do that for a black hole? That the problem of the singularity is not there. The singularity is not resolved in the sense that the system does not contain the wavelengths that we need to see it, basically. It's impossible. And whether we can use black holes to test quantum gravity, meaning whether there is phenomenological implications outside these objects that we can use to probe quantum gravity, that's of course open to debate. It's a matter of refining such a description, which I'm not sure is even possible. Anyway, this is pretty much everything I wanted to say. So thank you very much.
Thank you, Roberto, for your very interesting talk. We have time for several questions. So yeah, I see a question from Sugato.
Hello, Roberto.
Hello.
Hi. Extremely nice talk, right? So I completely agree with the spirit, right?
Thank you.
Yeah.
I suspect so, considering your papers. But
right. So what was very interesting. So what I didn't understand very well is how you managed to get these oscillations. So where are the oscillations?
Oh, okay. The simple. I didn't write down the exact expression. If you place that cutoff in your integral, you can actually compute exactly this expectation value. It turns out that, yeah, I forgot to put it there. You can find it in the paper. It's basically the Newtonian potential modulated by 1 plus the sine integral of the ratio between the radial coordinate and your cutoff. So that's why basically you are just removing modes from the Fourier transform. So obviously you get oscillations around your potential. That's a fairly generic thing. Whether they are observable or not is the real question.
I mean, is this in any way relatable to what people call like hairs of black holes, or not? It's not really the same.
I don't think so. What people call air of black holes, they have in mind the classical picture of black hole physics. And no, I don't. I would not say so.
Okay.
Whether you can redescribe everything in terms of a background and those are small part, yes, in principle you can, but I'm not sure it works.
Okay. Thank you very much. Yeah, very nice work. Yeah.
Thank you, Roberto. Let me see if there is any other question from the audience. Okay, there is a question by Alessia.
Alessia.
Hi, Roberto.
Hey.
Very nice talk.
Thank you.
I have a couple of questions / comments. So first, you say that black holes could be seen as macroscopic quantum objects and the ground state of the theory, but does this come from derivation or some minimization of an action, or
no, not really. I wish I could do that. You see, what this simple calculation here shows is that the minimum, apparently, the minimum allowed energy of your system, whatever, I mean, this calligraphic E, is it an energy? That's different. Anyway, it's very far from the absolute minimum value, which you get from here. Or conversely, this number is very large compared to the 0 you expect in the vacuum. So whatever this object is, and this is a simple description of it, it's very far from what we call the vacuum. Vacuum, if you wish, is what people refer to as the state that is diffeomorphism invariant or has a maximum number of symmetries. That's the one we play usually in quantum field theory. Now, the fact that the quantum state of this object is so far from that state in a non-linear theory, you see the problem. Makes it very difficult to connect the two, I think. So I wish I could give a more refined argument, but you know, the Schwarzschild metric extremizes the Einstein-Hilbert action. Of course, you should be able to do that. But it's a ground state very far from what we normally consider as the vacuum. And it couldn't be otherwise because there's a lot of matter there.
But at the moment it enters the computation as an assumption, right?
The moment what enters what?
The fact that you can see black holes are as ground states. So there was this statement that in the conclusion.
This is what you can see from this simple calculation. It looks like it is the ground. The black hole is the object that has maximum probability of being inside the horizon. I would call that a black hole. And of course, it's the ground state in this spectrum.
Okay.
I don't know if it's clear enough for you.
Yeah, maybe I will ask you later.
Okay, sure.
And one more comment. So when you show it if there is time, of course.
Yes, sure.
Okay. In the second to last slide, you have shown that potential.
This one, yes.
No, so the next slide.
Next one, yeah.
Yes. So you have this potential with oscillation, and
yes.
so this is somehow interesting to me because I'm not sure if you are aware of this, but it seems like when you add higher derivative corrections to the action. This is exactly what happens to the Newtonian potential, that gets some
I'm not
corrections.
surprised, yes.
Yes, and it starts oscillating. So maybe you are kind of simulating the.
Well, you know, very, very possible. The effective field theory approach should give similar description, provided in that approach you're smart enough to pick up the right background. You know, what I find it difficult to conceive is how can we pick up the correct background from the effective field theory approach, which assumes a background. And I don't know if I've made myself clear enough. The way I look at things here is that the ground state must be, of course, a solution of your quantum theory that minimizes, if you wish, something. It's a non-trivial, to describe a realistic object, is non-trivial state very far from the vacuum. If you now consider this ground state as your background for the usual background field theory method, then you should be able to recover something similar to that. That we have.
I don't think that you have to assume a background. So you have an action, and you.
Yeah,
just
well, what I'm saying, yes, you have an action, and most of the time you can't find the solution.
Yes, I'm saying that
okay, yes.
If you approximate your action.
Yeah, that's the problem. How you do the approximation could give you different answers, or could show you different aspects of the same problem.
Mm-hmm.
So
yes,
I agree.
with
It's very possible that the non-localities that people play with point to the same direction. Actually, I would be happy on one end and not surprised on the other end, because if the underlying structure we're studying is the same, they should point to the same direction.
Mm-hmm.
I'm strong
yes,
supporter of the idea that different approaches are complementary in general.
Yeah, I agree. And one more small question. So you say that this potential corresponds to a solution that is regular, but you mean?
Well, in a sense, it is regular, but really, if the object is fully quantum inside, what does it mean it's regular? I mean, what is the space-time inside the object? You have to reconstruct all observables from the point of view, the metric that we use to compute trajectories and compare with observation, that's an observable. It's not a formal thing. Observable in the real sense, also in the mathematical quantum field theory.
What is your observable in this case?
So exactly, you have to reconstruct it from inside an object that is fully quantum, like the hydrogen atom. What are the observables in there? True observables. We use the position of the electron, but that's not.
Yeah, I agree.
So in principle, yes, I could define a metric in there, but that doesn't mean that that quantity needs to have values that are semi-classical or close to semi-classical. They don't mean anything.
Yes, I agree. My question was just if you assume that you can describe that object with an effective metric. With
well, that would be the metric then. That what you see there would be the metric, but I wouldn't bet my life that it is.
Okay,
it seems to become a stretch.
Would it be an integrable singularity, or you think that?
I'm sorry to stop this very interesting discussion. Maybe we can postpone
continue later. Sure.
Okay, thank you, Alessia. So, God, I'm sorry. We can postpone to the discussion session. Is it okay for you? Okay.
Absolutely.
Thank you again, Roberto, for your talk. And let's move to the last speaker of this session, who is Pasquale Bosso. And he will talk about the position in models of quantum mechanics with a minimal length.
Okay, let me share my slides.
As usual, Pasquale, you have 30 minutes plus 5.
Sure. Full screen. There it is. Okay, so thank you everyone for being here, and thanks to the organizers for inviting me. So as the title says, I would like to talk about some aspects related to position in models with a minimal length. So first of all, why do we need a minimal length? And why do we include a minimal length in quantum mechanics? Well, we had talks here dealing with this topic, but one way that I like to introduce it is via a scattering experiment. So the scattering experiments usually also explain why you need the Heisenberg principle, or actually the meaning of the Heisenberg principle in quantum mechanics. So imagine that you have a target. It's a fuzzy target, and you want to study the details of this target, and you start shooting particles at it. Okay, we know that, of course, if you increase the energy of the bullet, you will improve the resolution of your scattering experiment. However, if you keep increasing the energy, as actually one of the previous speakers, Scardigli, showed, is that in principle, you will get so large energies in a so small volume that it will start making black holes. And black holes hide details rather than revealing new details. So in principle, if you keep increasing the energy, black holes, the radius of the black hole will actually increase, and you will start hiding more and more details. So it looks like we have basically two regimes. So if you start from very low energies and you start increasing the energy, you increase the resolution for your scattering experiment, meaning that you reduce the uncertainty in position on your target. And this is compatible with the Heisenberg principle. This is the Heisenberg principle. When you reach basically the Planck energy and you go beyond the Planck energy, what happens is actually the reverse. If you keep increasing the energy, you increase the uncertainty in position. You make larger and larger black holes that will reduce your resolution. Okay. So this is evidently something that doesn't work with the Heisenberg principle. And in this sense, you need to modify the Heisenberg principle somehow to include these new effects. So there are various ways to do that. One way is basically relying on the Robertson-Schrödinger relation. So we know from any course of quantum mechanics that if you have two observables and these two observables don't commute, you have an uncertainty relation between these two observables. Take position and momentum, for example. If A and B are respectively position and momentum, the commutator is IH bar, the Robertson-Schrödinger relation will give you the Heisenberg principle. So if we need to change the Heisenberg principle, including some modification due to these high energy effects, one possible strategy is to change the commutator between the position and momentum operators. For example, one operator that has been studied is of this form. Okay, so where you have a second degree polynomial on the right hand side multiplying H bar. If you plug this commutator into the Robertson-Schrödinger relation, you get an uncertainty relation of this form. And this was studied, for example, by Kempf, Munger, and mine in 1995, so 26 years ago. And this plot actually clarifies what is happening here. So also, Scardigli already showed this plot, but it's always interesting to see it. So the black line would be the Heisenberg principle, so where you have the usual hyperbola. The red line is the uncertainty relation that you will get out of this modified commutator. And as you see, you have a minimum for the uncertainty in position. Of course, we live above those curves, okay? So this is quite interesting. And of course, the minimum value for the uncertainty in position depends on this deformation parameter here. Okay, so what can we do with this? So first of all, there are a bunch of problems that we need to address. So in this case, I'm going to consider a generic modification function f, which is a function of the momentum only. It's a well-behaving function, and it's differentiable, integrable, and all these things. And just to fix a particular model, I will consider a second-degree model which contains a linear and a quadratic term. The reason why I want to consider a linear term is because there are some particular ingredient effects that come from the linear term, which are interesting. So what are the problems here? Well, first of all, how do the operators look like? In particular, how does the position operator looks like in non-relativistic quantum mechanics, at least? Okay. Also, since we are considering a model which contains a minimal uncertainty in position, we cannot include position eigenstates in our model. Or actually, position eigenstates become unphysical. And the obvious reason is that if you have position eigenstates, the minimal uncertainty would be 0, meaning the uncertainty on the position eigenstates, and therefore you will not have any minimal uncertainty in position. Also, if you don't have a position eigenstate, you don't have a positional representation. A positional representation is just projecting your quantum states on a set of position eigenstates. So we have these problems. So how can we address these problems first? Well, first of all, let's start from the last one. We don't have a positional representation, but since we are still claiming that momentum behaves as usual, in particular, we don't have any minimal uncertainty in momentum, we can still use the momentum representation. And in a momentum representation, momentum operator is just a multiplicative operator. So on that side, we are good. What about the position operator? Well, let's use the commutator at this point. Okay, so if we use the commutator and we know the momentum operator, we can get the position operator up to a factor ordering, although this factor ordering doesn't affect the physics of our problem. Finally, it's true that we don't have a position eigenstate. However, we can still define a new class of states, and this was actually the strategy of Kempf, Munger, and Mann in their paper. We can still define a new set of states which have the smallest uncertainty possible in position. Okay. These states are usually called maximally localized states. For a generic F, they have this form, the first line that you see here. So it's basically a complex exponential times a function chi here. There is some sort of relative of a Gaussian function. And you can see this, for example, if you put F equal to 1, this is basically a Gaussian. Okay. This P naught here that you see here, so it's a function of the momentum P, which is defined in this way. So it's basically an integral of 1 over F. And of course, if F is equal to 1, you get the same thing. So P naught and P are basically the same thing. Also, the expectation value of P and the uncertainty of P, they are treated as parameters that you tweak so that this function here has the smallest uncertainty in position. And the subscript just is here just to tell you that this function has expectation value, this quantity here. Okay. For the model that I was showing you, so that second degree model, the parameters that you need to use are this one. So in this sense, delta and epsilon, they have a particular meaning in the sense that delta represents the expectation value of momentum for a maximally localized state, and epsilon represents the uncertainty in momentum for a maximally localized state. Okay, so we have this new set of states. So we can try to use these states to create a new representation. In the sense, we can try to project our quantum state on these maximally localized states. In doing so, we basically make a new transform, which sort of generalizes the Fourier transform from, for example, from the momentum space to the space of these maximally localized states, which in the literature there, it's usually referred to as the quasi-position space. I will use psi as the variable for this quasi-position space. So the transform from momentum to quasi-position space is of this form. The inverse transform, and you can actually prove that they are one, the inverse of the other, is of this form. So the transform from the quasi-position space to momentum space is of this form. And at this point, you can also use these transforms to calculate, for example, the scalar product of two functions in quasi-position space. So you have two functions in quasi-position space. You want to calculate the scalar product. There is a problem if you try to approach these calculations from the perspective of quasi-position space. The problem is that the maximally localized states are not orthonormal, so they form an overcomplete set. And so the strategy that you can use is to transform them in momentum space and take the scalar product there. However, the funny thing is that you can still kind of define a sort of probability density in quasi-position space. So here I give you just three equivalent expressions of those things. So this is what I was talking about. So you take your state, you transform them in momentum space, and you take the scalar product. However, you can still define a sort of probability density, meaning this object that you see here, or equivalently this object that you see here. And you can also see that it's a real quantity in the sense that they are one, the complex conjugate of the other. And it also reduces to the usual probability density of quantum mechanics, so the squared modulus of your wave function. So this is for the probability density and for the transform from momentum and the quasi-position space. But at this point, we can use this transform to study some particular state. For example, momentum eigenstates. Momentum eigenstates, free particles. Okay, so in momentum space, well, that's easy. It's a Dirac delta. P tilde here is just the momentum eigenvalue. If you transform it to quasi-position space, you have still a plane wave. However, your wave number is not P tilde over H bar as it would be in normal quantum mechanics, but is P naught over H bar. And P naught was that weird function of the momentum, right? So it was something like this. So this just represents a modification of the de Broglie relation. So the Broglie relation in normal quantum mechanics is P equal to H bar K. In this case, we have P naught equal to H bar K, okay? Also, here we have a bunch of interesting things. So depending on the shape of F, you may have interesting features. For example, if F is an even function, so for example, the model introduced by Kempf, Munger, and Mann was a second-degree polynomial, which was, and F in that case was an even function. So if F is an even function, P naught as a function of P is an odd function, and everything looks fine. However, if F is not an even function, P naught is not an odd function, and at that point you may have some problems in the sense that for right moving wave you may have some a particular wave number. For left moving wave you may have a different wave number. For example, for the model that I was showing you, this is the relation that you would get between P naught and P, and this is what it would look like. Okay, so the orange line here is a model which doesn't contain the linear term, and therefore the F is an even function. The blue line is a model which does contain the linear term, and the F is not an even function. And then you see the difference. Okay, so the orange line is symmetric. So this is P naught on the X and P on the Y. So the orange is symmetric, the blue is not. And this also means that given any value of P, the wave number for left moving and right moving waves is different. Okay. Also, the dashed vertical lines, if they are just here to signal the fact that although P can range from -infinity to +infinity, P naught is bounded. Okay, so P naught has a minimum and a maximum value. Okay, if your F is positive defined. If F is not positive defined, for example, if it can become 0, the story is a little bit different. But for now, let's stick with a positive defined F. Okay, so this is for the free particle. So what about the operators? So at the beginning, I said that studying the operators was one of the problems, and we kind of avoid the problem studying the operators in momentum space. In particular, we saw that the position operator was of this form up to factor ordering, or if you want to use the P0 quantity that I was introducing, it has this shape here. In quasi-position space, though, what happens is that P0 is a derivative with respect to the variable, the quasi-position variable. The momentum operator, to define the momentum operator, you can use the relation that you have between P and P0. However, the interesting thing happens for the position operator. So the position operator, if you look at it, contains a multiplicative term and a derivative term. So the derivative term would be included, of course, in the momentum operator appearing here. And if you focus on the multiplicative term, it multiplies by a complex number. Okay, so this is basically telling you that considering a sort of position representation with a minimal length and considering a position operator, a multiplicative position operator, leads to something quite weird. So your position operator in that case would not be symmetric, would not be Hermitian. So it will actually, the expectation value will actually give you complex numbers. So there is something weird happening. Okay? And the reason is that if you just consider a multiplicative position operator, you are forgetting the derivative part. Okay, so this kind of fixes what is happening here. So let's see what happens in some particular case. So let's see, for example, what happens to the case of a particle in a box. Why choosing particle in a box? Because in that case, you have to work with the quasi-position space. You cannot work with the momentum space, or at least it is not easy in that case. Okay. So particle in a box, easy exercise of a first course in quantum mechanics. So you have a quantization rule in that case. And the quantization condition that you have is that the wave number is proportional to the inverse width of your box. L here is the width of the box. N is an integer which ranges from 1 to infinity. And if you increase n, of course, you will get larger and larger wave numbers, which means smaller and smaller wavelength for your wave in the box. And since n can go up to infinity, you can consider any size for your wavelength, meaning that you can put any number of waves in your box. So regardless of the width of your box, you can put any wave you like. The size, so the size of the wavelength for your wave function can be anything. With GP, the situation is a little bit different. First, you need to account for left and right moving waves in general. However, the quantization condition is kind of similar. You just need to remember that you have left and moving waves, which are different. However, since P0 is bounded, also K is bounded. And since K is bounded, N is bounded. So the integer N is bounded. So you have a maximum number N, which is related with the width of your box. And this also means that you may have boxes which are so narrow that don't allow any wave function in there. Okay, so for example, so there may be values of L such that the n max is more than 1. In that case, basically, you cannot fit any wave in the box. So in that sense, the model with a minimal length that I'm showing here is basically telling you that you may have empty boxes, so necessarily empty boxes. And this is what would happen, for example, for the spectrum of a particle in a box. So the green line is the usual standard quantum mechanics result. Notice that the y-axis is on a logarithmic scale. The blue and orange line so they have the same meaning. So the orange line is quadratic model, blue line contains a linear term. The vertical lines, again, they signal the fact that you have a maximum n, a maximum quantum number. Okay, and so basically you cannot have more than this many waves in the box. Now, in this case, just to put some numbers in, I was considering a box which is 1 meter wide, and that's the reason why you have these huge numbers here. But the point here is that in any case, you have a finite number of waves which can be, put in the box. Another interesting system that may be worth to analyze is the potential barrier. Again, why the potential barrier? Because it's easy, because it's the appropriate system to be studied in a position representation or quasi-position representation in this case. In particular, one thing that you can study is the transmission coefficient, and specifically the resonance of the transmission coefficient, meaning that if you have a transmitted wave, you will have energies, particular values of the energies corresponding to which your transmission coefficient is 1. And in the normal quantum mechanics, the energies at which you have resonances, they are related with this relation. Okay, so you have the wave number in the region of the barrier, which is given by this relation. So again, it's proportional to the inverse width of the barrier, and n is an integer that can range from 1 to infinity, meaning that you will always have an infinite number of resonances. So for an infinite set of energy, discrete, of course, set of energies. And this also means that regardless of the width of your barrier, you will always have resonances. With GP, again, the story is different because, again, you have to account for left and right moving waves, although, again, the condition is similar. Again, also in this case, K is bounded, therefore N is bounded. So you will have a finite number of energies which correspond to resonances. And again, you may have values for the width of your barrier which don't admit any resonance. So you will have barriers which don't present any resonance at all. Okay. So this is basically, for example, this is what would happen if you have a box, a barrier of the order of 40 Planck length. Okay. So you see that again, green line is the standard case, blue line has a linear term, orange line doesn't have the linear term. Now you see that, of course, the shape is different, but you can also see, for example, that the peaks are shifted, meaning the resonance is shifted, and also the number of resonances is different. The interesting case, so on the x-axis, you have just the ratio between the energy of the incoming wave and the height of your barrier. The interesting thing happens when the width of your barrier is smaller than the minimum value to have resonances. So you will have a situation like this. Look in particular at the blue line. The blue line, even when the energy of your incoming wave is smaller than the height of your barrier, the transmission coefficient is of the order of 1. Meaning that basically the wave is not seeing the barrier at all. Okay, and this actually makes sense from the point of view of a minimal uncertainty in position. If the width of the barrier is smaller than the minimal uncertainty in position that you have in your model, your wave doesn't see it. So it's basically the same thing that happens in optics, right? So the difference between ray optics and geometric optics and wave optics, basically, right? So if the imperfection of a surface is of the order of the wavelength of your light, then you have to use wave optics. But if the imperfections are smaller than wavelength, you can use geometric optics. And this is exactly what happens here. Okay. So basically, if the width of the barrier, if the height of the barrier, if the width of the barrier is smaller than the minimal uncertainty, basically the incoming wave doesn't see the barrier at all. So you will have sort of phantom barriers. barriers which don't affect your waves.
5 minutes, Pasquale, 5 minutes.
Thanks. Yeah, I was actually going to conclude. So actually, just to summarize here, so we have seen GUP in terms of phenomenological approaches to models with a minimal length. So why we need it, basically. And again, I would like to emphasize that this is just one of the possible approaches which relies on unmodified commutator. And we saw that, okay, since we don't have, since we have a minimal uncertainty in position, means that this means that we don't have position eigenstates, which means that we don't have a positional representation, which means that the position operator is not multiplicative. Also, we saw that the de Broglie relation is modified, right? So the relation between the momentum P of the particle and the wave number is no longer linear, but it goes through that P naught that I showed you. And also we saw, well, two particular cases, in particular the particle in a box and potential barrier. And we saw that you may even have situations in which boxes have to be empty, in the sense that no wave functions can fit in the box, or phantom barriers, in the sense that you may have situations in which your incoming wave doesn't see the barrier at all. And I will stop here. Thank you.
Thank you, Pasquale, for your very nice talk. We have time for some questions. Okay, there is a question by Fedele.
Yes, it is actually a fairly straight question. I didn't, probably you said it, I didn't catch, but this X self-adjoint operator, if it should be, otherwise wouldn't be observable. If it is your localized functions, which connection do they have with the spectrum, the eigenfunctions proper or improper of this self-adjoint operator?
So yeah, basically, I suppose you refer to this operator.
Q, I mean Q.
Yeah, they are actually symmetric operator, and actually this is the reason why you have the F here.
Symmetric or self-adjoint?
They are, well, they are symmetric in the sense that they are not bounded, right? So as in quantum mechanics.
Yeah, but they can be, or they can be self-adjoint or not. If they are self-adjoint, they'll have a complete set of observables and I can do a spectral decomposition. If they are not self-adjoint, then they are not observables. So if they are self-adjoint, they will have a set of observables, or a complete set of eigenfunctions. They like Q, the ordinary Q is self-adjoint, and the eigenfunctions are the delta. So the self-adjointness is fundamental in this.
It's self-adjoint in the sense that, of course, if you take the so you can move this Q on the left, on the right of your
yes, but is the domain of the operator equal to the domain of the adjoint? And I'm not sure it is. I would have to. I cannot see it. If you didn't consider, then but it's an important point. It's a mix of domains. It's like momentum in the box. Momentum
it is
symmetric, but it's not self-adjoint.
It is, and it was actually showed in this paper here. So it's basically the same operator. So that's the thing.
Okay. Thank you.
No problem.
Okay, thank you, Fedele. Let me see if there is any other question from the audience. Maybe some comments. I don't see any question. Okay, there is a question. Okay, there is a question by Fabian.
Can you hear me already?
Yeah.
Okay. So wait, let me. I was just thinking. I mean, we usually. You can see me as well. We usually, we apply the generalized uncertainty principle with, having this parameter. I don't know. We call it alpha or whatever. Free, and try to constrain it with observations. Now, as we're using usual quantum mechanical problems, which are, of course, not applicable really to high energy scenarios, yeah, until now, and I mean, it's already been some time, all the estimates on these parameters have always been poor, basically, because we assume this length to be basically the Planck length, and then, we're like 20 to 30 orders of magnitude above, kind of. Do you expect anything of this to change? Because I think we would need to get this into quantum field theory, right?
Yes. Yeah, that's a good question. So there are some estimates based on some experiment. I think the best estimate that we have for the quadratic term, so basically for this gamma, well, at least the dimensionless version of this gamma is of the order of, so it's an upper bound as usual, and it's of the order of 10 to 6, I think, or something like that. There are proposals for other experiments, for example, in quantum optomechanics and all these things, which are promising, although there are still details to be studied and fixed. But as you said, probably the best thing to do is to translate this thing in quantum field theory. There are approaches of the generalized uncertainty principle in quantum field theory, although they are tricky in the sense that they often present some problem in the sense of the problem here is how do you generalize a modified commutator in quantum field theory? That's the problem. So
yeah, because the field is not the same as the momentum operator.
Yeah, exactly.
That's true. I mean, I think that's the most important question. I was always imagining that something like the anomalous magnetic moment of the electron would be interesting, because there we have such a high precision in our measurements, right? But I've not really seen much about that anyway.
Yeah, no, that's because it's a quite complicated problem, and as I said, so it's related with the fact that how you translate this stuff in quantum field theory. But yeah.
Yeah, thank you.
Thank you, Fabian. Maybe we have time for one more question for Pasquale. Yeah, I don't see any other question, but maybe I have a small curiosity. If I understand, you are working in one special dimension, right? So do you have any idea of what happens if you generalize your formulas to 3 dimensions?
So yeah, if you generalize to more dimensions, what you would expect, and actually what you would have, is that you also have non-commutative between coordinates. And this, of course, creates a much higher complication for your model. And again, this actually can be seen kind of heuristically, kind of phenomenologically, using the scattering experiment that I was telling you, right? So if you consider so the Heisenberg principle relates the momentum in one direction and the uncertainty in position in the same direction, right? But if you start forming black holes, then you start messing with the uncertainty also in all the other directions. So it's like the uncertainty in momentum in one direction will mess with the uncertainty in position in all other directions. So this kinds of tells you that you will have to involve all directions. So in that sense, the commutator, for example, cannot relate only position and momentum along the same direction, but also along the other axis, basically. And of course, as I said, this will complicate the situation, and this will actually create more structure, definitely, on your problem. But this is definitely a complicated problem.
Okay, thank you. So if there are no more questions for Pasquale, maybe we can start. Oh, just a moment. Okay, maybe, well, we can have a very small break and then we can start the discussion session, or maybe we can start directly the discussion session. I don't know if you are still.
Yes, we can start right now. Probably we can enlarge if there is the possibility.
Okay, okay. So there were, perfect. So there were some pending questions. First one is by Luca Smaldone, and it was to Fabio Scardigli. Luca, are you there?
Yes. Yes.
Okay.
Oh, I want to do a comment actually to Fabio, to you, Luciano, and so on, to all the authors about the. I was thinking about the alpha that you don't fix, and I think the reason for which you don't fix is that you need some new argument, and the possible new argument actually was given by Maggiore in one paper. Is a PRL of some years ago. I don't remember precisely. And because he talked more in general of Bekenstein bound in a form like S minor or equal of alpha R times he. So not fixing the above parameter. And he tried to deduce such parameter from consideration related to study of quasi-normal modes of black holes. And in particular, it starts from the consideration that such alpha is related to the ratio between an fundamental element of area of black hole horizon and Planck length square. So you have, you imagine the horizon divided in n element of area. Okay, and each element of area measure is alpha times the square of Planck length, and this alpha should be the one which is present in the Bekenstein bound. This is the work by Maggiore, and he fixed it to 8 pi, yes, in like in original Bekenstein, or 2 pi. I don't remember now. There's some factor. But when in a previous paper, PRL by Hod, that fact, this ratio was fixed to 4 times log 3, or more general in 4 times log k, for example. And in a recent paper by me, Alfredo, and Giovanni Acquaviva, we fixed it to 4 times log 2 in particular. So always in the odd form of 4 times log k. But probably I was thinking the reason for which you don't manage to fix that parameter from your derivation is because you need this extra information about quantization of area, probably. That was my comment, actually.
Yeah, it's a very interesting comment. Thanks for this comment, and I want to see that paper of Maggiore.
I can send you. I can send
you. The alpha. I think this alpha is also related with the Hawking temperature, and that alpha is fixed by the exact calculation, quantum field theoretic calculation of Hawking, essentially. The famous 8 pi at the denominator, the formula. So
I think it depends on the model. I told you there is a paper of Hod, for example, always a PRL, before the paper of Maggiore, where he tried to fix and they found 4 times log k for an integer k, for example. And Hod proposed 4 times log 3. So it's not so easily fixed, I think. The argument of Maggiore was based on the study of quasi-normal modes of black holes.
Yeah.
I can send you anyway.
Yeah, sure. Thanks.
Okay, thank you, Luca. We had another question by Sugato, but I don't see Sugato in the list of speakers. I don't know if he's still there, but I think no. Okay, so well, in the meanwhile, I have a curiosity for all the speakers, but mainly for Fabio and Pasquale, but for Roberto as well, who worked in the past on this kind of deformation of the uncertainty relation. My curiosity, my comment is, You know, in the last year, there is a series of deformation of uncertainty relation which is appearing in the literature. Sorry. We have deformation with a maximal length or a minimum length, with a maximal uncertainty of position or a minimal uncertainty in position, quadratic, exponential, linear, and so on, whatever you want. So my question is, we don't have any experimental way to test so far this uncertainty relation. So that's the reason why I think we have all this plethora of uncertainty relation. But do you think we can say theoretically, at least to say, okay, maybe this is the right way to follow, or this is not the right way to follow?
Well, I think at this stage, from pure theory, I don't think you can. Obviously, you can always think to this 1 plus p squared, the deformation, as the first two terms of a series. There were people considering the deformation like an exponential, right?
Sure.
If you consider the exponential of p squared, the first two terms is just 1 plus p squared. So I don't know how much far you can go. You can constrain from the theoretical point of view this kind of topics, this kind of argument.
Yeah, I actually agree in the sense that, so as you were saying, so the models that you see are either polynomials which suggest a sort of expansion, or some particular function such as exponential or Gaussian or sometimes, or something like that. But yeah, those are usually put there for some reasons, but those reasons are not very compelling most of the time. So.
I don't know if maybe Roberto wants to add something else. So.
Well, what I can add is probably rather trivial. Quantum mechanics is an approximation of quantum field theory as far as we know. So I think it's hard to decide from an approximation what's the right way to go. On the other hand, it's not a simple approximation. Basically, you can assign a position to a particle only in the one particle sector of the theory, of the quantum field theory. As soon as you have more than one particle, they collide and then start. The number of particles is not conserved. It doesn't make sense to assign a position to what particle, right? And in principle, we are looking at the formation of the uncertainty relation in a regime. Well, it depends on the regime you want to consider. If you are too close to the region of strong field according to gravity, you expect huge departure from this simple description right there. So I don't know. I always look at the generalized uncertainty principle not as fundamental, but sort of effective, useful. They can be derived in some other ways. I think Fabio and I had a paper a long time ago about this. But again, if we had agreed upon theory of quantum gravity, the question would be answered. Otherwise, it's a nice game to play.
Okay, thank you. Thank you, all the speakers. So let me see if we have another question. Okay, there is a question by Elias.
Hi. Okay, okay. Let me just elaborate after Roberto that what at least I expect is to have an experiment, for instance, of what kind of experiment you can have, like the group from Vienna, that they said that we are using vacuum optics, and they derive their result and say, how can I prove it? I mean, vacuum mechanics, they cannot, doesn't work. I think they did it in 2012, 2013, 2015. There were several experiments, and they were trying to explain their results. So I think this is the answer, which is the correct version. I mean, I don't know, but the experiment will tell us if you need an exponential in the GUP, or a minimum and a maximum length, or a maximum momentum, and so on. So I think that it makes sense to have several versions till the time that the experiment will tell you, this is I will falsify this and I will accept this. For the time being, it looks like a game. This is true, because you can have infinite series versions. Anyway, I would like to ask. I would like to ask Fabio, because for 2 points. First of all, for the negative beta, he said that there is no minimum length. Okay, he knows that my concern is if you go back, you have a quantity under the square root. Is there any argument how you fight this problem? Because in this case, your minimum length become imaginary.
Imaginary, yeah.
Yes, yes. So this is an issue that we have discussed, but I don't know if you can make more, if you can elaborate more on this, and also, what do you expect for your last sentence in your conclusions? You said that I am expecting something for the black hole information problem, or I mean, do you expect the GUP? It's phenomenology, but it will give you an answer for the formation. It is lost, or it leaks out of the black hole. Do you expect an answer like this? I mean, let me know your thought about the last conclusion.
About your second question, there is a famous paper that was written almost, I think, 20 years ago by Pizin Chen, Adler, and Santiago, and where they proposed black hole remnants as a kind of resolution of information paradox. And the remnants seems to be required for if you compute the evaporation of a black hole using a GUP, of course, with a positive beta, so with a minimum length and so on and so forth. I think that also recently, Pizin Chen wrote and collaborators, I think. Ong or some other guy, they wrote a physics report on this stuff of information paradox, and part of the report is information paradox and GUP, so to say. So about the first question that you posed, the negative beta. Yeah, negative beta, yeah, can have problems, of course, because in principle you can the right hand terms can become negative, which would be absurd, so to say. But at the same time, from the theoretical point of view, it's quite intriguing because it seems to fit with a completely different research line, like those of double special relativity, where also they have these h bar depending from the energy and becoming zero at the Planck energy, or the other scenario, the one proposed by Toft, with a deterministic classical world at the Planck scale. Also, this one is absolutely an intriguing perspective, so to say. I don't know, obviously, I don't know if it is true or how much is the degree of reliability of these possible avenues, but I think they are worth of being explored. Well, we are theorists, so you look in every direction you can. And this fact that the beta negative somehow agrees with these different, completely different frameworks is also, in my opinion, it's enough to consider it a topic of research, so to say. At least this is my opinion.
Okay, thank you. Rias, you have another question by Nick.
Yes, hi. I have to apologize due to teaching. I missed, although I know the works of Fabio. Since I was in the discussion, I want to make a comment in the comment that Elias Vaganas made, that we have to wait for experiment to interpret the various uncertainty principles. That's very difficult because the experiment requires understanding measurement theoretically, right? So if you have various scenario of quantum mechanics, as people do, and you don't apply quantum field theory, which I would, then the measurements may admit different interpretations, and I doubt that in some of their scenario of the interpretation of quantum mechanics, you could understand what the measurement is giving you. So my point is, and I would agree with Fabio here, that we should have a theoretical framework, an underlying one, string theory, for instance, which was the first to propose modified uncertainty principles at high energies, or field theory, what they are doing. And based on this scenario, then we can try to interpret the phenomena. Of course, the issue of measurement in quantum field theory probably doesn't exist, right? I mean, no, in the sense that nobody is discussing measurement in quantum field theory, because there is no action, everything is through finite speed of light. There is no collapse of any wave function in field theory. So that's my point. My point is that to interpret experiments on uncertainties, you have to be careful how you apply. You need the theory of measurement if you're doing quantum mechanics, and if you're doing quantum field theory, you need to understand how measurement is done in quantum field theory, or string theory, or quantum gravity. In fact, it could be like Penrose, that gravity itself acts as a measuring apparatus, inducing a collapse of the wave function, the quantum fluctuations of space-time themselves. So that's my general comment on this uncertainty, is that we need a theoretical framework. We cannot discuss them in a model independent way. It's impossible, in my opinion.
Okay, thank you, Nick, for your very interesting comment. I agree with you. Okay, so let me see if there is any other question. I don't see. Okay, there is a question by Thomas.
Can you hear me?
Yeah, perfect.
Yeah, in the context of all these questions which came up in the last few comments which came up, and how one could possibly learn more about the whole approach of connecting uncertainty principle or commutation relations with entropy bounds. Has anybody ever looked into entanglement entropy in condensed matter systems? Because this is intensely studied also from field theory point of view at low temperatures. One just would have to find a suitable probe, I mean, in the sense of quasi-particles, because they typically have modified dispersion relations, and then try to apply the whole reasoning which Fabio, for example, was presenting to such a system where there are experiments, there's theory, there's everything there. I mean, at least much more than in the context of gravity. So it's just a question because I have not followed that, and I'm not really sure, but I know that in that field, there's basically everything you would like to have in order to check the whole line of reasoning which you're presenting here. Thank you.
Thomas, you're asking if essentially you can go to some analog system and to probe to probe I guess the standard Bekenstein bound, that one I think you can. There are many papers on the derivation of the bound related to specific physical systems, starting from the papers of Gibbons and so on, 30 years ago, 40 years ago, or whatever. If you want to go to analog systems in order to probe GUP, that's another story. That's another. It's a very interesting story, but I don't know if still you have you can identify some analog system where you can have a deformed uncertainty relation. One of possibility, perhaps, we were trying to work on this with Alfredo and Gaetano Lambiase, is the graphene, which is, by the way, itself a lattice, and on a lattice you should have some deformation of the fundamental commutators. Well, this is what come to my mind now. I don't know other possibilities or ideas on the moment. Maybe, I don't know if someone else want to add something.
No, personally, this is a question that I was wondering some time ago, because of course you have this relationship between basically the Heisenberg principle and entropic principle, so entropic uncertainties. So one question would have been, so what you have, so if you can keep the same correspondence with GP as well, but yeah, I don't have an answer. So it definitely is an interesting question to me, at least.
Maybe we have another question by Luca.
In my mind, went just another curiosity. Is it your reasoning anyway related to the type of statistics that you use of the particles involved? Because I recently read some papers of 10 years ago where they studied entropy bound related to statistics of various particles, for example, for fermions, for bosons. And it was proved in that case that the natural bound that you get, for example, for fermions and boson, is similar to a holographic bound, but with factor which is with a to 3/4. That was originally derived by 't Hooft, actually, but it was proved then in this more recent paper in general for gas of boson and fermions. And moreover, it was proved that for particles following an infinite statistics, that was the one proposed by Strominger for extremal black holes, for example, 1995. It was proved something like an entropy holographic bound, so maximum entropy bounded by the area of a black hole apart from factor. And so I was asking if statistics plays any role in your derivation. So to Fabio and to co-authors.
Well, statistics, okay, we just used the plain thermodynamics. So if you want there, the statistics is just a Maxwell-Boltzmann, the usual one.
So maybe the fact that you have distinguishable, let's say, particles can play a role in a certain sense, because it depends. In the case of infinite statistics, that exactly was the point of Strominger, where you consider different black holes. You have to, at least for these extremal black holes, you have to consider as a distinguishable objects, essentially. So this could play a role in, I think, your derivation.
Definitely, but also from the very beginning, I guess, because at the beginning we start from a law of thermodynamics, which for different statistics can be modified. Now, I was thinking about Tsallis thermostatistics because this is something that I was recently looking at. But I mean, you can also think of other statistics, just like it's done in the paper that you're mentioning, and in principle, you get some differences, of course.
I see, and can suspects, and this could be interesting in the Fabio mentioned at the end the study of holographic bounds. So in connection with this works, I think that looking at differences of various statistics, I think can be interesting.
Yeah.
To reformulate and to reformulate the things in different statistics, you mean these?
Yes.
Yes, yes.
Okay, thank you, Luca. We have another question by Fabian.
Yeah, okay. I think this one is basically to all of you, because I've been thinking a bit more about this. How could you, in fact, try and put the generalized uncertainty principle into working in the context of quantum field theory? Now, there are, of course, some theories which kind of modify the evolution equations of the fields, right? And then I guess there are also some other approaches, but couldn't one also try to do something similar, not on the base of some, of course, try to modify the commutator of the fields, that's a different thing. But couldn't we also try and just, you know, start with the minimum length and start just with the correlation functions and then try to reconstruct the theory from there? Is there any, do you know any literature on that as an approach?
Can I say something?
Sure.
Yes.
I'm not sure you need to change the commutators in quantum field theory. That's the point. Because
yeah, I understand
again,
it the same way.
the generalized uncertainty principle applies, we usually apply it to position and momentum operators for particles. We know it's an approximate description. Now, if the quantum field theory is correct, and you know, you've heard probably about hypotheses like classicalization or all sort of interesting stuff that could happen in the ultraviolet regime. And here we are in the ultraviolet, we are modifying stuff near the Planck scale. I think the modified uncertainty relations for those operators should come out from the quantum field theory, even if we don't modify it. Probably, I'm not sure we know how to do that, because if it happens in nonlinear theories, and we don't know how to deal very well with nonlinear theories in quantum field theory. Most of what we do is perturbation around the background. But the background is really a quantum state per se. If you don't pick the correct quantum state, and most of the time you don't know how to do it, it's not clear to me. Again, I'm not sure you have to modify, coming back to your question. I don't think we have to modify anything in the quantum field theory side. And if we were able to derive a single particle description in some consistent way, the modification to the Heisenberg uncertainty principle should come out from the field theory description for free, in a sense. But that's mostly my gut feeling. The minimum lengths you find in many different ways, including what I showed today, but that's not particularly important.
Okay, thank you, Roberto. Let me see if there is still more question. Fabio, okay. Well, I don't see any other question. Guys, do you see any other question? Okay, so if there is no more question, let's thank the speaker again for their talks. And well, I think that we can stop the session here. We shall see within more or less 30 minutes. Next session will start at 5:13. So, okay, so we stop here and we shall see later. Thank you again for your participation and thanks to all the speakers.
Thank you.
Gaetano, dopo fai tu la registrazione per la prossima sessione.
Yeah. Ma quella di ieri me la devo dare io o devo condividerla a qualcuno?
Vabbè, per ora teniamola noi da parte, poi si vede.
Sì, sì, no, sta tutto su YouTube. quindi-
Esatto, per il momento c'è quella completa su YouTube.
Sì.
Tra l'altro la prima giornata aveva varie visualizzazioni e 54 like, e persino un dislike, non sappiamo perché. A qualcuno non piace la nostra conferenza.
Quindi dici che a breve potrebbe contattarci YouTube per sponsorizzarci.
Non siamo ancora così influenti, però.
Ma almeno una pubblicità dei salamini berretti.
Non dire niente, che qua siamo appunto su YouTube, non pronunciare
Ok,
commerciali che
Perché-
bannano il video.
Che ci
Ha detto
fanno?
i
Ma per quale
salamini,
motivo che abbiamo detto?
i salamini teretta, che si è sentito male.
Senti?
Ma
Non c'è-
marca indipendente,
Dite-
niente copyright, niente.
Sento. Pronto?
Ah.
Lots.
No.
Okay. Okay, guys. Do we have the next speaker still here or?
No, we miss Peter, I think.
Dove lo trovate Petr Jizba? Gliel'avete detto che c'ha la talk oggi, sì. Perché se no
Dovrebbe saperlo.
va a finire che non lo recuperate più.
Vabbè.
Qui facciamo un colpo e faccio un colpo di telefono, ma penso comparirà.
Credo lo sappia.
Prendiamo fra 10 minuti, giusto?
30.
Vabbè, alle
30 minuti ha detto.
25.
Non so perché ho pensato a 15.
Sì, no, beh, allora ci sta. Ah, è Peter il primo talk, tra l'altro.
Sì, esatto.
Per pensavo fosse il secondo, non so per quale motivo.
Se voi lo vedete. No,
non c'è ancora qui.
Comunque in questi giorni vi invio questi articoli che secondo me sono...
Anyway, guys, I don't know if you see, we had an email by Peter Cameron. Peter Cameron, you say, I very much enjoyed your workshop and particularly appreciated Vaclav geometric algebra presentation. There is much in the formalism I find confusing and difficult. This talk and this paper are helpful. Then he shares some links and he say, share with this participant you feel might have interest. Okay, maybe we can share somewhere sometime these links.
Very good. Fortunately, people is enjoying.
Okay. I'd like to invite also the advisory board to take part to this conference more actively.
What do you mean?
Maybe sometime they can switch on their camera or microphone. They can make some question or comments. Or
Okay.
Anyway, don't say anything compromising. We are
no, nothing.
Live on YouTube. You're live on YouTube.
Sure, I'm just saying that.
We decided to not stop the live.
Yeah, I mean, at this point, it's meaningless.
This is a transparent conference, so we have nothing to hide. It was just a kind of invitation to the advisory board.
Probably. Okay, there's Nicolaus who wants to say something.
Guys, I don't know Italian at all, but I know a little bit of French. I can understand many of the things that you are saying to each other. And I'm not very good with languages. It seems that the Italian language, nice and sonorous and everything, is not really very difficult. And so if you have people from Spain, from Portugal, from France, and so on, they can most definitely understand what the hell you are talking about.
Yeah. Well, you know, actually,
nothing compromising.
Yeah, precisely.
But I have to tell you that, as I said, I don't even know anything, but I can read, and sometimes if you speak slowly, I can sort of understand what you are saying.
Maybe we can switch to our idiomatic language, but in that case, probably also
you have to find another way to communicate with each other.
Yeah, no.
Okay, sorry, I didn't want to interfere, so I'm getting out.
Don't worry.
This is just a break, so everyone can say.
Can say almost anything.
It's really.
This is funny time.
Exactly.
No, it's a good thing that you did this. I mean, maybe next time if you run it again, you can invite some people like Astekar, right, to speak about loops, right? Not necessarily Astekar, but or Rafael Sorkin, who is now, I don't know exactly what he does.
We have last session 2 speakers, but we have Carlo Rovelli and Renate Loll about loops. So.
Oh, Renata is going to talk about loops because Renata does causal diametrical triangulations, right?
I think she mentioned loop. I don't know if we will talk exactly
I don't
about.
think Renata has.
Carlo Rovelli, which for sure will talk about loops.
Yeah, for sure.
Mention loop in the abstract. I don't know if how much.
Yeah. No, I don't say that I am a proponent of loops, but you may want, right? I mean, Steve Carlip, right, made a presentation, and William Monroe and stuff like that. So.
We try actually to give space to different approaches. So
right.
Invite everyone. Loops you have seen this morning. We have conformal gravity and strings, and
right.
We try to give space to everyone.
Right, of course, which is nearly impossible. You have also Jorge Zanelli, who is
yes. Guys, I leave for a moment.
Yeah.
Peter is not here, right? Not yet here.
Not here yet. Okay, probably.
And who is then? We have Fabian, right? And
yeah, Fabian and Tsallis, they're both here. I've seen it 5 minutes ago. Right. Yeah. But Petr is nowhere to be found. Probably, yeah, you can try and call him just to remind him that the conference is starting in 20 minutes. Okay, I'll try to see if
Vabbè, ci vediamo tra un po', eh? Io later.
Ok, Fabio.
his phone is not even ringing, so I guess we should try with an email.
It's over.
Yeah, I should try with an email, I guess. Yeah, no, Luca's right. It's still early anyway, but just, to inform him.
Are you here?
Who are you talking to? It depends.
To you.
Yes.
Organizers. Anyway, I rectified what I said. I was reading the Renate LOL abstract, and there's no mention to loop. I was just bad memory of of myself.
Okay. Anyway, I tried to type an email to Petr, still not here. So, I mean, if...
How much time?
Oh, well, it's 8 minutes, let's say, before the beginning. So, I don't know.
Luca, Biggs. Can you go to the Czech Technical University to see if that is there?
One moment, I take the tram and I come back. Okay, to get Brehova, I mean, I need half an hour from now almost. So we don't manage for maybe for the second tour.
If you increase your speed,
you can accelerate.
This was the yesterday session.
No, actually, Luca, we remember that you're quite good with accelerations.
LHC, the L stands for Luca.
H stands for hole, so Luca hole collider.
Luca hole is not best.
This is black hole.
No, not hole in the sense of hole in the sense of corridor.
No higher theorem. Luca shows no higher theorem.
This is the Hare theorem, not the no Hare theorem.
Yeah. So honestly, I have no idea how to keep in touch with Petr. I don't know if because okay, last time I heard him, he said that he was going to the university because probably the Wi-Fi was more stable there with respect to his.
This is another problem.
So I don't know if it's lost in the Czech Republic somewhere.
Some
or
connection pro. Some connection pro.
If no clue. Because it's impossible also to contact him. I don't know if you are afraid or some number.
Vaclav can say something more, no?
If I don't know.
I don't know if he's here.
So what's going on?
Oh no, we're saying
we don't find Peter.
And he's the first speaker. So actually, I guess that if it's still the case, we shall ask Fabian to go first.
Yes, at least we exchange.
Yeah.
Yesterday for
Still 5 minutes.
Yeah. That's 5 more minutes. Okay.
Petr Jizba.
Yeah. Okay, in the worst case, Fabian, are you ready?
Wait, did you ask me something? I didn't.
No, well, actually, don't panic. But the thing is, probably the first speaker will be late, or I don't know what's going on.
You mean that I exchanged?
He's here. He's here. Peter is here. He's here.
Okay, he's here.
Probably your luck. Your luck.
No, I mean, I can also speak earlier, and that's okay. But I told, for example, my supervisor that I'm speaking at 6. That would be nice if that he sees me speaking, not someone else. Then.
Sure. No. But actually, luckily Peter is here now. So as soon as Luca, next in post, we can make some tests.
Okay,
so
done.
You're safe.
Peter is here. Good.
Okay, so you made him cost.
Yes. Hi, Petr. Do you want to share your slides?
Sure. So, yeah. So share slides. So let me go at the very first page. And then I was, yeah. So I will share this. So, can you see the slides?
Okay.
Yes. Sure. Good.
Okay. So, yeah. I see that this picture of Gaetano is quite popular. This is already the second time.
It's the one which I can find most easily on the Google.
I know. Okay, yeah. Guess we can wait a couple of more minutes. Okay.
Yeah, so I will come in a minute then. Let me go.
Yes. You have time. So
but it's your photo, Luciano, which is very artistic.
Okay. Yeah. yeah. This was done 5 years ago, my master's degree. Yeah. Okay. Probably we can wait another couple of minutes just to let someone else join.
Okay.
Time to person to come back from the break.
Yeah, we'll wait just a couple of more minutes, Peter.
I have no problem. I don't have any rush.
Okay. Let's see.
Do I have camera switched on or switching?
No, we can't see you actually.
You can't see me?
No.
So
I don't
sorry,
know.
that was not intention. In fact, I wanted to be seen in full glory, but how can I switch on camera? Yeah. Yeah, good. Oh no, it's.
Yeah, but I don't know. It's okay. Probably it's because of the camera. Because okay, now we can see you. Try to go on.
Yeah, sorry.
To see. Oh, okay.
Good.
Okay, now we can see you. Yeah.
Wonderful. So I can even see myself. So it's wonderful situation.
Okay. Let's wait just another minute and we can start now.
Peter, because we didn't find you, I was coming to Breho just.
You really?
No,
you are
I'm joking. I'm joking.
Because I can see that you are sitting in the very same room as yesterday, so it would be.
No. I was joking. No. I'm at university now.
Okay, I believe that we can start. Probably people will keep coming in as soon as Petr will start talking. So, welcome everyone, and welcome to the third session of this day. And we will have three speakers, and the first one is Petr Jizba from Czech Technical University, and he will be talking about coherent states for generalized uncertainty relations, a new paradigm for Tsallis thermostatistics. So, Peter, whenever you're ready, you can start.
Yeah, I think I feel ready. So first of all, I'm really pleased to be here. And second, I would like to thank all organizers. It's really a wonderful conference so far. In this talk, I would like to sort of talk about generalized uncertainty relations from quite unusual point of view. I would like to discuss coherent states, and then I would like to highlight the role that Tsallis entropy plays in this framework. This work was done largely with my Salerno collaborators, Gaetano Lambiase, Gaetano Luciano, and Luciano Petruzziello. So outline, as you can see, is composed of three parts. So in the first part, I would like to make some background, indispensable background in GUP, generalized uncertainty principle, and coherent states that will be required in my talk. In the second part, I will highlight the role that Tsallis distribution function and Tsallis entropy plays into the scheme, and I will set up the entropic uncertainty relations that will be sort of equivalent or even more general than conventional GUP uncertainty principle. And in the third part, I would like to show up some applications, put forward some speculations about possible applications of this framework into entropic gravity. So let me start with the fact that it's rather well known that actually already from 50s that if you would like to reconcile general relativity and quantum mechanics, then typically some dramatic conceptual shift is required in our understanding of space-time. This goes really back into David Bohm in his 1954 paper, Fradkin and Minsky, who were actually firstly introducing slur automata in describing universe to spin chains to Roger Penrose and many other people, and most recently, I think, Gerhard Toft, who was a big proponent. In parallel with this idea, there was also, again, from 50s, starting a big revival of ideas that something really fundamentally interesting and new should be going on around the Planck scale. I think first who pointed this quite clearly was John Wheeler in his description of spin foam, who realized basically that fluctuations of the metric field around the Planck scale must be of order unity. So he really realized that fluctuations must be so large that spacetime start to be fractal, and all standard differential Riemannian manifolds, which we typically use in description of spacetimes, stop to be valid. In 80s, they started to be very, very popular, the lattice gravity from T.D. Lee, which actually stemmed from the works of Reggie, energy calculus. Most recently, it was Kleinert-Wold crystal approach that was basically successor of this lattice gravity. Loop quantum gravity, of course, it's a big field which is working with discrete volumes, and discrete volume operator with discrete spectrum. Black hole physics is also discrete areas that correspond to single bit of information. And in last years, it was cosmic solar automata. It was very much supported by Stephen Wolfram and Gerhard Toft. So those are just motivations why we could expect that spacetime should be discrete. So how this finiteness of the spacetime grains should be reflected in Heisenberg uncertainty relations. So obviously, we have one scale factor in conventional quantum mechanics. That's the scale factor Planck constant, which is quantifying the quantum fluctuations. But if we go really to Planck scales, then we have yet another scale factor, either Planck length or Planck mass. That should be also reflected. This existence of a new fundamental length should be also reflected in uncertainty principle. And indeed, there are many variants of such uncertainty principles. Perhaps the simplest and most popular one is the generalized uncertainty principle, which I wrote down here. This one is really for one dimension. And it was motivated by both quantum gravity and string theory community. It's quite popular in physics, but from a mathematical point of view, it's much easier if you would also add the variance in a position to it. So it would be symmetric right-hand side in variances in position and momenta. So it's interesting that this uncertainty relation automatically predicts for positive beta that there is minimal allowable fluctuation in position, because if you look here, this tells you that dx is 1 over delta p times something that behaves for larger p as a parabole. So it's hyperbole combined with parabole. So first it started for small delta p as a hyperbole, then it reaches some minimum, and then it goes to parabole. So there is the minimum which can be found as this particular value. So for positive beta, there is a minimal length scale, which is of this value. On the other hand, if you have negative beta, then you have actually maximal uncertainty or maximal fluctuation in momenta. There is actually no minimal fluctuation in position, but there is maximal allowable fluctuation in momenta, which is given by this value. And that will be something I will try to talk a bit more about later on. In fact, when you identify those deltas in Heisenberg language, they were called Angenauigkeiten. If you identify them with standard deviation, which is not by itself automatic, you don't need to really identify them with standard deviation. But if you do, then the former GUP principle can be directly written or can be derived from the deformed commutation relations of this type. So you can use the standard Schrödinger-Robertson procedure, or you can even use more general procedure with density matrices, which I'm not showing here, but it can be done also quite easily, as straightforwardly. And if you assume that you work with mirror symmetric states or mirror symmetric density matrices, that means when the expectation value of momenta is 0, then you derive the uncertainty principle, which I was showing on my previous slide. This deformed commutation relation is quite popular in community, and it appears actually in many works which range from quantum mechanical, foundational quantum mechanical issues through particle physics and even finite temperature quantum field theory. So you don't need even to go to Planck scales. In such case, this Planck mass is not necessarily related to Planck mass, but it's some fundamental mass or length scale, inverse length scale in the theory, in the description. Another ingredient in my descriptions are coherent states. Coherent states, basically in its essence, despite of the fact that there is a variety of definitions, are basically states or density matrices that saturate Heisenberg uncertainty relations. In fact, even if you start with the density matrix, then you find out that if you, in order you would like to saturate uncertainty relations, you always end up with the pure state. So coherent states, despite of the fact that you can work with density matrix, you end up with the state that is pure state, that is extremizing uncertainty relations. Despite of the fact that various definitions, I will basically, that will be my working definition in this talk. So it's the state that saturates uncertainty relations. In a sense, they are the most classical-like states in the framework of quantum mechanics, in the sense that both position and momenta are localized as well as possible as it's allowed by quantum mechanical rules. Coherent states have a huge amount of very, very interesting and important properties, like they closely approximate particle motion, classical particle motion, because they are least entangled with the environment. So they are least perturbed by the environment. That's actually a very important thing for discussion in quasi-classical limit of quantum mechanics. as we already heard from Klaus Kiefer. Coherent states are also provide also very simple passage to quantum classical transition, precisely because they are least perturbed by entanglement. So they are longest surviving states in going to classical regime. And coherent states are also allowing to discuss nicely quantitatively the things like Schrödinger cut states. There is a lot of works about so-called cut states when you have linear superposition of two coherent states, which are in a sense macroscopic states. So they are like the Schrödinger cat. Because there is no sharp value of number of particles in coherent state, so it can be arbitrarily large number of particles in coherent state. But they can describe entanglement, so it's very popular for description of entanglement in a noisy environment because they can really survive entanglement pretty well despite of the noisy environment. There is a lot of work in this direction. So one can of course ask if you would like to address the issue about GUP driven universe in this quasi-classical limit of quantum universe, how the coherent state should look like in this GUP. We can follow the same strategy as in the classical case. So because we are using the usual Schwarz inequality for description of uncertainty relations, we know that Schwarz inequality is saturated if the P and X are acted on the coherent states are linear combination of each other. And we also need that the anti-commutator between X and P is disappearing. This is basically what is sometimes called a Robertson term in the uncertainty relations. And basically, this first condition is direct consequence of saturation of Cauchy-Schwarz inequality. The second term is basically nullifying the Robertson term, which is basically telling you that the only possible way how it can be done is that C is complex number. So basically, what you need to solve for coherent states is this particular equation. This equation, it's easiest to solve in the momentum representation. You can solve it also in position, but in position you get basically the corresponding momentum operator in position representation is non-local operator. So it's very nasty differential equation. So it's much easier to work in momentum representation. And in momentum representation, the momentum operator is just multiplication operation. And the position operator we write in this form, which has here anti-commutator. The typical way of writing in older papers is just P squared dP. But we use this formulation because it's explicitly symmetric. So the operator X is in this way explicitly symmetric, which brings a lot of advantages, mathematical advantages. Particularly, it's very easy to prove, for example, for negative beta self-adjointness of the operator. While it's much more difficult to do that if the operator is not symmetric. So equation, this former equation, this one, in the momentum representation turned out to be very simple linear differential equation, which can be solved. And here is the generic solution. The generic solution has, depending on beta positive or negative, has different normalization factor. And of course, in the limit when beta goes to 0, then as anticipated, corresponding coherent states tends to the usual Gaussian wave packet or Glauber coherent state, if you want. In order to uncover what is actually behind the coherent states, it's convenient to define new set of variables. Instead of beta and gamma, one defines Q and B in this way. It can be shown, for example, that if I keep the variance of momenta fixed, then Q and beta are monotonically increasing function of each other. So particularly when beta is equal to 0, then Q is equal to 1. And in this way, you can rewrite the coherent state in this way. And if you come from statistical physics community, you immediately recognize that this is basically probability amplitude for Tsallis distribution, which is extremely popular in statistical physics community for free non-relativistic particles. So this is basically Tsallis distribution. You can actually show that it can be also related to Jüttner relativistic distribution, but I will not go into this point unless somebody would ask. So it's important we have Tsallis distribution. And in order I could proceed, let me mention a couple of things that are relevant in this context. So first, Tsallis distribution is called Q Gaussian distribution. It's denoted exponent with Q subindex. And when Q goes to 1, then it turns to be the conventional exponential distribution, in this case, Gaussian distribution. When Q goes to 1, then beta goes to 0. When Q is bigger than 1, that means when I have positive beta, then my integration over momenta is unbounded. And the Tsallis distribution is normalizable only for Q smaller than 3. If the beta is negative, which means the Q is smaller than 1, then the Gaussian distribution, the Q Gaussian distribution, has the finite support. So in fact, it has maximal value of momenta, which we already saw, that for negative beta, you should have maximal fluctuation in momenta. So we really see that support is bounded. In fact, it goes even farther. Q cannot be arbitrarily large. It can be even bigger than 3, or it cannot be even smaller arbitrarily. If Q is bigger than 5/3, so it's not even 3, then variance is infinite. So you cannot even define GUP because variances are infinite. So GUP is basically ill-posed identity. If actually, if the Q is more than 5/3, then variances are well defined, and you can find that they give you explicit prescription between gamma and fluctuations of momenta. In fact, if Q is bigger than 2, then even first momenta doesn't exist, which means that you cannot even define mirror symmetric states. So the only sensible region in which we should operate is Q from 0 to 5/3. But that's actually also restricts possible values of beta. It's very interesting that once you find out that you have extremizing distribution, you have Tsallis distribution, you can do a lot of interesting things with it. So first of all, normal Gaussian distribution, normal Glauber coherent states are extremal distribution for Shannon entropy. So if you fixed first 2 momenta being finite, then if you extremize Shannon entropy, then you get Gaussian distribution or just Glauber coherent states if you want. If you try to do the same, I mean, just having first 2 momenta fixed, you will never get distribution that is of Tsallis type, because Tsallis type distribution is power law distribution. It is power law tail distribution. In this case, you can never get the power law tail distribution out of extremization of Shannon-Gibbs entropy. In fact, however, Tsallis distribution is maximizer of Tsallis entropy. So I wrote for you here Tsallis entropy. And here this F is the probability distribution, or better, probability density function, which is induced by my wave state vector. So in order to, it's quite interesting that in the moment when you have a distribution that extremizes your entropy, then you can set up entropic uncertainty relations in parallel with usual variance based uncertainty relations. In the conventional quantum mechanics is done as follows. You have conventional canonical relation. You can represent it, for instance, in momentum representation in this way, similarly in position representation, which tells you that corresponding eigenstates are plane waves. Which basically means that if I take any state in momentum representation, I can convert it into state in position representation via Fourier transform. The reason why it's Fourier transform is that eigenstates, both for X or in position representation for P, are plane waves. And by using Beckner-Babenko inequality, which is basically a relationship between Fourier transform duals, norms of Fourier transform duals, you can set up Shannon entropy based uncertainty relation, where this N is called entropy power. I immediately mentioned so that it is, and this entropic uncertainty relation is saturated precisely only for Gaussian states, for coherent states of Glauber type. So entropy powers are defined for Shannon entropy as variances of would-be Gaussian distribution that have the same information content as the distribution you are expecting, you are basically inspecting distribution that not necessarily need to be Gaussian. This equation can be solved. You get uniquely that entropy power is just exponent of Shannon entropy. So it's basically like Einstein-Boltzmann relationship between number of states and entropy. So as I mentioned, those uncertainty relations are saturated only by Gaussian distributions. They actually define only for distributions with continuous spectrum. So they cannot be defined for discrete spectrum. And they are pertinent, that actually also shows why Shannon entropy is pertinent in conventional quantum mechanics. Let's just follow the same strategy for our GUP commutation relations. So again, here is the GUP commutation relation. Here I have a momentum representation, but unfortunately now the eigenstates are not plane waves. They are much more complicated. In fact, they are also not quadratically integrable, similarly as plane waves are not. They belong to a state of temperature distribution, similarly as plane waves do. And in fact, if beta is negative, then the operator x written here is self-adjoint. In fact, you can symmetric operator can be extended so that it can be made self-adjoint, and the spectrum is continuous. It's not true for positive beta, but I will not discuss positive beta here. So this is the dictionary which is connecting wave function in position and momentum representation, provided I connect them through this eigenstates. And again, I can find the generalization of Beckner-Babinko inequality, and again I can define entropy powers, but this time with respect to Tsallis entropy and with Tsallis maximizer, which is not Gaussian distribution, but Tsallis distribution. So it's again, entropy power is the variance of would-be Tsallis entropy with zero mean and unit covariance. That would have of order Q, that would have the same information content as Tsallis entropy of the order Q for a given distribution you try to explore. And if you do it, you get basic uncertainty relation, which are in terms of entropy powers. Those P and Qs are Helder double, which I mentioned on my previous transparency. And it is very similar structure as a variance-based uncertainty relations, but in fact, this is infinite tower of uncertainty relations, which is one parametric tower of uncertainty relations. And yeah, so I will possibly discuss things if there would be any question. Again, this is saturated if and only if the corresponding states entering here are the GUP coherent states, which are in the case of momentum case, they are Tsallis distributions. They are defined only for negative beta, because only in this case I have continuous spectrum. They cannot be defined for positive beta. Also show that Tsallis entropy has a pertinent framework if I would like to discuss GUP in quasi-classical limits. So if I would have universe that is GUP driven, and I would like to discuss quasi-classical limit of that universe, Tsallis entropy would be pertinent tool to do it. In fact, if you have extremizer, similarly like in conventional statistical physics, if you take extremizer like Gaussian distribution and plug it into your Shannon entropy or Gibbs entropy, what you get Clausius entropy of thermodynamics. This same is here. If you take the maximizer of Tsallis entropy, you plug it back into Tsallis entropy, you get entropy of non-extensive thermostatistics of Tsallis. In fact, non-extensive thermostatistics of Tsallis should be a pertinent framework for discussing the GUP-driven universe in quasi-classical limit. So in fact, we would like to discuss the borderline between classical and quantum territory. And if we have universe that is GUP driven, then the statistical physics of Tsallis should be very natural framework to do that. In fact, I would like to, in the last few minutes, show you that there is very nice, toy model maneuvering space which allows to do that, and that's entropic gravity. In fact, one can generalize our 1D reasoning to 3D, provided you choose correctly your commutation relations between xp, pp, and xx. So very convenient are the ones which were defined in Kempf paper 95, when all p's, three-dimensional p, mutually commute. Then you can find out that the coherent states between x and p again can be written as a Tsallis coherent states, and they again extremize the Tsallis entropy, and again you get the same uncertainty relations generalized to 3 dimensions. So now one of course would like to ask, if I would like to have something like entropic gravity, how it would be generalized if I would have GUP universe with negative beta? And of course answer is just combine the original Ferlindes idea for entropic gravity with non-extensive thermostatistic of Tsallis. So let me briefly remind you what Ferlindes entropic universe is about.
Petr, 5 minutes.
Good, that should be enough. So Ferlindes paradigm is based on the fact that you have some true microscopic degrees of freedom which you don't know what they are in any part of the space-time, but if their information about them is reflected in the holographic screen which is wrapped around that area, that region. And our emergent world is basically just emergent by the fact that we observed our external emergent world through the degrees of freedom that are on the holographic sphere. The sphere doesn't need to be really a sphere. In Ferlindes prescription, it can be any closed area. But, let's take sphere for simplicity. So it's holographic screen sphere with radius r. And in Ferlindes prescription, if there is any gradient of entropy between here and the holographic screen, then there should be force, which is described by standard thermodynamics. This is just work, and this is the heat-one form. So this is just thermodynamic identity. And you can get a Newton force, or you can actually get even more. You can get, for example, Schwarzschild solution. But for simplicity, Newton force, just by setting that dx in this relation is related to Compton wavelength, just a minimal distance from the screen on which you can still sensibly speak about single particle. If you have smaller, then of course single particle is losing its meaning. Mass here, the mass inside, it's basically energy, which by the equipartition law you can relate to a number of bits on the holographic screen and the formal temperature, which is related with temperature here. Then one can use the holographic prescription, which tells me that number of bits is related to 4 times the entropy on the sphere, which is Hawking-Bekenstein entropy, which is proportional to area. And final thing is that I use the Landau erasure limit, which tells me that if erase or I gain 1 bit of information, then my entropy will increase by 2p k beta. That's all. This is Boltzmann constant. If you plug it inside, then you get Newton law. If you plug it in this thermodynamic relation. The time of Tsallis non-extensive thermostatistics is generalizing the heat-one form from here to here. When here I have Tsallis entropy and generalizes Landauer principle for erasing 1 bit of information. Then if I take any dimensionless length scale, then I know that Hawking-Bekenstein scales as L squared, as area, which means that number of states must have this type of scaling. When n is some constant, and this is some function, arbitrary function of the scale that must disappear in the large N limit, a large L limit. So in fact, I can write my Tsallis entropy for the Hawking-Bekenstein scaling in this way. This is Tsallis entropy with Hawking-Bekenstein scaling. And in fact, what I can say that if I'm quasi-classical limit, then I can expand it, and I can do something which people typically do for small or mesoscopic systems. It's called Hill expansion. So I can take, apart from the leading order, also subleading order, because I can expect that in semi-classical regime, even subleading order, because universe should be small, even subleading order should contribute. And I get force. This is the force. From force, those coefficients are both positive. K1 and K2 are positive. From force, I can get potential. And apart from this subleading order, I get something which is known as a Mannheim-Casanas spherically symmetric solution of conformal gravity, which it can wonderfully fit the galactic rotational curves for more than 200 galaxies. In fact, the they could fit even more, but they were using those data from Little Things survey and Things survey and Spark surveys. So they were trying to pick up the best data. They were showing that, in fact, there is only one adjustable parameter, and it's the galactic mass to light ratio. So it's wonderful, this sort of fitting. It actually origin comes from conformal gravity. So this was published, first paper was published in 2011, but now there are many more papers. So in fact, we can fit this quite nicely, and we can even put upper bounds on Qs. So in our case, if I remember well, our Q-1 was similarly as in this case, wasn't it? You can correct me. It was 10 to minus 33, if I remember well. So it was the bound for Q-1 coming from this conformal gravity was
actually even smaller now.
Even smaller, yeah. So thank you. So we see that Q is very, very close to 1. So it's very, very close to classical thermodynamics, but it's not entirely the same. That of course gives all the interesting physics. So I would end up here and just summary. So momentum coherent states for GUP is basically Tsallis probability amplitude for with Q parameter that is allowed in this region. Mathematically, such coherent states are as basically represented as a deformed analog of the minimal uncertainty coherent states that are typically known in mathematical literature under the name Nieto coherent states. And entropic uncertainty relations, which goes together with that, basically they offer very natural theoretical setup for Tsallis entropies as an entropy for the decoherent or quasi-classical phase of GUP-driven universe. So it's a very natural framework to use GUP or statistical physics of Tsallis if you would like to discuss that particular GUP universe. Tsallis-Maxent allows to use non-extensive thermostatistics, which I was using, to explore, for example, modifications of Newton gravity. But there are perhaps other areas which are interesting to discuss. And actually, we also provide possible restrictions on Q parameter, which in turn impose also restrictions on beta parameter. Important is that in our case, we were using negative beta. So I would end up with this epilogue.
Okay, thank you, Petr, for the nice talk. And I guess we have time for a couple of questions. So Luca first with its hand. So Luca.
Okay, very clear talk, Peter, actually. I just a curiosity, because I admit I don't know anything about this Tsallis entropy. Is this exponential Q exponential you introduced at some point related to the one of the exponential function of the Q calculus?
No, actually, it's pity that no, it's in fact many people use Q calculus as a name, but no, it's shortly answered no. It's misnomer. In literature, you can find Q exponentials both from Q calculus and from Tsallis calculus. And I think it's because they were developing independently each other. So only thing which they share is the Jackson derivative, which is the only concept I know that is common both for Q thermostatistics of Tsallis and Q calculus of.
You mean the Jackson integral or the
Jackson derivative? Jackson derivative is basically derivative on lattice, if you want to see this.
I see, yes, sure. The Q derivative.
Q derivative, yeah.
Q derivative, yes, okay. I see, thank you.
Okay, so we have another question from Nikolaos.
First of all, thank you very much for the nice talk. I have talked to Tsallis for the last many years about this, so what I will tell you is not really, what I will ask is not really only my idea. I think the Tsallis entropy is related to, let's say, P-Laplacians and systems with memory and stuff like that.
That's right, yeah.
Therefore, I don't think a Fourier decomposition is appropriate. Because the Fourier decomposition assumes you work in Hilbert spaces. Here it seems you need some Banach space of some kind in order to do a natural decomposition, right? And you can see really this. Therefore, I don't really feel very comfortable, right, extending, and you can see that in Tsallis entropy, if you try to use Hilbert methods on Tsallis entropy, the expressions are quite ugly, they are quite complicated.
That's right, yeah.
I don't think they are very natural. The other thing that I have told Tsallis is that I question the use of the conventional Legendre transformation, because these results will certainly use it at some point. I don't think it's appropriate. There was some issue of invertibility. So probably something else is needed on this. And last but not least, these generalized uncertainty principles, right? Somebody can see them from a commutator viewpoint, like you have essentially a Heisenberg group. And the Tsallis composition property is essentially the same property, basically. You can embed it as a Heisenberg composition. So the generalized uncertainty principle, instead of having a two-step Heisenberg group, can be an nilpotent group of some sort, right? Therefore, it sort of naturally generalizes in this framework through the composition of the Tsallis entropy. Therefore, what you say is essentially correct in some sense, right? But so it is. I think it is guided really well from the viewpoint again of macroscopic things. But
so, what do you mean by decomposition of Tsallis
composition?
Tsallis entropy has decomposition. Of course, it has generalized calculus, which means that you can.
Right. But this can be easily recast in a sub-Riemannian context.
Precisely, yeah.
Right, and therefore, essentially, you fall into the general category of Heisenberg groups, Carnot-Raychaudhuri geometry, essentially. And there, you can basically, many of the things that you say happen sort of naturally. For instance, the Jackson derivative, which is directly associated with scale transformations.
In fact, I should maybe at this point mention that with Fabio Scardigli and Hagen Kleinert, we published, I think it was 2011, we basically published the work when we really worked with discrete calculus. That means we really defined quantum mechanics on discrete lattice. The work, we followed Bender and other people from past. So you can define self-adjoint operator on discrete lattice.
I believe that. I believe that, but I think you can do it also in the continuous context.
Sure.
If you generalize everything to sub-elliptic operators of essentially Stein and Weiss, 1971, and work with basically sub-things, right? Sub-Riemannian things. And that's all my comment, and that's all my... So I think that the appropriate context is something like, in the case of Banach spaces, sub-Riemannian geometry, rather than trying to do Fourier decompositions, Riemannian geometry. And therefore, I think things will fit more naturally in this mathematical framework.
I would say that so far, I was not using any geometry. I was, of course, of course, you can use Hilbert space. You can, on the Hilbert space, you can define topology. Riemannian topology, of course, you can define metric tensor on Hilbert space, but I was not doing that. I was not assuming any Riemannian structure in my Hilbert space. Not even here. I was not really touching even all those type of computations are back onto envelope type of computation. For example, this Verlinde. I was really doing just very simple back onto envelope calculations. Verlinde himself, he could extend things after quite big labor to Schwarzschild solutions, even to Reichner-Nernström solutions, but it involves a bit more. So that's what we have not been doing here. I was really just looking on the Newton law without looking on any Riemannian structure that would be from which it would descend, if you want. So it was not something like non-relativistic limit of Schwarzschild solution. That's what.
Okay, thank you.
Okay, thank you, Nicholas. Wickman, I'm sorry, but I guess we're running out of time. So if you would like to stay with us for the discussion session, you'll be the first that can ask the question to Petr. But now we shall move on. So I would like to thank Petr again for his contribution. And now we have Fabian Wagner. So Fabian, if you want to.
Right, yeah, you can hear me, right?
Yes.
All right, so I'm going to be sharing my screen. Let's see.
Okay, are you going?
Do you see the slides already?
Yes, yes, perfect. So next speaker is Fabian Wagner from University of Szczecin, and the title of the talk is Curvature-Induced Uncertainty Relations. So you can go, Fabian.
Hello, everybody. First of all, let me thank you, the organizers here, for giving me this opportunity to speak at this illustrious conference. Today, I'm presenting work I've done in collaboration with my supervisor, Mariusz Dąbrowski, and with the very chair of this session, Luciano, right? The title of this talk is, as you can see, curvature-induced uncertainty relation. Now, we have already, heard a lot about uncertainty relations today, but this is going to be kind of a bit of a different approach. And in particular, I'm not going to be talking about the generalized uncertainty principle, but the extended uncertainty principle. In particular, I'm going to try and answer in this question, okay? Are extended uncertainty relations of quantum gravitational origin? That's supposed to be kind of the background for all of what I'm doing. In order to tackle it, I divided my talk into the following 5 points. First, I'm going to introduce you to extended uncertainty relations, and so you have the background, and then introduce you again to the novel approach that we were following in our work. But in order for this to really get to work, we first of all have to talk about the dynamics and especially the kinematics of a non-relativistic particle in curved spacetime. And then once everything is defined, I will be able to give our final results basically in the uncertainty relation part, the fourth part. Then in the end, in the discussion, I'll try and answer the question I just posed, right? But let me start with the introduction. Uncertainty relations are, of course, at the heart of quantum mechanics. And I mean, this is the most famous formulation. We've seen it several times here in presentations already, so let me be fast. Let's say we have two observables, non-commuting operators, A and B, right? And we describe our system by a normalized shape psi, then we can define their standard deviations in this way, right? And then we have the Robertson relation, or if you have something more stronger, the Robertson-Schrödinger relation, which you can directly derive from here, which relates basically the product of these two uncertainty relations to the expectation value of their commutator. I think all of you know this already. This is the first quantum mechanics class stuff. In particular, if you choose the position and the momentum operators, and then you have the canonical commutation relations, and what you will obtain is Heisenberg's uncertainty principle. Now, okay, people have been talking about minimum length scenarios already at length here. We've seen very, very good talks about this, but let me briefly explain what I mean here. Say in the last 20 to 30 years, I mean, this is a very old idea, but this has become prevalent in the quantum gravity phenomenology community, that people are talking about these minimum length scenarios. Imagine you're doing a measurement, and then with this measurement, you're resolving a certain length scale, and this should be always bigger than some certain length scale, call it, L0, okay? And of course, we assume it to be more or less of the order of magnitude of the Planck length. One possible and by far the most often used way to implement that is by just modifying the standard Heisenberg uncertainty relation, adding this green term, right? Where we have something which depends on the standard deviation of the momentum operator and this L0. Of course, there are different ways of writing this, or different functions you can use there, but this is the most often one, I guess. Using or invoking, the Robertson-Schrödinger relation I showed before, this of course amounts to modifying the canonical commutation relations, right? And by adding terms which depend on the momentum operator. Now, all of this, as you know, goes under the name generalized uncertainty principle. That's not exactly what I'm going to be talking about today. In fact, you could do something like, you could do a completely dual discussion about what I'm doing, which you might then call minimum momentum, all right? There, the idea is in fact quite similar, or you also have some kind of motivation thinking about our cosmological horizon, which gives a distance limit in a way. and a limit in particular of wavelength, because otherwise, if the wavelength of something is larger than the horizon scale, then within one period you have no causal connection, right? So you say there is a maximum wavelength, and according to the de Broglie relation, then you'll have a minimum momentum length scale, which will be related to your Hubble parameter, which gives you more or less the distance to the horizon. Okay, all of this is very rough, of course. Now, again, you can implement this in exactly the same way, right? You're adding a term, but this time, this green term depends on the standard deviation of the position operator, not the momentum operator. And here we have this minimal momentum. And by the Robertson-Schrödinger relation, again, you'll have to modify the canonical commutators. That's what you do then. Now, all of this goes under the name extended uncertainty principle. That's what I'm talking about today. But we might ask, is this the only possible formulation? I mean, of course, if someone asks this question, you'll expect him to say no, and that's exactly what I'm going to do. Let me introduce you to this novel approach, this novel idea in that direction. So, in fact, this is very similar to the way we usually explain the Heisenberg uncertainty principle to undergraduate students, for example, or the public, say with the single slit experiment, right? If we have some kind of wave package coming in here, and here we have this characteristic spherical wave pattern, then at this slit, right, which has a slit width delta x, we can use this delta x as a measure of our position uncertainty exactly there. And then you define the momentum uncertainty in a different way, and depending on the way you define it, you can get different result. But the product of the two will always be of the order of h bar. Now, this is of course just very hand wavy anyway. We have to be a bit more rigorous, and what we want to do is, or what we wanted to do is to generalize this to curved three-dimensional space. Okay. Now, the original idea for this approach is not ours. This was done by Thomas Schürmann and published in 2019. That's where this comes from. And it goes the following way. Imagine on your three-dimensional background, you place some kind of domain, whatever, for the moment, whatever shape you wish, okay? And to this domain, you constrain your wave function psi, okay, which may symbolize a particle. And you constrain this by imposing Dirichlet boundary conditions, and then it vanishes outside, right? If you now find some kind of measure of the size of this domain, which has to be diffeomorphism variance, I don't know, you can relate it to its volume or something like that, right? Then you can see that this could be a measure of position uncertainty. In fact, depending on how you choose, or if you choose this well, it's quite natural to use this as a measure of the position uncertainty, because that's where you localize your wave function in. Then on the other hand, you can define the standard deviation of the momentum operator now kind of a bit different than usually, because on curved backgrounds, it's a bit more complicated. Of course, the first part, the p squared part, is quite simple because that's a scalar, but here we would have the expectation value of a vector, and for differential geometric vectors, this is complicated. So it's just not a vector in that case, unless you introduce this Clifford algebra valued objects, which is in fact then just equivalent to describing everything in a local inertial frame, because then you can take out the metric, right? And that's how you can even only define these expectation values. Now you can prove, or I think actually like this general statement should be relatively obvious actually, that there will be one state psi naught, right? Call it psi naught, or state which minimizes this standard deviation. And the corresponding result will be bigger or equal to 0, right? Because it's a positive definite quantity. Apart from that, this result here, this standard deviation, will be a function of rho, for measure of position uncertainty, I recall. So what we get there is an uncertainty relation, right? That's the idea. Now, first of all, I didn't really say anything about the domain. So which domain is useful on a curved manifold? I mean, of course, this is just a matter of choice, okay? If you do an experiment, and of course, if you had the power, you could just do an experiment, then you could kind of, use a choose a domain which kind of suits well to your experiment. what Sherman did and what we did afterwards as well is just to choose the simplest possible one, which is a geodesic ball. Okay. Now let me first tell you what this is the geodesic distance. Unfortunately, you use the same letter, the same symbols to symbolize geodesic distance and standard deviations. These are sigmas. Well, I'll stay with the literature here. Now the geodesic distance between the point P and the point Q, right here, is really just the distance measured along the shortest geodesic connecting these 2 points, and that's how you define this, right? That's what this integral means. And now a geodesic ball really is just a region of points whose geodesic distance to its center, okay, is smaller or equal to some radius, call it rho. And I don't call this rho without a reason, because of course this radius of the geodesic ball is a diffeomorphism invariant quantity. And as a radius of a ball, it's really natural to interpret this, of course, as your measure of position uncertainty. That's the idea behind all of this. And that's, if you choose this kind of domain, you can do everything analytically. That's of major importance, of course. B rho is how you call that. Now, a geodesic ball, of course, doesn't always look like a ball. That is just a matter of coordinate system. For example, here, here we see how a geodesic ball is getting deformed as it is approaching a Schwarzschild horizon, as seen from the static observer at infinity. Okay, and you see this mushroom kind of form that it obtains. All right. Now, of course, as we're doing quantum mechanics, it's always good to choose a base. That's what we're doing here. The negative Laplace-Beltrami operator, which is, of course, just the free particle Hamiltonian, in fact, basically, right? Is self-adjoint within geodesic balls and in curved backgrounds. And thus, its eigenstates will make up an orthonormal base of a Hilbert space, which is, of course, characterized by the quantum numbers NL and M, which you all know, of course, from spherically symmetric quantum mechanics problems, right? Correspondingly, these lambdas are the corresponding eigenvalues. And in fact, for all of this to work, what we have to do is to solve this eigenvalue problem here with respect to these Dirichlet boundary conditions. Okay. If you do all of this in flat space, that's actually quite simple. It's not very complicated, and we were able to show a bit more precisely last time that this state of lowest uncertainty is in fact just the ground state of free particle Hamiltonian, in fact, okay, where n equals 1, m and l equals 0. And correspondingly, you will be able, or you can calculate this result, and you get pi h bar over rho, multiplying by rho, you get basically or analog of Heisenberg's uncertainty relation, okay, in flat space. On the right-hand side, of course, we have pi h bar, but this is anyway dependent on the shape of the domain we have there, right? Now, we didn't want to do all of this, of course, in flat space. We wanted to do this actually coming from curved space-time. But in order to be able to do that, first of all, we have to think about the non-relativistic particle in curved space-time. Now, the procedure we followed in order to get there is the following. Starting with the dynamics of a relativistic particle, okay, we took the non-relativistic limit and obtained the then appearing effective fields for a non-relativistic particle to then be able to define the physical momentum, the one we actually measure, and correspondingly from the quantum mechanical side, the physical momentum operator. Okay, because if we want to calculate standard deviations, what we need to know is the physical momentum operator. All right, the action of a relativistic particle is just the integral along its, the length of its trajectory, basically. And if you rewrite this in terms of the affine parameter, you get this, one particle Lagrangian. I think most of you have seen this already. Of course, there are also other formulations which are equivalent, but this will do for the moment. Now, this action is, of course, invariant under time reparameterizations. That's very famous. So we can choose a gauge, and we'll choose the gauge that along the trajectory, the affine parameter just always equals the time coordinate. All right. Now, the background metric will be described by ADM variables, just because they're really well suited, as they already decompose or metric in a 3+1 form. They're really well suited for the non-relativistic limit of what we are having there. Then you describe the metric in terms of the lapse function, n, right? The induced metric on slices of constant coordinate time, which is Hij. These are, of course, in the ADM formalism, these are the dynamical objects, right? And then we have the shift vector, which usually relates to, rotating coordinate systems or rotating metrics in general, like Kerr, for example. If we rewrite now the Lagrangian in terms of these variables, okay, this looks very similar to, just special relativistic Lagrangian, just that here we have the lapse function multiplying, and or beta, which is of course usually just, the velocity over the speed of light, is a bit more complicated. You can see it here. Also depends on the shift and on the other variables we have here. But still, the non-relativistic limit will be the same. Beta has to be small, right? So what we do is that we expand the square root, and we obtain, of course, the rest mass term, that's this one. And then we have the kinetic term, which is here. A word, of course, of caution might be in order, or beta squared does, of course, not transform as a force scalar, right? So we introduce a preferred frame here. But of course, I mean, we're taking the non-relativistic limit, so this was to be expected. We just have to have in mind that this, this slicing must, in our Gedanken experiment we're doing here, always be the slicing of our measurement device. This is coordinate time, right? And the measurement device is at rest and slices the space-time exactly in this way, right? While our geodesic ball containing the particle might be moving relatively to it. Not as much as that, perhaps, but you know what I mean. Now, we can, in fact, rewrite the Lagrangian now, finally, in terms of the real variables we need, which you could also call, or it goes under the name gravitoelectromagnetism, and for a reason, of course, because this Lagrangian here looks very similar to the one of a charged particle, right, moving on a curved background, just that the charge is replaced by the mass, because, of course, gravity couples to the mass. In fact, our new effective field we're having here is our effective metric, capital G, okay, you see here, which gives us the background curvature. And then we have some kind of, gravitomagnetic vector potential, AI, which relates to the shift, and a gravitoelectrostatic potential phi, which kind of gives you the time dilation. But we don't really care about that, because what we mainly want to know is what our momentum is here, right? And there it doesn't really play a role. The vector potential, though, does. The reason is that, of course, this is very similar to the minimal coupling of a charged particle, right? And correspondingly, our action has the same kind of U1 gauge invariance, right, as the electromagnetic field action. But the problem is that the canonical momenta, call them pi, right, which are just derivatives of the Lagrangian with respect to the velocities, read like this. Right, that's how they read. And here we have a part which depends on a gauge-dependent thing, right? So they're not invariant under this gauge transformation, and thus they cannot be observable. If we measure momentum, that's not what we measure, right? In fact, we have to define physical momenta, which read like this, in fact, so which cancel off this gauge-dependent part. And well, now this finishes, of course, our classical treatment. Once we know what the physical momentum classically is, we can now go to the quantum mechanical one. And what we need, as I said, was the corresponding operators. Now they look a bit more complicated now than in usual quantum mechanics, right? So first of all, this is, of course, the usual differential operator, but of course we have to replace this by some kind of covariant derivative for sections for the specialists, where here we have, of course, the Christoffel symbol. And apart from that, we will get, of course, this extra term here, which comes from the physicality of our momentum operator. But this is, of course, not the only one we need. We also need to know what the squared momentum operator, in fact, is, right? Because, there might be some operator ordering ambiguities, but in fact, they all cancel out. That's good, like lucky for us. This part, of course, is the Laplace-Beltrami operator we were already seeing. That stands for the squared conjugate momentum operator, but then we already also get these mixing terms where H stands for Hermitian part. You subtract off the anti-Hermitian part. And this part is quite obvious. Lambda C bar, of course, is now replacing the mass as we describe everything in terms of the reduced constant wavelength. That's what this means, just because we want to have everything in terms of length scales, okay? So this is what we get here. And once we have all of these ingredients together, we can go back to our uncertainty relation. And that's what we wanted to get in the first place, right? Now, first of all, let us assume that these balls are small, right? This tells us that we can approximate the metric around their center, P0, because we're having there a sufficiently small neighborhood at this point, such that the metric is basically flat plus second order corrections by the equivalence principle. And in particular, you do this quantitatively by using Riemann normal coordinates. Then your metric, your background metric, will look like the Kronecker delta. And here we have this correction term, which is dependent on the Riemann tensor, evaluated exactly at the center of the ball. And of course, the center of the ball, by the way, will always be kind of the expectation value of the position operator inside of this ball, right? Just so we know now. Having all of this together, we can expand, or we can treat this entire problem perturbatively, right? And thus, the state of lowest uncertainty will still be the same state as it is in flat space. So we don't really need to choose anything new. We can just do quantum mechanical perturbation theory. We will get changes, though, in the Hilbert space measure, in the Laplace-Beltrami operator. We also have to expand the lapse function and the shift and so on and so on. But you can do all of this perturbatively, and in fact, you will get this kind of quite neat result. Okay. First of all, here we have the flat space result that I was citing or showing you in the beginning, pi h bar, right? And then here we have second order corrections. The first one of which depends on the Ricci scalar of the effective metric, right? Evaluated at this expectation value of the position operator. And it comes in here with a minus sign, which means that if we have positively curved slices, we decrease the uncertainty. If we have negatively curved slices, right, we increase the uncertainty. The second part here is depending on gradients of the shift, which relate, of course, to the rotation, and it is completely positive. I mean, this is a square, basically, right? It may look like this term could be of fourth order, of course, because we have a rho to the 4 here. But in fact, rho squared over lambda c squared is a dimensionless number, right? And the non-relativistic limit just tells us that this is much bigger than 1. So in fact, this is a second order contribution, and it might be much larger because we have this much larger than 1 factor here. Okay. Xi here is really just a mathematical constant I put here. Now, just to show up with my drawing skills, I thought about showing you an example of, for example, a rotating black hole. So it's a particle rotating around a black hole, or in a geostationary orbit around the Earth or the Sun, around this here. And the result looks as following. Okay, on the left panel, you can see the trajectory of the classical trajectory of the particle as it's surrounding this black hole. It has to be a black hole because this white thing here is the outer horizon, which tells us basically that this is very small, very close, but still not close enough to leave the non-relativistic regime. Right? On the right-hand side, we see the deviation from our standard uncertainty relation, and we see, of course, that the closer you get, the stronger is the deviation, which is, of course, what you would expect, because then the gravitational influence increases. Now, this was our result. So yeah, let me go from here to the conclusion already. First of all, let me summarize what we did. what we did was that we started with a relativistic particle in a general curved spacetime, right? Then we took the non-relativistic limit and obtained the corresponding effective background fields. From there, we were able to define our physical momentum operator, which is really all we needed to solve our problem in the end. And assuming small position uncertainties, we were then able to give a novel formulation of the uncertainty relation, in fact, which is sensitive to curvature-induced corrections. Right? So then what we obtained here was an extended uncertainty principle, or EIP, which is what I was talking in the beginning about, right? You know, a second order correction to the usual uncertainty relation. That is exactly what we got out here, in fact. And apart from that, an increase, or it shows us an increase in uncertainty for negatively curved slices, and of course a decrease for positively curved ones. And apart from that, for a non-vanishing shift gradient, all right? So now that I've told you all of this about what we did, are extended uncertainty relations of quantum gravitational origin.
Fabian, got 4 minutes.
4 minutes, okay. Yeah, that's no, are extended uncertainty relations really of quantum gravitational origin? I mean, we didn't use any quantum gravity here. In fact, there is no relation to two horizons or anything like that. And we just have curvature-induced corrections, right? And this is just semi-classical. I mean, we have quantum mechanics and a curved background. That's all of it. So for the moment, this is my answer to this is negative. Of course, this is just my opinion, but that's what this seems to suggest, right? Now that you've heard me rambling quite long enough, let me just finish off with a couple of fun facts about this. In fact, the uncertainty, the standard deviation in the momentum operator we calculate here, right? This uncertainty relation can vanish, which is something that Sherman showed in his paper for manifolds of constant curvature, because there was no, he didn't do a perturbative treatment. It was simply enough to be solved, you know, entirely non-perturbatively. And there you could have a vanishing standard deviation just, you know, for closed manifolds, when once your geodesic walls were as large as basically the entire universe, and your uncertainty in the position was maximal, as if it was, you know, infinite in flat space. That's how the standard deviation of the momentum operator could vanish then, okay, which is like basically like a classical behavior, kind of funny somehow. And then something we found out, we found out after we wrote these papers, is that in fact you can circumvent the non-relativistic limit. So I showed you all of this in terms of the non-relativistic limit because that's simpler for the moment, but it can be circumvented, and you can do the entire calculation in relativistic quantum mechanics, even though, of course, you will still have a preferred frame. This will always be there. I mean, your geodesic ball, you know, it looks like a geodesic ball just in one frame. In a different frame, it may look like a geodesic egg, or, you know, if you're a bit wilder, like a geodesic tuba or whatever, what you want. And apart from that, of course, you know, this standard deviation of the momentum operator is a gauge-dependent quantity then anyway, because, you know, it's a frame-dependent quantity, of course. Yeah. But, well, still it's interesting because this then works also for relativistic velocities and strong curvatures and so on and so on. Right. Apart from that, and that's just a completely additional fact coming from here. Imagine we follow the exact same reasoning, starting in curved momentum space, using geodesic balls in momentum space, right? And then calculating the standard deviation of the position operator. Quantum mechanics is completely invariant under exchange, basically, of X and P, right? So this tells us that we would get like a generalized uncertainty principle here from momentum space curvature, which really just relates to the curvature you have in momentum space. Okay, and this is something which of course relates to a lot of research which is already done, for example, in the realm of doubly special relativity, where you have, you know, this duality between minimum lengths and curve momentum spaces. All right, so as you have all listened to me until now, thank you very much for that. I think that's it for the moment, and I'll leave you with this take-home message. The more uncertainty you can tolerate, the more creative you can become. Thank you.
So, thank you, Fabian, for the nice talk. And okay, we have right on time, and so I've time for a couple of questions. First one is Nikolaos.
One very fast question. Have you ever thought about doing a similar analysis in phase space, right? Why do I say that? Because in phase space, you have a natural analogy between X and P's, and this buys you an I, right? Which is essentially an almost complex structure, which may allow you to say many more things than you would say otherwise.
Yes, indeed. I've been thinking about going into this direction as well, especially also because, as I've not done it yet, but I've been thinking about doing that, especially because I was also thinking about curving position and momentum space at the same time, right? And then, you know, this would also be interesting in that respect. Yeah, I think it's something that is coming up now, and yeah, I think it's a good avenue.
Thank you.
Okay, we have another question from Fabio.
Hello, hi, very nice talk. Can you go to your result? I mean, when the slide where you presented the formula,
Yeah, I'm going, wait. Oh, wait. Let's see, here we go. Oh, that was too much. Okay, I don't know, my computer is going nuts. Here we go.
Yeah, that one. So there you can compensate, right, between the two terms, since they have
yes.
What does it mean? This there is a particular distance, rho or uncertainty in the distance where the inequality becomes essentially the standard one, or there is maybe a particular curvature, particular manifold on which these two terms they cancel out each other.
Yes, this can definitely happen, that they cancel out. I mean, the point is that, of course, this first of all depends on not only on the manifold, but it depends also on the observer, right? So it's quite improbable to keep this in this delicate balance that will get no influence, basically, right? And then, yeah, you could probably construct something like that, definitely. Right.
So you can construct a manifold in which in principle, at least, perhaps you can derive an equation for a manifold in which the two terms cancel out everywhere.
A manifold with a certain trajectory and then a certain observer. You have to take all of these things into account, yeah. Because these quantities here are not dependent on the position. I mean, they are dependent on the position you are at now, right? But they're not dependent on the measure of position uncertainty, right? They're just, you know, numbers for all what is get at some point. And they cancel each other. They can cancel each other out, definitely. But I think so. In fact, this part is usually from many applications. This is 0 anyway, or it's very small because shifts are not very strong, right? But you can, of course, always, you know, by this you can always kind of cancel this out. And in our example, for example, we chose this to be very large to have a very strong influence. Okay, this is how you get some 10 to the minus 6 corrections and something like that.
So you say they are more or less of the same order, you say, because the second...
No, this depends on your setup, definitely, completely. Like for example, in the example we have here, right? here, the third term, or like, the one depending on the shift, is much stronger, like 6 orders of magnitude stronger. It's just dependent on basically usually on the mass of the particle.
I see. And in principle, you can even get, suppose you can neglect the 4th order term, then can you have 0? 1 minus rho squared can become 0 in principle.
Yes. So first of all, this is not 4th order. This is 2nd order. I'm just saying it's also 2nd order. That's why I said, right, because this is just a dimensionless number. Yeah, you can get 0. That's what I was saying about talking about before. It doesn't work in this setup or in this approach because these are just corrections, right? So you cannot make them large. I mean, at least you cannot trust your equations then anymore, or this result anymore. But as I said, Thomas Schumann in his original paper was thinking about manifolds of constant curvature. And when they are closed, as I said, he had this problem, when you have a closed, like a closed section of Friedmann universe, right? It is finite in its extension. And then if your geodesic wall is so large that it kind of covers the entire manifold, you have a maximal uncertainty in the position. It's just like taking, the infinite and making finite, and correspondingly, then you get 0. Exactly, this is when you get 0.
Okay.
And that's heuristically how I explain it to myself. Like you have this closed form, like from topology, basically, not local geometry.
And one very last question about the orbits that you showed before, maybe the slides. Yeah, these orbits here. So you are computing on the left.
Yes.
It's an orbit of something around gravity. What's that? Around the black hole?
It's a rotating black hole. So basically, Kerr approximated to some point now. Mm-hmm.
And if the black hole is not Kerr, what happens?
I mean, you would see something similar, right? It's just we used Kerr just to get here larger influence, because otherwise you have no shift, right? Shift for Schwarzschild is 0. Then this term completely vanishes. And as I said, you can enhance this effect with this term if you choose the mass, for example, of the particle large enough in comparison to the size of the ball, right? And if you do that, then you will get this 10 to the minus 5, for example, influence. Otherwise, it would be of the order 10 to the minus 10, I guess. So this is just why we did this.
Just to have an idea, what is the difference between this effect that you are showing here and the precession of perihelion that you get around a Schwarzschild, the black hole? The orbits, I mean.
So I mean, this is this is now a bit. So I mean, the trajectory is just classical. Okay, this is just as an aside. Here we have a classical trajectory here, and then we evaluate our result on it. So I think it's a bit hard to compare these. So this precession you can see here is just the natural precession.
Oh, okay.
Yeah, so what we did here is using the classical trajectory just to see on the left-hand side what is actually happening on the right-hand side. It's just, explaining this. Okay. And then always evaluating this at this relation along the trajectory.
Okay, thanks.
Okay, so yeah. Any eventual question can be postponed to the discussion session. So I'd like to thank Fabian again for his contribution. And now we'll move to the last speaker of this session and of today, which is Saurya. Okay, Saurya is here. Okay, Saurya, can you share your screen?
I'll do that. Can you hear me, Luciano?
Yes. Yes.
Okay. And I have 35 minutes, including question time, right?
Yes, sure. 30 minutes. Typically, it's 30 minutes plus 5 minutes for questions. But if you want to take all the 35 minutes, then we can immediately go to the discussion section. I mean, it's up to you.
But thanks for explaining. Okay. So Control L, full screen. Let's see.
Okay. Yeah, we can see your screen. Okay, perfect. So the last speaker, we already said, Saugadas from University of Lethbridge, and the title of the talk is Quantum Raychaudhuri Equation, Implications for Spacetime Singularities and the Quantum Origin of Cosmological Constants. So you can go, Sauga.
Thank you. Thank you very much to the organizers for this opportunity. It's much appreciated. And I realize this talk is probably a little bit different from the others in the sessions, which I quite enjoyed. Hopefully that would be okay. So yes, still a good morning from Western Canada. This is our university with the Rockies in the background. So a quick introduction to the overview of the talk. I'll talk about the Raychaudhuri equation and singularity theorems, and then the quantum Raychaudhuri equation and no singularity theorems, and how that translates to the quantum corrected version, or a quantum corrected version of the Friedmann equation in cosmology. And then with the proposal that a viable candidate of dark matter, which is one of the important components in the Friedmann equation, is a Bose-Einstein condensate made of light bosons. We'll see how far we can go with that in terms of a source of dark matter and potentially dark energy or a cosmological constant. And I will end with summary and conclusions. So, right. So let me start a little bit with the singularity theorems. And well, the reason, of course, like they're very important. And last year, as we know, the Nobel Prize went to singularities in space-time. In any case, the singularities in space-time are pathologic. They are space-time pathologies. They signal the breakdown of all physics, as well as the start and end of time. For example, the Big Bang and Big Crunch, as well as black holes. Now, often curvature going to infinity is taken as a sign of singularity. Yes, it is indeed indicative, but it is neither necessary nor sufficient condition for a space-time or singular space-time or space-time singularities. Because, for example, infinite curvatures can take a finite, like an infinite proper time to reach. So they're there, but you can never reach them. So the space-time can be deemed non-singular. Or curvatures could be finite everywhere, but for example, a hole can be cut out or the space-time is not complete. Then you know, in fairness, that can be deemed as a singular space-time. So what is considered as the necessary and sufficient condition of singularities in space-time is so-called geodesic incompleteness, which is basically without any other agent, every geodesic, like it doesn't begin or end, right? But if a geodesic reaches a dead end, that's called geodesic incompleteness, and it's considered to be a necessary and sufficient condition of singularities. Now, how does that come about? Well, the Raychaudhuri equation, it's a pretty straightforwardly derivable equation, as I'll try my best to demonstrate. That's kind of the, I would say the most, or one of the most certainly important ingredient in this whole, business of singularity. So here we have a pencil of geodesics. Sorry for the small print. I'm still getting used to it's online. Anyway, so you have a pencil or congruence of geodesics with a velocity field, u suffix a as a function of space-time. One takes the total derivative of it along the geodesic, which can be written in this way by definition. Change the order of the derivatives. One picks up a curvature term, and then change the first one to a total derivative with the excess term here. The total derivative term is the derivative of the geodesic equation, or the geodesic condition, therefore it's 0, since these are geodesics, and we end up essentially with these two terms here. Now, if we take a trace of this and define the trace, well, define the velocity, the derivative of the velocity field, which we have taken here, right, as a combination of the trace and the symmetric and the antisymmetric part, then the trace of that part is known as the expansion. And if you take the trace of this equation, we end up with this Raychaudhuri equation, which is, as you can see here, it tells us that the right-hand side, so the expansion, the rate of expansion, the right-hand side, most of the terms are negative. This is the important point. So since most of the terms are negative, there exists for every space-time pretty much a congruence of geodesics for which because of the negativeness of the right-hand side, the expansion converges. If it's initially converges, it keeps converging. And one can easily show by integrating that equation that within a finite proper time, the geodesics end. So geodesics are incomplete purely by virtue of this equation, and the negativeness of the right-hand side, essentially. So, and that what happens is because geodesics are incomplete, so as you can see here, it begins and ends like any congruence of geodesics, begin and end at a finite at 2 points. These are known as conjugate points. Now, what's the problem with that? So conjugate points follow from the Raychaudhuri equation, and conjugate points imply that the geodesics are no longer maximal length curve. This is the situation is a little bit opposite to a Riemannian manifold. Remember that this is a single Riemannian manifold we're talking about. In a Riemannian manifold with all plus signatures, for example, the surface of the Earth, as you can see, the great circle, which has both the conjugate points, so the North Pole and South Pole, they are the maximal geodesic curve. So those are the geodesics you don't want to take if you're flying on a plane. For a pseudo-Riemannian, it's the other way around. So conjugate point implies that geodesics are no longer maximal curves. However, maximal geodesics are predicted by global arguments. For example, when we derive the geodesic equation. So there's a tension, there's a contradiction between, apparent contradiction between the prediction of Raychaudhuri equation and the dynamics of or the kinematics of GR. And the only resolution of this is that sufficiently long geodesics cannot exist and that geodesics are incomplete. This is the essence of the singularity theorems. And it holds for most space-time. And, you know, like we know that Hawking and Penrose first proposed in its entirety the singularity of singularity theorems. The equation Raychaudhuri was derived by Raychaudhuri as relatively lesser known physicist. And around the same time, it was also proposed independently by Landau and Lifshitz. You can find the equation in a certain form in their classical theory of fields. Now, the importance of this, of course, is that the Raychaudhuri equation and the singularity theorems, it's very general because and it means that all reasonable space-times are singular and in which physics breaks down. And they're very general. Basically, the reason is that gravity is universal and attractive. So therefore, the right-hand side, all the terms are, most of the terms are negative. This is essentially the reason. The second point to note is that it uses this fluid picture. So it uses the velocity field and takes derivatives. So it's a field, right? It's a function of space-time. It's a vector, so it's a field. However, the fact remains that all these singularity theorems, as well as the Raychaudhuri equation, they are, it's of course a completely classical equation. So the question is what happens when one tries to quantize it or write a quantum version of the equations, right? And for example, one might want to look at expectation values or Ehrenfest type theorems and what happens. But first, let's try to find a quantum version of the velocity field. So now to do that, so we write the Raychaudhuri equation once more here. Again, theta is the expansion, like tells us how quickly the geodesics converge or diverge. Right-hand side, as I said, most of the terms are negative. Remind ourselves that this is the term we set to 0 because because of the geodesic condition. So this is the geodesic condition. When we try to include quantum terms here for simplicity, and I will complete the argument for completeness for the non-simple case as well. But for simplicity, we look at the so-called non-relativistic version of the Raychaudhuri equation to do our calculation that will generalize. And I'm happy to answer any questions about this at any point. So the non-relativistic version is basically you replace the curvature by the Poisson term. And this is the non-relativistic version. So the term I ignored here in the non-relativistic scenario, it's equivalent to this term here, which you can clearly recognize is basically, you know, non-relativistic version of geodesic equation, which is Newton's law, right? So how does that change? Now, of course, when we change from classical to quantum, if we talk about the non-relativistic scenario for simplicity, we must replace Newton's law by the Schrödinger equation, or whatever equation you have, relevant to the scenario. So let's take the Schrödinger equation for simplicity. Write the wave function as amplitude in a phase where curly R and S are real fields, real functions. Define, following the standard Hamilton-Jacobi formalism, define the velocity field. This is the quantum velocity field, if you like, is the gradient of this phase times h bar over m. Again, this is as is done in standard Hamilton-Jacobi theory. And if one substitutes this in, one actually arrives at two real equations from the complex Schrodinger equation. Interestingly, the first one is nothing but the conservation equation, right? As you can see, where rho has the standard definition, like absolute value of psi square, and v given by this, so rho times v is j, right? Interestingly, the second equation, which also follows from here, is simply the Newton's law augmented by the so-called quantum force or quantum potential term, which looks like this. This is wave function dependent. So it's nabla square or nabla on the real part of the wave function divided by itself, and so on and so forth. So this is known as the quantum potential term. Now, how does that help us? Well, so the way one can use this is that if one chooses initially the quantum particles, say an ensemble of a bunch of electrons, let's just say, distributed initially as a Gaussian or some kind of distribution, then the probability conservation equation, which is this, guarantees that they remain distributed. So rho continues to represent the probability density over time. And then each particle follows a trajectory which is governed not just by the classical potential, but the classical plus the quantum potential, right? So classical plus quantum potential, and then make a measurement in the end. And what happens, for example, and one can check it out. For example, if you have a double slit with some electrons, let's just say, coming out from the two slits, and so on, if the electrons are evolved by virtue of just a free Hamiltonian, so force is 0, you get straight lines, no fringes, right? But if the same electrons distributed are evolved by these two terms here with physical boundary conditions, one ends up with these fringes. Okay, so the point is that all quantum predictions are the same. They're correct. The only dynamical input is the Schrodinger equation, nothing else. No other input has been used. And the reason I'm kind of giving this example is this approach may not be familiar with everyone. If it is with you, I apologize and proceed. And in the classical limit, when you take h bar, this is also one of the simplest examples of of trying to go to the classical limit, because if you take h bar going to 0, these fringes disappear immediately and you get this picture again. And as one probably knows, this was one of the first researchers who proposed this, were de Broglie and Bohm, and it's used quite extensively in many branches of physics. So note that one curious and interesting fact is that this quantum potential, which is this, interestingly, if the wave function that's considered here, psi r is the real part of the wave function. If the wave function is a stationary state, then one can prove quite easily that the quantum potential is essentially exactly equal to the classical potential with a minus sign. So it's a valid picture. And again, these are the researchers one of the first to propose it. And so now we come to back to the Raychaudhuri equation derivation, and remember that this is the part that we set to 0 because of geodesics motion. And this is the part now, instead of setting it to 0, we must augment it by what we obtained from the quantum picture, which is this term here. So when you do that, we obtain a quantum corrected version of the Raychaudhuri equation, which looks like this. So on the right hand side, firstly, one sees that one has an extra term here, which could potentially be positive and thwart the convergence of geodesics into conjugate points. So let's talk a little bit about that. But before that, since I mentioned that for simplicity, when I tried to do the generalization, I used the non-relativistic limit. Of course, we have to do the most general relativistic limit as well. So one can start, instead of the Schrodinger equation, one can start with the Klein-Gordon equation, if one likes, and do the decomposition of the wave function in the same form, feed it back in the Klein-Gordon equation, take the real part and the imaginary part. One of the parts, the real part of the Klein-Gordon equation, in fact, gives rise, with the definition of the velocity field that we had done, suitably generalized to this particular situation, one gets the geodesic equation. Well, not exactly. One gets the left-hand side of the geodesic equation. The right-hand side is no longer equal to 0. So again, if we remember that it's the geodesic equation term, geodesic term in the Raychaudhuri equation derivation, which we had ignored or we set to 0, it's no longer 0. There is this extra force term here, if you like, quantum force or quantum correction term here. So this is essentially the corrected equation. And interestingly, if one puts in certain wave functions here, you can put in a Gaussian or whatever you like. And if you put certain test wave functions, one can see that this term turns out to be indeed positive for short distances. So there is a short distance repulsion between them. But one does not have to confine to a particular wave function because of the following. So let me, I just put this in focus. So this is the extra term. This is a positive term as one desires. This is wave function dependent, and the quantum term prevents focusing and formation of the conjugate points. Now, as I said, the reason for that is the quantum repulsion, of course, at short distance, but it's more even more fundamental than that in certain sense, because unlike the classical equations, for example, in the quantum equations, to obtain the so-called quantal trajectories, which are integral curves of this equation, which replace classical geodesics, this is a first-order equation. Therefore, the geodesics don't cross. Okay, not geodesics, the quantal trajectories, I should say carefully, do not cross because they are first-order equations. So it just follows that they have unique solutions. So there's no focusing, no conjugate points, and geodesics can go on forever. And when I say no singularities, I just mean in the sense of the fact that the singularity theorem ceased to be valid for this quantal trajectory. So if one replaces the geodesics by quantal trajectories, not in any straightforward way, the singularity theorems are valid. So that's one of the conclusions from there. Now, the next thing is, of course, one would like to apply to cosmology because from Raychaudhuri, well, one of the equations of cosmology is the Raychaudhuri equation, so one of the two Friedmann equations. The way it turns out, again, one of the first places where I saw this correspondence being made is by almost a 50-year-old book by Raychaudhuri himself. And this is the cover of that book. So one starts with the standard FL, the Friedmann-Robertson-Lemaitre-Walker universe, and this is the scale factor. As we know, we assume that the scale factor is 1 now, just by choice. And the way to go from the Raychaudhuri to Friedmann is one identifies the expansion in Raychaudhuri with essentially the log derivative of the scale factor times some number. And of course, one replaces, assuming that at large distances our universe is described by a set of perfect fluids, one replaces the curvature term by Einstein equation essentially, right? And when one does that, one inevitably lands up with the Friedmann equation, right? So this is the Friedmann equation. However, now if we start with the same FLRW universe, now the Raychaudhuri equation is no longer this, but you have to add this term here because it follows directly from the corrected Raychaudhuri equation. So what one does here now is instead of theta, we replace it by the log derivative of the scale factor, but this extra term doesn't go away, it remains, right? So that extra term in the quantum corrected Friedmann equation, this term shows up in this particular way. So this is the extra term here. Suggestively, again, it is to be proven, but suggestively, I write it as 1/3 of lambda sub q. Q, of course, stands for quantum. And there's a possibility that this might be a term which contributes to a cosmological constant. Therefore, I write it this way. And it is wave function dependent. And one of the consequences of this, again, because now the quantal trajectories, which are the trajectories of, let's say, a speck of dust you carried forward, backward in time towards the initial singularity or towards the future, the trajectories will no longer cross for the same reason. Therefore, the converges into a single point that doesn't occur, right? And in a way, it's not that surprising because we know that the universe has been it started from very small and things like that. But once we go to the very, very small regime, quantum effects need to be taken into account. So like naively extrapolating it to a point, like, you know, we never really expect that to hold good. So, so this extra term is there. Now, before we see what we can do with this extra term, let me just, like, you know, give a very quick one slide review of, you know, something which is, I'm pretty sure it's very well known to this audience, but just to put things in context. So, for example, in cosmology, this is an old picture, but it kind of brings on the point, is that if one plots the luminosity distance versus, say, the redshift for standard candles such as type 1a supernovae, then one can see that the curve is best fit by this theoretical model where you have a dark energy or a cosmological constant, which is about 70% energy matter content budget of the universe at this epoch, at the current epoch, and about 30% matter, out of which about 25% is dark and 5% is visible, which is shown here. Now this is well known, and this is, you know, one of the, I would say, argue most important discoveries of the century, I would say, as a fundamental constituents of the universe. And it also shows that at large distances, the universe is really simple. It's very simple. It's just two kinds of matter, flat space, and GR. However, as we also know, there are lots of questions which come associated with these observations. Well, for example, what constitutes dark matter? What constitutes dark energy or a cosmological constant? Why is the cosmological constant positive? Why is it so tiny, about 10 power minus 123 or 124 in Planck units, right? Whereas if one estimates it from quantum field theory, for example, the discrepancy is ridiculous, right? The discrepancy between theory and experiment is at least 10 power 50, and it could be as high as 10 power 120 or something like that. So there is clearly something which needs to be understood there. And currently, there's also the question that currently the dark matter density and the dark energy density, or the density corresponding to the cosmological constant, they're almost equal. They're like same order of magnitude. And also, they're also of the same order of magnitude as the critical density, which is about this. And the question is why? There's nothing wrong with it, but, you know, so we must be terribly lucky to be living in an epoch where these two are about the same. So this is also sometimes called the coincidence problem. I mean, it seems like a huge coincidence, that's for sure. Now, so with that, I propose what our proposed model is. So we propose that as a viable candidate of dark matter, we propose that it's a Bose-Einstein condensate. It's a macroscopic Bose-Einstein condensate stretching across cosmological length scales, and made of very light bosons. And the motivation is as follows. Of course, it all depends on what we get out of it. We can, I mean, propose anything that sounds reasonable. So the reason why it sounds reasonable is that Bose-Einstein condensates of BECs by definition are very cold, right? They're dark because they hardly interact with anything else. And if these are made up of very light bosons, then one can show that there is a very low chance of having small scale structure of this quantity, say subgalactic scales and things like that. So that's a plus. And Bose-Einstein condensate is one of the very few quantum systems which is quantum and macroscopic. It's a purely quantum system, but it's not a microscopic quantum system. It could be as large as you want, really. And the thing is that a Bose-Einstein condensate, if we assume that it can provide a viable explanation of dark matter, we'll see that the quantum potential can also contribute to the dark energy budget. So that's the interesting thing, in my opinion. So Bose-Einstein condensate at dark matter, there are lots of very competent authors and who have proposed it before us. So that's not new. What we proposed, and one of the earliest, to the best of my knowledge and that of my co-authors, is the fact that, or the realization that it can also give rise to a quantum potential and dark energy. Anyway, and the last point is, of course, it has very few assumptions and very few parameters. So the first question, of course, is if a Bose-Einstein condensate can actually form in the universe or in the early universe. So to do that, we do a critical temperature calculation, because we know even in the lab, right, Bose-Einstein condensates can form at, let's say, 1 degree Kelvin, well, not even smaller, right? It's a few degree or millikelvin or whatever, because the critical temperature is of that order. So the bosons must be below a critical temperature. So we do a critical temperature calculation, and the critical temperature calculation, these are standard results. So I don't like write the origin of this. The standard statistical mechanical calculations. So the interesting point is that there's a density, there's a number density here, which if we replace it by the critical density times a factor, because the dark matter is about 25%, and with the appropriate expansion factor of the universe and do the calculations, the critical temperature turns out to be this. So it's about 1 over m power 1/3, where m is the mass of the constituent boson electron volt, 1 is the scale factor. And comparing it with the ambient temperature of the universe, which is about 3.7 at this epoch, so divided by A. So once we do that, we can see here that as long as the mass of the constituent boson is less than a few electron volts, the critical temperature always exceeds the temperature of the universe, which means that the BEC can indeed form and should actually form in the early universe, provided there are an abundance of light boson. So that's an assumption, but subject to that, the critical temperature certainly remains much smaller than the ambient temperature of the universe. So it can form.
5 minutes left.
I'm sorry?
5 minutes left.
Okay, 5 minutes.
30 minutes.
5 minutes to 30 minutes, right?
Yeah.
Okay. Thank you. Okay. Thanks for So right. So the Bose-Einstein condensate can form. Now now we want to look at the Bose-Einstein condensate's macroscopic wave function. And again, subject to proof and everything, let's assume that the macroscopic wave function, is a Gaussian. Let's just assume it for the moment. Okay, I'll argue justify later. If we simply put this in this expression which we have here, a macroscopic Gaussian wave function, indeed, the extra term turns out to be a constant. Okay, and if it's a constant, we just call it lambda, right? If it's a constant, whatever the value is. So how do we justify the Gaussian wave function? Well, 2 quick slides, and I know I have about 3.5, 4 minutes. So the first one way of doing it is space is really flat, right? Space is flat, and the curvature of space-time is also like almost 0, as you can see here. Therefore, Newtonian cosmology approximation is a good approximation. It's an approximation, but it's a good one. So assume a sphere here in the cut out from a co-moving sphere with dark energy filling inside, with a test particle outside. Then the matter that's inside the sphere is the only one which contributes. So when we do that, we write every length scale is scaled by a scale factor, right? So when you do that, long story short, we do get the Friedmann equation, which for if we don't stretch too much in the past, then indeed this equation, as you can see, it shows that we have essentially a harmonic oscillator trap. Okay, and it's valid so long as I said, we don't go too much far back in the time. And of course, since it's a harmonic oscillator, approximately the wave function would be Gaussian. So our assumption of the Gaussian wave function is not out of line. So we assume it is a Gaussian, and of course we can calculate corrections to it. And again, I'm looking at my clock, so I will not go into the detail, but the long story short, you can calculate first order corrections to what we got. So you can assume that the scale factor is constant over a certain period of time, plus a slowly varying factor, and do all the calculations. And again, in the end, what we get is this particular value of the wave function, or this particular form of the wave function, is valid so long as we don't go too far in the past. Too far in the past meaning like the time that we look back is much smaller compared to the Hubble time, for example. So that's how the wave function, at least approximately, is valid. And then if we get back to this wave function, we put it back in the quantum potential term, which translates to a lambda q. As I said, I suggestively wrote as lambda. You put it back here, then calculate the density of lambda, like the density corresponding to lambda, which is lambda over g. We get almost the same order of magnitude as the dark matter density. And the reason, of course, as I said, the underlying reason is that curious observation which I stated, which is that for stationary states, which it is, a Gaussian, the ground state is a stationary state, the classical and the quantum potential is approximately equal and opposite to the classical potential. So I would like to summarize. So the questions we asked are the following: that what constitutes dark matter? We propose that it's a Bose-Einstein condensate of very light boson. What constitutes dark energy? And we showed that that same BEC inevitably, if the matter is like the bosons are light enough, the critical temperature is high enough, therefore such a BEC should form, and the quantum potential of that indeed gives rise to, for a suitable choice of the wave function, indeed gives rise to a positive, like a positive constant in the Friedmann equation. Why is it positive? Because essentially in this picture, negative gravitational potential gives rise to a positive quantum potential, and vice versa. And why negative? Because gravity is attractive, of course. And why are they two equal? Because again, as I said, that the quantum potential is approximately equal to the classical potential for stationary states. So a few quick remarks, which is, we don't get like, in observation, rho lambda is about 3 times rho dark matter, right? We don't get exactly 3 for a couple of reasons. One of them is like, the dark matter starts decaying immediately, and it's incorporated in the wave function. And secondly, we assumed all the bosons are in the ground state. No, so that's another source of corrections. One can precisely calculate the fraction of bosons that are not in the ground state. So that would give rise to a mixing wave function and corrections. One of the predictions is that we need an ultralight, an abundance of ultralight bosons. We don't know what they are. They could be gravitons, axions, could be a new particle, but that could be taken as a prediction. And an interacting dark matter, dark energy model, that's something which we're working on. And the last thing is, another of the predictions is, since I mentioned that my calculations hold good only if you don't go too far back in the past. So that strongly indicates that the calculations or the results would change. And in the far past, the cosmological constant might have a different value as well. So I'll stop here and thank you for your attention. I'll be happy to try to answer any questions to the best as I can. Thank you.
Okay, thank you, Saurya, for your nice talk. I see that we have time for a couple of minutes. So we'll start from Nikolaos.
Okay, thank you. Saurya, can I ask the following question? You said that...
of course.
I want to ask, the Raychaudhuri equation assumes a lower bound on the energy conditions, right? The null energy condition or something like that. I don't remember. Is it true, though, that the Raychaudhuri equation, to be valid, you have to have lower bound? One of the several Hawking and Ellis kind of energy conditions, right? Is assumed or not? I don't remember.
It's a great question, and I can answer at various levels. So let me just give the main thing, and then we can talk later, whatever. So Raychaudhuri equation per se is a statement in geometry. It's an identity, right? So everything is geometry. The only place where, as I'm sure you know, the only place where gravity, like the Einstein equation, enters is the last term when you replace the RAB by the and then of course. It's absolutely. So when we integrate it, if we want to assume that the right-hand side all terms are negative, then that shows that there will be a condition on the stress energy tensor as well, right? So we could start with the softest or the weakest condition, if you like, which is the weak energy condition. So even with that, the conclusions of the Raychaudhuri equation would hold good. So
my problem is this: that, as you know, at the quantum level, all energy conditions are violated, all of them. This is Epstein, Glaser, and Jaffe in 1965. And therefore, that may mean that if you do not choose wisely, essentially Schrödinger equation that you are writing, you are doing essentially, you are writing a Schrödinger term, right? To generalize the Raychaudhuri equation, then you do a polar decomposition of this. Then there is always the possibility that you may end up with something having essentially a quantity that gives rise to infinitely negative sectional curvature, and if that happens, then essentially, or positive curvature, then everything is going to collapse. That's what I'm afraid of, that you have to exclude probably some states that will essentially force, despite all basically geodesics, to pass through the same point, therefore they will result in geodesic incompleteness.
Yeah, well, yeah, so with the quantum energy conditions, I agree that the energy conditions are, that one normally states are classical, and quantum is very likely, to violate some of them. My take on that is that would further reinforce the non-convergence of the geodesic results. So it would not spoil it. It would because any violation would negate the conclusion of the Raychaudhuri equation. And that's what we want. We want the negation of the Raychaudhuri equation results. So, but it's a good point, and I'm happy to think about it further. Absolutely. So thanks.
Thank you.
Yeah.
Okay, so we have another question from Sugato.
Hi, Giorgio. Very interesting talk. Very interesting approach. Yeah.
Thank you.
I'm just wondering. So I come from the quantum mechanics side. So the de Broglie-Bohm approach that you used. It's equivalent to standard quantum mechanics, right? So why didn't you take could you not do the same problem by taking an initial wave packet following same
Probably. Yeah, it's a good question. Probably. So let me in a few seconds explain why I did that. So Raychaudhuri equation, as you probably have noted, like it's basically a derivative of the velocity field, and then you do some algebra. Very important algebra, but essentially that's what it is. So I was looking for a quantum version of the velocity field, and of course I spent a lot of time on that kind of thing. But then I realized it was already there. So the de Broglie approach, it starts with the quantum velocity field approach. And the interesting good thing is, like, you can always go back to the classical simply by taking h bar going to zero limit.
That is true. Yeah.
It doesn't solve all problems of quantum mechanics. It doesn't solve all the problems of classical limit. But in this particular aspect, I think it's very useful for us. It gives a physical picture. It gives a fluid picture, a quantum fluid picture, which replaces the classical fluid picture. So that was the motivation. But yeah, it's equivalence. I'm sure it can be done in
I mean, one reason people try to avoid it in general is that because it's a very non-linear, difficult to solve equation, right? But I guess you are just obtaining positive, negative constraints rather than really. Are you solving them also in some case?
Not integrating in the sense of solving. So but we do compute that extra term with a suitable choice of physically motivated choice of wave function. So we do some explicit evaluations, but we don't solve in the sense of integrating it. No. So.
And does your approach help to explain things like black holes as like a star, like some kind of repulsion, quantum repulsion balancing the collapse force?
Yeah, I don't know, but it's definitely worth checking.
Okay, thank you.
Thank you.
Okay, so Roberto, you will be next, but first, since now we can start with the discussion session, there was already a previous question for Petr by Alexander. So if Alexander is still here, he can raise his hand, and then I can unmute him. Then we will go back to you, Roberto. Okay, so okay, this is for Petr.
Okay, great. So it's a very interesting conference. So thanks, guys, for organizing it. I have a kind of general ideological question to all the guys who are doing generalized uncertainty principle. And the point is the following. So especially in context of quantum gravity, the first thing we learn from Unruh effect is that particles actually are observer-dependent objects. Moreover, we know that even in normal Minkowski quantum field theory, there are no uniquely and well-defined proper operators which would correspond, which could be built out of fields and which would correspond to coordinate and moment of a particle. I mean, in general, proper relativistic setup, these interactions, and so on. So talking about quantum gravity, I think what would be much more natural there to investigate is any corrections on uncertainty relation for quantum fields. And this is much more exotic, but actually much more well-defined object, right? Because fields are exactly the dynamical variables for which you do have the commutators and Poisson brackets, whereas these X and P are not even clear for which objects they are if you follow the logic that people would tell us particles don't exist from the Unruh perspective, right? So we don't even know what this X and P and which particle do we mean and what are the states and so on, especially if we are going to a regime when the quantum gravity corrections are important, right? So I'm just wondering, has anybody tried to look at modifications of uncertainty relation for quantum fields?
No, but I think if I can say, It's difficult because fields cannot be mostly measured. You cannot measure fermionic field. What is even worse, you cannot measure conjugated momenta to field. How you would measure it?
Oh, Peter, if I sorry for the interruption, but actually conjugated momentum for in normal electrodynamics, conjugated momentum is a field.
Electrodynamics, yes, but electrodynamics is one of extremely few exceptions. How you do it, for example, for a scalar field? How you measure, for example, something like Higgs field?
Oh, but it's the same.
You measure only Higgs field through excitations. You never measure directly field.
But it depends on proper experimental setup. From the point of view of formalism, we apply commutators.
No, in quantum, if you do particle physics, you are always interested in S matrix. S matrix is not formulated in terms of field; it's formulated in terms of particles.
Absolutely, absolutely. Yeah. But S matrix does not exist even in cosmology. We don't know how to formulate it in gravity
of course,
in general.
But GUPs are formulated in first quantization. So it's never formulated in second quantized version. So for first quantization, of course, you make just projection of the field operator into single particle state. That is a relatively well-defined concept. Single particle is well-defined in gravity as well.
But what is with UNRU in that case? I can fly through
UNRU is second quantization. So you need, of course, you need vacuum state. You need but problem is that you need ensemble. You need vacuum state. You need to do Bogoliubov transformation on entire vacuum state. It's a completely different thing. It's not about single particle picture.
Absolutely, absolutely. But the point is, we do know. Look, whole inflationary paradigm is about how to transfer quantum fluctuations of the inflaton. It's a field into the observed thing. So basically, it is what we do observe on the sky.
Fluctuations of the field, that's right, but you don't observe the field, you just observe quantum fluctuations of the density fluctuations due to the field. It's a very different thing. You really, in particle physics, you really never go to fields as a fundamental observable objects. And in fact, many fields cannot be observed per se, like gauge fields, they cannot be observed. You can point this that it depends. All particle physics is modern particle physics is based on Yang-Mills theory, so it depends on your choice of gauge. So gauge fields are per se not observable because they are gauge dependent. Fermionic fields are not observable because they are Grassmann variables, which are not observable. So you basically end up you just end up with very few things which are observable, but fields are things. I mean, nobody is still in particle physics very much interested in fields per se.
Right, but we are doing quantum gravity, and
but I mean, metric field is also not observable.
Gravity, the best manifestation of
metric fields is not observable.
But exactly, but you see, what we do observe on the sky, they are directly transferred quantum fluctuations of the inflaton together with the combination of all these objects. And we do observe them.
No, we don't.
Equation, right?
We can observe the fluctuation of the metric field, which should be gravitons, which we still do not observe. So even in this case,
no. But you see, the interesting thing is, when we do inflationary calculations, if we do not quantize Newtonian potential together the matter, which induce Newtonian potential. In reality, there is no way to obtain standard inflationary results if we do not quantize Newtonian potential, if we don't combine Newtonian potential with the inflaton field fluctuation. There is no way to do it. So you see, that's why what I'm wondering about, it's, of course, the gauge issues, it's not clear what to do with fermions, that's true, but in reality, the things on which we write commutators, they're not coordinate and moment of a particle.
I think you should set up something that is operationally possible, like variance for a wave function of single particle. What is variance of field? How you can operationally measure variance of field?
Look, there are devices which measure B and E. Am I right?
Yeah, but that's the only thing which you can do. But typically, very rarely you formulate quantum electrodynamics in the language E or B. You typically go into something that is much easier transformation with respect to Lorentz group, actually a linear representation of Lorentz group, but that's the gauge field, which is totally non-observable.
Sure, sure. But you see, the point is, it's our desire to write a particular variable, which is good to write an action principle. But there is no doubt that F mu nu is unobservable.
Yeah, but then you would basically need to go into gravity and identify observables. I mean, in electrodynamics, identify observables, it's easy, it's EB. But then,
yes.
Then try to do that for gravity. I mean, that was precisely, that's the program of loop quantum gravity, to identify observables.
Sure, sure. But you see, at least in linearized gravity, there is no problem to define the things, right? In linearized gravity, we know how to do it. Moreover, you see, surprisingly enough, people in cosmology, when they talk about Newtonian potentials, that's exactly what we do observe. These are the perturbations which we measure. Now, in all these cosmological observations, there is no doubt that it's related to the Newtonian potential which we do quantize in linearized regime. So you see, that's what I mean. I mean, like if I fix a gauge, if I take conformal Newtonian gauge in cosmology and do perturbation theory, I definitely do know that my Newtonian potential is in one-to-one to the matter which is there. And if I quantize both things, then I should include the quantization of this Newtonian potential. And that will be my observable.
Yeah, but it's gauge dependent, because if you choose gauge, it's your choice. Gauge dependent things cannot be observable.
Yeah, but then they can contribute to things which are directly then observable. That's the point.
That's right.
Fluctuations of temperature, they are observable. And then if you do correct calculation, how...
But that's true. And you should have, you can have thermodynamic uncertainty relations. They exist, of course. They can be formulated in terms of fields. That would be perhaps...
Yeah, but that's a bit different story, right? Because on the other hand, we do know that, for example, Casimir effect, right? One of the best examples of quantum fluctuations. There are no particles there involved at all. But there are fluctuations of fields, and exactly that's why the whole thing is measurable.
Yeah,
in a sense. So you see, I was just wondering because it's a very interesting activity, and I have some friends who are doing it and interested in that. It's all great, but the very point that we don't even talk, even we use a completely direct formalism. So basically, our quantum field theory is just nothing else as a continuum Hamiltonian system with the same commutation relations, the same Dirac procedure, at least for real scalar fields. That's 100% sure so. And then suddenly, we switch to do this single particle state, but taking into account that we are supposed to talk about huge curvatures, then we will produce thousands of these particles. We would not be able to identify which one are we measuring, which coordinates of whom are there. Because this one particle Hilbert space would not be properly even defined for huge curvatures. Because, in cosmology, curvatures are not that huge, but in the early universe, we would produce tons of these particles, and then it would not be possible to look for them where they are. So I was just wondering, maybe, it's worth to generalize this setup and look at what are the fluctuations of fields.
May I answer to this as well, please?
Sure. It's a discussion.
So just so to say, you mean to modify the commutators in quantum field theory in a similar way to the generalized uncertainty principle? But in fact, this would have a completely different meaning. The generalized uncertainty principle has as a meaning that it is like it has, or from it you can kind of it yields basically a minimum length. That's what you want. So the generalized uncertainty principle doesn't only exist for itself. You just want to have a minimum length in quantum mechanics, and your generalized uncertainty principle is what gets you there. But if you do this for quantum fields, you have no interpretation of what this modification in fact means, because what you get would be, I don't know, like for a scalar field, something like a minimum field value, this is just very heuristic. But you don't have the same result. So there are ideas of introducing minimum length scenarios into quantum field theory that does exist. And there are also papers which have modified commutators in quantum field theory. This also exists, even though I'm not myself not a huge fan of that, exactly due to the argument I gave before. But that's a different thing, because that's usually, you know, similar to these kind of non-commutative geometry kind of ideas. That's where you get there. But it's not as simple as just, you know, modifying the commutator for quantum field theory, because you will have a completely different result. It will just, you know, physically not be the same situation, right? That's just.
Oh, look, with that I completely agree. It's not the same situation, because first of all, in order to even formulate the uncertainty relation for quantum fields, you would need to smear them up, following, like, let's say, formal Weitmann arguments, but let's say being a bit maybe more primitive in a sense and going to a Cauchy hypersurface, you would need to smear them on this Cauchy hypersurface and filtering them out in order to produce out of distributions proper algebra of operators, which are operators and not distribution valued operators. But after you're done with the smearing, there is no doubt that you would introduce uncertainty relation to that. That's pretty easy, actually. And that's direct. If you want, it's a direct consequence of your formalism.
I think I could agree with Alex in one thing. If you go to Planck scales, which are typically much smaller than typical Compton wavelength of a particle, then the single particle picture is lost. I mean, it's well known that if you localize particle below its Compton wavelength, then it's impossible to speak about single particle. Suddenly you get multi-particle. Minimally, you have pair formation, which means that in this respect, GUPs are a little bit inconsistent, because you cannot sensibly speak about single particle picture at the Planck scale, unless the particle is so heavy that its Compton wavelength it's shorter than Planck scale. But that's not true for most particles. So in this respect, GUP, as it is formulated, it's not entirely logically consistent. It's tenable only under assumption that you still sensibly speak about single particle picture. Either your particle is very, very heavy, or you are very, very far from Planck scale. So in this respect, of course, it would be sensible to sort of use field theory. But there is, of course, as I said, there is this drawback that with field theory, which would be much more natural for the distances which are comparable with Planck scale. We really don't have operational meaning that we would be able to give to such uncertainty relations. So it's very difficult. That's actually all the reason why Unruh was trying to make operational meaning to vacuum state by his single particle probe or detector. It's a very difficult to make really operational meaning to quantum fields in a way that the primary object is field and not the excitation. So
yeah, of course, because in reality it boils down to even the point that, let's say, in the case when there are definitely fields like B and E, we actually probe them through wires, and that implies that we probe them through fermions, and that's what is. So basically, there is always a mediator in all these measurements, and that's a hard story to address. But formally speaking, if you just follow the formalism, we can definitely do that. I mean, and that could be actually an interesting story, because smearing fields over Planck lengths. So clearly we cannot smear fields on scales shorter than Planck, because that would not make any sense. But maybe if you smear them on scales larger than Planck, or I don't know, make some uncertainty in the smearing over like Planck lengths, that could be actually an interesting story.
You're right. That sounds really interesting. In the commutator, just replacing the delta function basically by a Gaussian or something like that, which in the limit
absolutely.
Yeah.
You know what?
I think fields are not good things to work with. I mean, as you mentioned, it's good to work with observables. Something like, I mean, typical observable in field theory, like gauge theory, are non-local. Yeah. So, I mean, for example, Toft loop or other. Yeah. So. In those objects or in gravity loops, that's the reason why the spin networks were introduced, because because they can really be observable quantity or related to observable quantities. So in those observable quantities, one could speak about, or they can be formulated in terms of variances, and to find uncertainty relations for those objects would make operational meaning.
Absolutely,
Because,
absolutely.
Yeah. But that would be, of course, to work with non-local observables is, of course, by itself very, very, very difficult stuff. I think it would be quite challenging to, first of all, formulate that uncertainty relation, and secondly, operationally explain what you do, how to measure it in practice.
Sure, sure. But you see, there is another problem with that. If, for example, if you go to fermions, then clearly the things which are observable in fermionic fields are only bilinears.
Indeed,
but
yeah.
Definitely what we can observe is the energy momentum tensor, because at the end, neutron stars are built out of this stuff. And then the question would be, what is the energy momentum tensor?
I should say, energy momentum tensor cannot be observed either, because energy momentum tensor is defined up to 4 divergence of the tensor that has 3 indices, and first 2 are antisymmetric. That's sure. basically it's very frequently used as an advantage that you can define so-called improve energy momentum tensor. That actually makes the difference between this Noether theorem, energy momentum tensor, and energy momentum tensor, Belinfante's energy momentum tensor, which use general relativity. So you cannot observe energy momentum tensor either.
Well, then we cannot observe energy, right?
No, that's different. Energy you can observe, but energy momentum tensor not. Because energy momentum tensor is designed to satisfy conservation law. That can be satisfied by adding this 4 divergence into it. But of course, in relativity truly speaking, you cannot observe density of energy. That's true.
On the other hand, we know how to define energy momentum tensor uniquely by doing variational procedure.
You cannot, because problem is that this 4 divergence term is basically informing you about surface effect of gravity. And that's precisely what you don't know, because you don't know what is the global geometry of our spacetime. The only thing that you have is Einstein equation with local. You have absolutely no information about the topology of our spacetime.
Oh yeah, that's
the point which is embodied precisely in this 4 divergence. So you cannot know it.
But on the other hand, okay, let's think about it differently. If we do a geodesic deviation experiment, then we can locally probe the spacetime.
Locally, yeah.
Just a second, because I don't know if Roberto, because he had his hand raised for a long time.
Well, I think the discussion was going in a different direction. If I can repeat what I said today anyway.
But
the generalized, sorry, and then I'm sorry, but I have to go. I thought the discussion was open to everybody. If I don't have I can't talk. I'm sorry, guys, I have to say goodbye. It's up to you.
No, I'm saying, I saw that you ran.
Yeah, because I have to leave in 5-10 minutes. So
that's why I told you
you
can make your comments now.
So 2 comments. One, very quickly. The GUP is supposed to describe gravitational correction to the quantum mechanics of single particles. If we were able to solve quantum gravity at the Planck scale, we would not need to change the uncertainty relation for single particles. So this is just an effective way of looking at things. I don't think we need to change the commutator of quantum fields if we include gravity among them. The theory should tell us what to do. Second comment, I like very much what Saurya did. Sorry, did I pronounce the name correctly? About the Raychaudhuri Equation. I think it's a very interesting approach, and it matches with some of the things we found in a different way in the corpuscular picture. And have you looked at the connection between that and your approach, just for my curiosity?
What do you mean by the corpuscular picture? Can you elaborate?
Well, the idea that the de Sitter background is a condensate of gravitons, sort of similar to how we can describe black holes. And then the dark matter phenomenology comes out just as the back reaction of this condensate to the presence of matter.
Right. So I believe I'm aware at least partly of what you mentioned. It's really interesting. No, I have not looked at the details of the connection.
Well, unfortunately, I have not much time, but maybe we can find a time to discuss it in another occasion. Sorry.
I'd be very
Again,
happy.
there are several directions that point there that dark matter could possibly just be the back reaction of the actual quantum state of the universe to matter, and I think that's quite intriguing.
Yeah. I'd be delighted to discuss because I have thought a little bit about it.
Okay, thank you. Sorry, but I really have to go right now. Bye, guys.
Bye-bye.
Bye.
Ciao. Ciao, Roberto.
Okay. No, I saw that Roberto lowered his hand, so I thought that he had to leave. That's why I wanted him to just make his comment before he left. So, okay. Probably, I don't know if Fabio has something related to what we were already discussing, or if it's something.
I have a question for Peter.
Okay, okay. So maybe, sorry if I interrupted you, Alexander. Probably after Fabio's question, we can continue. Because we were accumulating other questions.
No, absolutely.
Okay, so Fabio, you can ask.
Okay, Peter, I get lost about the origin of your negative beta in your formula.
No, there is no, there are two possibilities, negative. I was not mentioning origin. I just.
Why you have the negative beta?
Because, I mean, because it's better behaved. It's better behaved for two reasons. First of all, our position operator is directly self-adjoint. In contrast to positive beta, where you have deficiency index 1,1, you need to self-adjointly extend it. And in fact, it cannot be extended uniquely. There is actually one parametric class of self-adjoint extension, which is quite mathematically troublesome. For negative beta, it's directly self-adjoint because the deficiency index is 0, 0. So it has better mathematical properties. Spectrum is continuous. In contrast to positive beta when the spectrum is discrete for position operator. Mm-hmm. So the continuity of spectrum it's precisely what I need, and in order I could set up these entropic uncertainty relations. Otherwise, I wouldn't know how to do that. So so it was just I would say technical convenience that I could progress and to get somewhere. And so I was just exploring how far I can get. And the fact that we got this at the end, we got this Mannheim-Casanas solution, which is actually, it's not just formally similar to Mannheim-Casanas, it is properly science in front of the linear and quadratic term, radius term, which would not be correct if I would choose beta positive. So I should maybe mention that this Mannheim-Casanas solution describes the rotational curves of galaxies without the need to invoke any dark matter or any bizarre type of matter. So in a sense, it's just the change of gravity, which by itself explains this modification of Newton's law, which by itself describes those correct rotational curves, which with positive beta I wouldn't get. So that is one indication. But strictly speaking, I mean, we were actually originally trying both. We started with positive beta, but then we realized that we get into many troubles. Mathematically, it's quite surprising because most people in community work with positive beta. Yes, but yes. Mathematically, positive beta is much worse than negative beta.
Very interesting.
Yeah, mathematically it's much more worse because, I mean, if you really, and problem is that if you have just symmetric operator, which you have, then you cannot guarantee, for example, that your spectrum is real only. Yeah, I mean, that's the problem. So that's the reason why you need to do self-adjoint extensions by appropriately sort of narrowing your definition region for the operator. But problem is that with the positive beta, it's a very ununique. I mean, as I said, you get one parametric class of extensions. You should pick up somehow which one you like most. So there is something like gauge freedom in the choice of self-adjointness. In the negative beta, it's immediate. You don't need to do almost anything. You just appropriately choose the definition region, which is basically the same as the symmetric operator region. And then because the efficiency index is 0, 0, you don't have, your spectrum is immediately real.
Understand? Yes, very nice. So and then from there you get the.
Then I can use my because the spectrum is real. I can define the entropic power, because entropy power originally even by Shannon was defined only for entropies with the continuous probability densities. That means for random variables that are continuous. So entropy power is actually possible to be defined only for continuous variables, because if you do manipulations with the probability density functions, you need to do change of variables. And this can be done easily if you have continuous variables, but it's almost impossible to do that if you have discrete variables or discrete spectrum. So it's that's the reason why we at the end, despite of starting with positive beta, we ended up with negative beta, because it was mathematically better behaved and provided sensible results as well.
Yeah, very nice. And then you get the rotational curve of galaxies.
Yeah, we get rotational, and in addition, of course, we can, as you know, we already did the paper also with negative beta. You can make connection with the Magish-Smolin double spatial relativity, which is also negative beta.
By the way, there are no connection with some lattice structure of spacetime as we did in our paper.
I don't know. Problem is that commutation relation, as you have them, they have many realizations. If you are assumed that you have differentiable structure of your Hilbert space, then the natural realization is in terms of differential operators. But our representation of commutation relations was in terms of difference operators. So it's different representation of commutation relations, which was much more suitable for the discrete, Hilbert space over discrete configuration of space. Because I assume everywhere that I work with differential operators, I cannot really invoke a priori discrete structure because I am assuming differentiable structure. But of course, we know that the negative beta is also present if I work with Wald crystal, because the discrete structure automatically dictates. It's very interesting, because if I have discrete configuration space, the negative beta appears automatically naturally if you do properly quantization on discrete space, configuration space. You really don't. The negative beta is an automatic consequence of discrete structure. You don't have chance to have positive beta.
Yeah. If you formulate things on a lattice commutator, I mean on the lattice, then you almost immediately go to negative.
That's right. Yeah. And in fact, on lattice, you have those two beautiful regimes that if you have small beta, so if you are close to momenta being 0, then you really get the usual the usual GUP uncertainty relations. But if you are close to maximal momenta on lattice, which is close to first Brillouin zone, then you really get that the commutator might vanish. So you get into classical regime. So it's interesting, because at maximal energy you can achieve, which would on the Wald crystal would be precisely Planck scale, then physics becomes classical, which in a sense is fascinating. That was the original idea of Toft. Then you would like to precisely at the regime when classical and quantum world are merging, you would like to have classical physics. So that's in that case, all those problems with quantization of gravity would be basically spurious. That was the original Toft idea.
Yeah, sure, absolutely. Okay, thanks for the.
Okay. So, Alexander, do you still want to continue? I can unmute you because.
Well, we can, but I don't know, it's not too late, guys. We can always discuss, and I presume with Petr I could even discuss in person, maybe at some moment, because we're in the same city.
That's entirely true, yeah.
I mean, we can also continue discussion. Probably, if you want, you can still stay here with us. Then we see. I mean, now let's see. Okay, Fabio, will lower your hand so that I can check how many other questions.
Let me lower my hand somehow.
Okay, I can. Okay, so now.
Can I just add something to what was said before?
Okay.
As I said in the framework I was explaining in my talk, this was actually happening as well, right? Just from the other point of view, when there were these closed manifolds, you could have a vanishing uncertainty relation, vanishing uncertainty for momentum. But that was, I think, a topological effect. But you could imagine something similar happening in this place anyway.
Yeah, there's more than one way in which you can get a vanishing commutator.
I think, if I may add, that is, despite of the fact that this GUP uncertainty relation, which has the modification only in the square of momenta or square variance of the momenta, it's very popular. It's from mathematical point of view, it's not very convenient, because it basically make X and P asymmetric. You know, in conventional quantum mechanics, commutator X and P is just constant, so X and P are treated on equal footing. While if you just emphasize P, you are losing to symmetricity. This is actually repercussions if you try to look for coherent states, because I mean, what would be much more natural to also add the same term for dx, like
but indeed,
quadratic terms for dx, because in that case, the coherent states for momentum and position would be completely identical. Similarly, as they are identical if you have just conventional XP commutation relation. In both cases, for conventional case, coherent states are always just Gaussian, or both for position and momentum representation. Here we have the coherent states being Tsallisian only for momentum representation, but not for position. So because the disparity in treatment of position and momenta. So from a mathematical point of view, if I would like to have parity and I would like to have something that is on the same footing with the classical physics, then I would emphasize also that I should have similar term with the position, and then both would be coherent states with Tsallisian distribution function. Here it's here it's only for momentum.
Yeah, but indeed, on the original formulation, also in the first papers, for instance, the one by Kempf, also previous to the one of 1995, the treatment, I mean, the original modification of the uncertainty relation accounted for both delta x square and delta p square.
Yeah, because as what I was showing, if you have, yeah, I think, yeah. In fact, you have. You have different constraints, because if you have dxp, if you have dx squared, then you basically have constraint, or I think Hubble radius. While if you have dp, then you have the scale which is related to Planck scale. So if you have dx and dp both present, then you basically make take both those fundamental scales into account. While if you have only dp squared, and you just take Planck scale into account, you don't take the Hubble radius into account.
Yeah, sure. You have two scales with but I think I mean the formulation of Kempf and Mann and so and I think was mainly dictated from by symmetry. I mean, in order to have a symmetric.
Yeah, but as for instance, also we have seen from the work from the talk of Fabian. Well, actually, you can ascribe the modification associated with the momentum to UV corrections, and the modification associated with delta x square as PR corrections.
That's right. Yeah, that's right.
So in a sense, they're not in conflict in this sense.
No,
I mean,
particularly in a small universe, when Hubble radius might be comparable with Planck scale.
Right, but I think here it's very important that in that case we are losing the major think about normal classical mechanics, namely canonical transformations and equivalence, exactly as you said, between X and P. In reality, if we follow just normal Hamiltonian paths, there is no difference between them in some sense. So therefore, every correction, I would say, should also kind of respect this symmetric property. Kind of naively, it would be nice if there would be something like Hamiltonian or something, but of course, it's a bit maybe too crazy to say that it's the Hamiltonian which is appearing there. But yeah, it would be nice to have something what is symmetric and X and P.
Yeah, but indeed there are also justification from both sides, as I already said. So I mean, the most generalization should account for both of them, not only for a question of symmetry, but also for more practical and physical reasons.
Yeah, there are mathematical reasons and also physical justification, so to say, interpretation.
Yes.
Physical interpretation of the mathematical beauty of symmetry, so to say, to have X and P together.
Yeah. Okay.
By the way, I presume Elias Vagenas left, right?
I don't know. You can check in the list. But in the meantime, sorry, Fedele, because I unmuted you something like 10 minutes ago.
I was listening. I don't want to interrupt the discussion, since as long as the discussion is going, it's good. Because I have a question, really, to not anyone in particular, or the people that know about this generalized uncertainty principle. Now, if I have the usual commutator of usual commutators, I can find them with a while map. Namely, I can take P and Q and then associate operators, and this I can do in various ways, ambiguously. In general, the while map is sends symmetric into symmetric and L2 into L2. I just don't know, probably I should. Is there something similar, so some sort of map which associates to function, not only coordinate functions, but any function, operators, so that in the end you find that your Mangano-Kempf and Mann uncertainty relation. Is there something such work?
No, it's maybe even worse than you are asking, because in quantum mechanics, you have typically von Neumann uniqueness theorem, which tells you that all representations are unitarily equivalent. Here, you don't have anything like that even. So you cannot even be sure that if you find some representation, that the representation is unitarily equivalent with any other representation you find.
Well,
so
one is enough.
Yeah, one is enough. Yeah, but that's the problem, because in quantum physics, you would like to have sort of unique represent. Of course, in quantum mechanics, we know that in quantum mechanics, you can also spoil von Neumann uniqueness theorem by having non-trivial topology in the configuration space. But in the normal configuration spaces, von Neumann uniqueness theorem works pretty nicely, while it doesn't work in quantum field theory. And that's the reason why we have, for example, renormalization. So in the moment when you would...
electrons and all this. But I would be, because for Kappa-Minkowski, for example, there are such maps. Then there are these things, because this just makes a quantization procedure so that you have the algebra of functions on P and Q. Now, in general, people do it for the algebra of functions on space-time. Now, this is phase-space. So one has all the observables of space-time, and then associates to them operators. So it is if it's not unique, and if it's also not unitary equivalent, I can live with it, but there can be ways to discriminate. For example, you would like to have to send two functions, density, probability, into good matrices, density matrices, and so on.
But the Wigner approach was based basically on the fact that you know that position and momentum operators are self-adjoint but unbounded. So he wanted to make bounded operator, because for bounded operators you have many theorems. So he created exponent of those unbounded operators, which are unitary operators.
Yes.
But in this case, problem is that operators are originally not even self-adjoint. So there are various ways, I was just saying, that you can have many self-adjoint extension of the same symmetric operator. So that means that you have many unitary operators that are related to that particular self-adjoint operator. And so all this Wigner program is failing in the sense that you don't have unique unitary representation.
I'm a lover of self-adjointness and self-adjoint extensions, and the fact that there are ambiguities, because Aharonov-Bohm, all these things. So I'm seeing in this GUP, which I didn't really study very much, I see a very interesting set of things in which doing while quantizations can be interesting, let's say, useful. So So you are telling me that
it's better. While is better because you directly work with unitary operators that are bounded. So
Yes.
boundedness is what makes this program going. Working with unbounded operators is dirty because you don't work on Hilbert space. You work on something which is a space of tempered distributions. It's nasty. So it was very clever trick how to put things back on the conventional Hilbert space of Wagner. This trick of Wagner was a very convenient trick.
Yeah, so I wanted to see if somebody has played some Weilish, Wagnerish trick in this, and it seems that you are telling me no one has done, basically.
No one done it really in this way, at least not in GOP community, as far as I would know.
No,
it's dirty. It's very dirty, and start to be dirtier when you put more correction terms on the right hand side, because the proving. I mean, we were proving with my colleagues. We were proving self-adjointness of the operator. Really, to prove if the operator is self-adjoint, really calculating the deficiency indices. You spend really a huge amount of pages just doing this type of reasonings. So it starts to be extremely complex question if you have much more complicated.
No one has done that. You are suggesting me that I don't do it because I would be.
You can do it, and you would be first, and everybody will be quoting you.
Okay, thank you very much.
Okay. Well, there are no other answers.
Maybe could I ask Saurya, because I hope I pronounced that name correctly, because I like the idea that you are getting this quantum potential through the usual bomb de Broglie wave pilot basically approach. It's this, or that was basically done before even by Madelung. This is basically the Madelung way how you, yeah. But it's also well known that it works only in non-relativistic framework.
Well,
if you try to go to relativity, then that's the reason why all this program stopped. Basically, that was the most fierce critique, as far as I know. It's that you cannot relativistically generalize this bomb de Broglie program, mostly because if you define p squared, you get a negative mass squared. That this dynamical mass starts to be negative, which is non-physical. So it's basically you can have tachyons in the theory.
Right. So I'm aware of that, and if I can respond to that, so part of it is founded, and part of it is a bit of kind of. I think the interpretation is not quite right in my opinion. So traditionally, of course, I agree with you on the Madelung and Madelung transformer. It was done much earlier. Absolutely, I presented only the main references. But coming back to your point, so depends on what one wants to do with it. So one of the raison d'etre for the de Broglie bomb pilot wave was to actually have a physical picture of the trajectories, and it works and all that kind of, which is great. So indeed, if you do relativity, there's no guarantee that the trajectories would be time-like. It could become space-like. But you see, the caveat is that you're not measuring it. So if you measure it, the wave function collapses. So as far as the prediction, see, the point is the only input is the wave equation. I did Schrodinger just because it's just easier to explain. But then I did have a slide on the Klein-Gordon and that kind of thing. So the formalism goes through. There's no other input other than the wave equation, and the predictions are all same as the normal Copenhagen interpretation. If one wants to attach too much of physical reasoning, physical meaning to the trajectories, then yeah, the trajectories become time-like. But
no, but you have even more problem. You have the same problem which is related with Klein-Gordon equation, that the density of probability might be negative. This sigma. It's because it inherits exactly the same shortcomings as Klein-Gordon.
Right. But that's not a problem of this formalism. That's a problem of relativistic quantum mechanics. So what you're asking, yes, relativistic quantum mechanics has its limitations, as we all know, and we can continue the discussion. But that's not a problem expressed to this formalism. So all I'm trying to say is that this formalism is completely equivalent. And when researchers raise the question of relativity, and there's good reason behind it, I get the point. But it also, the issues are mostly related to the physical, the physical nature of the quantal trajectories. And if you don't attach too much importance to. I mean, in quantum field theory, right? Like we have the virtual particles which are off shell. We don't care because we don't see them. So I take that point of view that technically the steps are right and it gives something useful. To me, it's basically just a useful tool without going too much without investing too much into the interpretation. But you're right. That's one of the reasons why this approach is not very popular. And as you probably know, because you mentioned Madlung as well, it is actually used quite extensively in many other branches. Like
that's right. That's right. Yeah, it's the fluid dynamical description of quantum mechanics, which is very popular. Yeah, that's maybe a reason why people like to work with superfluidity.
Yeah. It's all kind of, yeah. And also keep in mind that's not to justify the relativistic use. The justification is what I mentioned. But also keep in mind, which was why I kind of confidently use the non-relativistic to demonstrate the point, nothing else, is that, if you apply to cosmology, I mean, Newtonian gravity is more or less sufficient, right? So just to, because its curvature is very small and that kind of thing. But again, as I said, that's an added bonus that doesn't justify the approach per se. But thanks for your question.
I have a curiosity, Saurya. You quoted Alessio Figalli in your paper on the quantum version of Raychaudhuri Equation. So I was curious to know what is the connection with this topic.
I'd have to get back to you on this. This is like I derived this like 6 or 7 years ago, and I obviously put in the references that I thought are all useful. This particular reference, I don't remember right now what exact part of that thing I used, but I can definitely look it up and give it to you. I mean, get back to you.
Okay.
Thanks for asking. So.
Okay. So, Saurya, I would like also to ask you something. First of all, I apologize for having pronounced your name in the wrong way before.
Saurya, I mean, I'm lucky that nowadays names are not just some alphanumeric. I don't care, but
okay.
Yeah, it's good.
Okay, so I just wanted to ask you, as far as I've understood, everything, all your formalism and all your interpretation related to the Friedmann-Robertson worker and then the cosmological constant boils down to that term, which typically should be zero, but instead you identify it with that quantum potential. But I was thinking, in principle, that very term could be non-vanishing, not only because of the presence of some quantum potential, as you've said, but also, for instance, if you consider some extended model of gravity, probably the Raychaudhuri equation will be different. Or I was also thinking of some other thing, a more conservative approach. That term, it seemed to me that it was somehow related also to the equivalence principle. I mean, if equivalence principle holds, then that term would vanish. But if, for instance, we consider a finite temperature scenario, that term should survive in principle because at finite temperature, the equivalence principle does not hold anymore. So can also this can be viewed as some sort of effect? I mean, it can be, it can substitute your approach or it can enhance, I mean, what you said, but in principle, can this also be viewed as a...
I agree. So just one quick clarification, if I may. So, and I think you're right, but just to clarify. So are you saying that because the geodesic equation per se will not hold good for the systems that you mentioned, right? So there'll be extra forces.
Yeah, I mean, no, in principle, so, I mean, I was thinking in particular the equivalence principle, but the term that in your case would be vanishing, but you substitute with your quantum potential, in principle could be non-vanishing by simply forgetting about the quantum potential and implying that and imposing that the equivalence principle does not hold at finite temperature. So, in principle, in a finite temperature analysis, the existence of a non-vanishing temperature would prompt all this stuff.
Indeed. So the equivalence principle. So firstly, looking at it from the other way around, whatever I have violates the equivalence principle, because so that's it. But yeah, so anything absolutely. So anything which violates the equivalence principle would change the Friedmann equation, but it would also change the Einstein equation, right? So there'll be all this question of new solutions. And interestingly, I mean, we perhaps all know this, but interestingly, Einstein's own derivation, as in his book, he derived his equation purely from the equivalence principle. And if one follows the steps, any any additions to the equivalence principle will entail additions to Einstein's equation. So which means there's this whole slew of work, new solutions and new everything. Yeah, I mean, I didn't have time to look into all those details, but absolutely. So the equivalent, any violation of the equivalence principle would entail terms in the Raychaudhuri equation, Friedmann equation, and Einstein equation. And one last point, which is, I don't know why people don't play this game, but there was a few papers in the beginning where from string theory, for example, or loop quantum gravity, or from other approaches, researchers tried to actually get a repulsive / positive term in the Raychaudhuri equation, because that is one way of, trying to avoid singularities. And part of it, I guess, like they got interested in other things, trying to, but this is a good way of resolving singularities as opposed to, naively looking at the Kretschmann scalar. I mean, Kretschmann scalar is a good indication, but this is a kind of a sure shot of avoiding singularities. So.
Yeah, because one can also look for, as I've said, more conservative approach and something that can also be explained in terms of quantum field theory of space-time, but with ordinary geometry. So it's at least it seems in principle. Now one should do the calculations again, but it seemed to me that there can be some explanation also in standard scenarios.
Yes, and indeed, if any of the standard scenarios give rise to a positive term in the right-hand side of the Raychaudhuri equation, it's worth exploring what the application is in terms of singularity. Absolutely.
Yeah.
Thanks.
Okay. Okay, so are there any other questions or observations? Well, actually, we are also losing people in the meantime, but of course, I guess I can compare. Some of them probably have to go to sleep. Some of them have to do other issues, but we are also
discussion.
Huh?
They lost a nice discussion.
Yeah. I must admit it was a discussion session. Yeah. So, I mean, as all the beautiful things, they must come to an end. So I guess that we can end also the discussion session, and so the third day of this meeting and of this conference. And so we will reconvene tomorrow, I guess, at okay, it's 12 Central European Summer Time. Oh, the German will be Luca Smaldone. So good luck to the speakers.
I'm very precise, Chairman.
So I would like to thank Saurya, Peter, and Fabian for their presentation and their patience to be with us until the end of this discussion session. And so this day is over. So thank you again, and we will meet tomorrow.
Thank you. See you.
Bye. See you tomorrow.
See you.
Bye-bye.
Bye.